Good morning, distinguished guests, ladies and gentlemen, and welcome to the International Workshop on Future Communications. My name is Wayne Chan, and it's my pleasure to be your host at this important event. Now, information and communications technology has progressed significantly in recent years, with the introduction of concepts such as Industry 4.0 and Internet of Things. Billions of devices will be connected in a global network through wireless interfaces using standard protocol solutions. In today's workshop, we will explore the technological changes that provide us a huge leap forward in speed, capacity, and connectivity, the challenges we face moving forward, as well as the efforts underway to consider beyond state-of-art protocols and mechanisms for wireless, data, and network communication. Over the next 2 days, we'll be hearing from 10 distinguished keynote speakers on the future generation of communication to meet new demands and challenges that go far beyond distribution of voice, video, and data. Now, this workshop will not be possible without the generous sponsorship of Huawei International Private Limited, MPIX Innovations Private Limited, Roda and Schwartz Asia Private Limited, and the support of IEEE Communications Society. Thank you very much to our sponsors and partners. And now, to officially kick off today's event with his opening address, I would like to introduce someone who actually needs no introduction. He's an IEEE Fellow and is a widely known authority in low-power RF MM-wave IC design and a recognized expert in CMOS technology. Ladies and gentlemen, let's welcome the Associate Provost, Research and International Relations, Singapore University of Technology and Design, Professor Kiat Seng.
Distinguished guests, ladies and gentlemen, a very warm welcome to the first International Workshop on Future Communications. I'm Kiat Seng, Associate Provost at the Singapore University of Technology and Design, in short, SUTD. To our overseas participants who may not be familiar with SUTD, SUTD is Singapore's fourth public university established in 2009 to pioneer interdisciplinary research and design innovation. Let me give you a quick introduction of SUTD. The vision of SUTD is to nurture technically grounded leaders and innovators to serve societal needs through an interdisciplinary, design-centric education and culture. SUTD emphasis on design and attitude beyond the book knowledge allows students to develop soft skills in creative thinking, problem solving, and social emotional skills. This fosters a growth mindset of continuous learning and entrepreneurship. We offer programs that break down silos to bring together cross-disciplinary learning, global exposure, and human-centric education. Coupled with a personalized, no one-size-fits-all education model, it offers flexibility, diversification, and choices for students to pursue pathways that suit their talents and interests. SUTD's programs are structured in terms of what the world needs: products, systems, and services. We are organized into 4 pillars: engineering product development, engineering system design, information system technology and design, and architecture and sustainable design, which are distinct from the traditional disciplines or schools. We combine these technical disciplines with 2 clusters: humanities, arts and social sciences, as well as science, mathematics, and technology. SUTD is a research-intensive university and one of the first universities in the world to incorporate the art and science of design and technology into an interdisciplinary environment. With deep collaboration with some of the top universities such as MIT, Zhejiang Universities, and Aalto University, SUTD is distinguished by its unique East and West academic and research programs, which incorporate elements of innovation, entrepreneurship, management, and design thinking. In 2018, SUTD topped the list of emerging engineering schools in the world by MIT benchmarking study on the global state of the art in engineering education. In addition, in 2017, Carivac Analytics released the State of the Innovation Report, which analyzed year-on-year research and patent activities in 12 industries between 2006 and 2016. Its studies ranked SUTD as the 5th most influential scientific research institutions globally in telecommunications. Currently, SUTD is in the process of setting up a mega research centers on future communications. The center will focus on 4 disciplinary areas: connectivity, hardware, edge computing and intelligence, and cybersecurity. The main objective of the center is to bring together local and international research institutes, universities, industries, and agencies together and provide test bed and tools to support digital innovation and technology translation. The center will also participate in standards to ease technology adoption and increase international impact and visibility. As the future network will become extremely heterogeneous, it will bring great challenges to wireless connection, spectrum share, as well as data fusion. With Internet of Things, billions of devices will be connected in a global network through wireless interfaces. The connectivity of these ubiquitous devices will be heavily relying on wireless communications. Therefore, the challenges such as scalability, reliability, signal coexistence, data rate, and energy consumption faced by existing systems need to be thoroughly analyzed. We all know that engineering education has evolved with the changes brought about by the first, second, and third industrial revolution. Digital transformation has ushered the world into the fourth industrial revolution in the 21st century, which is also known as the connected revolution. So when we talk about the connected revolution, we will immediately think of the huge opportunities behind 5G, AI, which is artificial intelligence, and the Internet of Things. The combination of 5G, AI, and Internet of Things will bring change at a speed, scale, and scope unlike anything we have experienced before. It will affect the very essence of human experience. The interplay between them will create realities that were previously unthinkable and impossible. Currently, most of the devices and systems are connected via wireless technologies, and numerous emerging solutions and applications are proposed based on wireless communications. So with the introduction of concepts such as Internet of Things, billions of devices will be connected in a global network through wireless interfaces using standard protocol solutions. Furthermore, due to the explosive growth of mobile devices and 5G connectivity, wireless transmission and greater than 1 gigabit per second data rates is becoming essential. So as a result, the network infrastructures will be endowed with an unprecedented degree of intelligence, integrating with the environment and offering fast, secure, and reliable communications. However, it is extremely challenging to achieve gigabit per second data rate applications below a 6 GHz band due to spectrum scarcity. Therefore, the millimeter wave has drawn increasingly interest over recent years to enable ultra high-speed wireless transmissions. It will transform the way we live, play, work, and even travel when deliver more performance, efficiency, and comfort, as well as to provide a huge leap forward in speed, capacity, and connectivity. Hence, efforts are underway to consider beyond state-of-the-art protocols and mechanisms for wireless communication. Thus, the next generation of wireless communication is expected to meet the demands of various challenging use cases that go far beyond the distribution of voice, video, and data. I'm therefore delighted to know that this international conference aims to discuss the open problems and present new solutions that address the challenges of future communication system. Finally, I would like to thank our keynotes, our speakers, the conference participants, IEEE Communication Society, and our sponsors, Huawei, Roder and Swart, and MPIC's Innovations for their strong support. My special thanks to the conference organizer, Lin Chiu, and her team for putting together this wonderful program for everyone. Thank you and enjoy the conference.
Thank you so much, Professor Yeo, for that brilliant opening to kick off our conference. And now, for today's session, we have a schedule packed with lots of really amazing content. And to help you make the most out of this event, we're going to have to be very mindful of time. So please don't be surprised when you hear this chime playing at the end of some of our talks. There it is. It's just a reminder to our speakers that their allotted time is up. So once again, don't worry if you hear this. There's no need to adjust your computer settings. That's just a reminder about time to our speakers. And also, don't forget to type in any questions that you might have for our speakers into the chat box. They'll be very, very happy to answer your questions if there's enough time. Now, coming up next, our first keynote of today on selected topics for 6G enabling technologies that will look into perspectives of the emerging wireless technologies and discuss the open problems, the R&D roadmap associated with these enabling technologies. And to tell us more about all of this, I would like to introduce our first keynote speaker for today. He is an IEEE Fellow, a Huawei Fellow, and an industry-recognized leader in the invention of advanced wireless technologies. He was the recipient of the IEEE Communication Society Industry Innovation Award in 2014 and the IEEE Communication Society Distinguished Industry Leader Award for pioneering technical contributions and leadership in the mobile communications industry and innovation in 5G mobile communications technology in 2018. Wow. He's also a recipient of the R.A. Fessenden Award, or should I say the R.A. Fessenden Medal, rather. Ladies and gentlemen, let's welcome the Chief Technology Officer, Wireless Network, Huawei Technologies Co. Limited, Dr. Wen Tong.
Hello, everyone. I'm very pleased to have this opportunity to participate in international workshop on future communications. I like to talk about the future, and I'm in particular excited to see the vibrant and young Singapore University of Technology and Design is a rising star of our community. Thank you for the invitation. Looking forward to working together with you. In my talk, I would like to share my views on 10 enabling technologies which have the potential to be mature as a mainstream in communication areas. My intent is not to make a precision prediction, but to stimulate our thinking. Some of the discussions are over-optimistic. However, let's follow the proclamation from Alan Key. The best prediction of the future is to invent future.
For the past 40 years, wireless communication had a phenomenal success. Mobile technology became a dominant driver not only for communications, but impact every aspect of our daily life and work. Wireless revolution has fulfilled the mission to connect everyone in the world. And with 5G, we are entering into a new stage for connected everything. Communication infrastructure is a platform for the digital transformation of every business. With the rise of AI, in next 10 years, we are very well in a position to create connected intelligence future. And this will be realized by 6G wireless. Before we dive into the discussion of future wireless technologies, let us look at the top transformative technologies that can emerge in the next decade and has the potential to change the landscape of wireless communications. In my view, with next 5 years, there will be some continuous breakthrough in deep learning technologies. The machine learning will be full steam to drive the massive innovation in both hardware and software. It will certainly have a huge impact on communication technologies and services. The next is the fast innovation in low Earth orbit satellite communications. It will realize the full Earth coverage of connectivity and shape the future of mobile technology. And it will be a reality in next 5 to 10 years. The third is quantum technology, both for computing and communication. Quantum computer and quantum network will have a long-term impact to revolutionize the internet as we know today. In this talk, I would like to articulate 10 technologies in the communication area. To pick these selected topics, we'll try to balance the academia research interest and industry practical challenges. And of course, from my point of view, they have a large impact to design of the 6G wireless. Certainly, I will have the risk of ignorance of some of the innovation from the research community. And these topics are cognition for communication, semantic communications, mobile network for sensing, extreme side link, mega LEO constellations, quantum networking, MIMO topics, physical security, in-network computing, and green communications. The first topic is the brain cognition-based future communication, especially for wireless communication. The ambition for this research is to look into the aspect of communication based on the information bit is not the only game for communication. With the success of a deep learning technology, we can revisit our quest in the communication of human brain-like intelligence. To discuss the artificial intelligence for the future communication, the first question is what is the scope and the capability for artificial intelligence? Here we would like to apply some of the theories of human minds. In particular, we find Daniel Kahneman's work on the analysis of cognition of a brain is useful. The key result of this work is the study of both automatic and the more rational thought process of a human brain. We can tackle the artificial intelligence research by exploring the concept of two systems of the brain. By identifying the function for two systems in our brain, we can understand where is the boundary for AI research we should focus in the near future. In Kahneman's theory, human brain consists of two systems. System 1 is a small portion of a human brain called limbic. This part is formed from 400 million years of evolution. Kahneman identified human intelligence associated with System 1 with the following 6 key properties: fast, automatic, associative, unconscious, impulsive, emotional. System 1 is accountable for 90% of intelligence of the brain, while System 2 is a very large portion of the brain called neocortex. This part is formed from 4 million years evolution. Kahneman identified human intelligence associated with System 2 with the following 6 different key properties: slow, logical processing, analytical, conscious, reflective, deliberative, rational. In a simple term, system is a higher and sophisticated human intelligence, and our current research on artificial intelligence is not yet fully capable to handle these complicated human cognition process. On the other hand, the recent progress of AI can be successful in terms of performing the System 1 functions. The concept of a new model is shown in this chart. Here, we model the 2 users, and each with 2 systems, namely System 1 and System 2. The communication and their deficiency between System 1 and 2 are the core part of the theory of a Kahneman study, i.e. the link between S12 and S11 for user 1, and S22 and S21 for user 2. Our interest is to study the communication between user 1 and user 2 at the System 1 level, and i.e. the link of S11 and S12. And perhaps the most interesting part is the communication at the System 2 level, that is the link of S21 and S22. The key assumption for this model is that the deep learning technology can model System 1 very well after a very long training of an individual for user 1 and user 2 separately. We can make such a model for System 1 as a replica or local digital twin available for the other party. In this way, we can deal with the communication instantaneous interaction between System 1 and System 2, between user 1 and user 2, locally, and avoid use of communication networks. In this way, communication between the 2 users can be reduced much more slower process, in the true sense of the System 2 communications. This is a real sense semantic communication, or even in the effectiveness communication. Semantic communication has been put aside for the communication research for more than 60 years because of the huge success of Shannon's information bit-based communication framework. Shannon deliberately avoided semantic in all his communication technology framework in order to focus the efficient and reliable information transmission. However, with the progress of the deep learning technology, we can re-examine the feasibility of semantic communications. In this chart, I would like to propose a new machine learning communication model based on the theory of System 1 and System 2 framework. In his joint work with Shannon in 1949, Warren Weaver categorized three levels of communication models. The first is a technical level, which is the Shannon information theory. The second is a semantic level. The third is effectiveness level. Since fundamentally communication of intelligence is a learning process as well, the two or multiple communication parties can use deep learning to learn communication context in a specific use case and scenarios. Therefore, it is possible to build up semantics and even grammar for the text context after sufficient learning and training. The deep learning model can handle the meaning over the communication at the semantic level or even at the effectiveness level to compress the actual transmission data without loss of intelligence. To elaborate further, the new machine learning-based communication paradigm consists of three parts. The first part is a Shannon inner communication channel. The second is the local communication between System 1 models. In other words, interdigital twin communication. The third part is the System 2 communication, and it is a so-called semantic level, which is in fact the semantic outer channel communication. The model has several new properties. It is a low throughput and low latency because deep learning neural network contains a huge amount of memory. After training, the memory captures the self long-term information and the other party's long-term information. To explore the context of memory, we can effectively remove the redundancy of the communication, which the entropy-based method cannot do. One of the most potential breakthrough for the machine learning-based communication is the robustness nature against the channel outage. This is because fundamentally, with this model, System 1 is always on in the cyber world, and System 2 can be on and off. When a mobility user is out of a coverage area, the perceived communication cost still carries on. The interaction among the System 1 are not interrupted, even we lost the communication channel. If we have success in this deep learning-based communication model, it will be a really breakthrough for 6G. The radio wave by nature has a rich property in terms of refraction and scattering. But for the communication purpose, these are not very useful for information transmission. However, the future communication system will not simply just for connectivity, but also for the can be expanded into sensing. In particular, the combined sensing and communication will be critical for massive data needed for the deep learning-based AI. Sensing by using wireless network is a game changer for 6G. We can natively integrate sensing signal into radio transmission wave for every 6G base station, every 6G device. The radio transmission at a wider channel and smaller wavelengths can provide much higher resolution for the real-time environment of the entire network. Even so, at device side, we can use the terahertz technology to scan and retrieve the material detection imaging for many new applications. Therefore, 6G is a network of sensors. It is a cross-sourcing and federated sensing from billions of devices. Furthermore, we can use device-assisted network and network-assisted device sensing to overcome the obstacle such as non-nanover of sensing. As shown on the right side of the chart, the cooperative sensing and communication will allow 6G network to see almost everywhere anywhere in the environment. The device can send the sensing information to the network so that the network can synthesize the sensing result even for 9-hour of a case. Of course, the additional sensing information will be able to utilize to assist to enhance the communication performance. It is very effective in the case of a millimeter wave communication for the beam processing and management with more sensing assisted side information. This can reduce even or eliminate the beam search scanning overhead to reduce the power consumption and extend the battery life. Here, in this chart, we have two examples. On the left-hand side, the UE is in the blocking shadow and cannot communicate with base station. In this case, UE will trigger the side link information to set up a data link path where other links such as D2D side link or, for example, a pad as a reconfigurable intelligent surface. On the right-hand side, the sensing of the people and the car can assist autonomous driving to avoid the blind spot for both for autonomous car and the blind spot for the people as well. Device-to-device communication is a very old topic, but so far it has no commercial success. There are a couple of factors, such as the data rate is not very high compared to the network access. It drains battery power and without any other benefit, and the security is a showstopper. For the future communication systems, several new opportunities can enable D2D communication. For example, the V2X require extremely high-speed side link. Virtual reality and hologram communication require a short-range wireless connectivity, and the emerging terahertz communication can deliver these capabilities. This is a human-centric D2D connectivity picture. It is based on the millimeter wave or sub-terahertz short-range technologies. Because of the availability of a large bandwidth, the link data is at a range of 1 gigabits per second to 100 gigabits per second to enable those XR type of applications. On the other hand, the low power consumption target is very challenging. The design is heavily focused on the energy efficiency rather than the spectrum efficiency. In this case, things like 1-bit analog to digital conversions, signal waveform, and extremely low power FEC decoder will be required to achieve 0.1 milliwatts to less than 100 milliwatts target. In addition, the beam searching and beam management will have to be much more efficient. The transmission and the user data rate, transmission range and the user data rate is plotted with different semiconductor technology implementations. We can see among 4 different mature technology, namely the CMOS, the SiGe, BiCMOS, 3.5, and photonic transmitter, we can see the current status of a sub-terahertz implementation is around 100 gigabits per second and tens of to hundreds of meters of range. Among these, CMOS is out of scope, and the 3.5 technology is promising and worth a good investment for the to further optimize the performance. As a major use case for extreme side link, here is the current autonomous car uploading data rate requirement. The huge amount of sensing data is required to upload to the RSU, i.e. the roadside unit, for cloud to perform the autonomous driving processing. These sensing data include LiDAR for 560 megabits per second, camera 320 megabits per second, radar 0.8 megabits per second, and GPS. The total amount of data for every day is at 4 terabytes. And in 6G, the more advanced autonomous driving car will require to upload tens and more time updated data rate in real time. Short-range sub-terahertz transmission is a promising technology for many other industry applications as well. Space communication is always fascinating. It is always challenging for challenges the communication technology to the next level. As I mentioned before, recent breakthrough is the possibility of a massive low-orbit satellite network. Coincidentally, as is Tom Stone, the space pioneer and architect Werner von Braun, it was inscripted only one word from the Bible, Psalm 19.1, which implies the sky above proclaims God's handiwork. Fully integration of all these network elements in terms of satellite constellation for 6G architecture design is our object. It's one of our goals. Our vision is that these elements will not form several separate network and independent network. They should be designed as a single network at day one, which means for the radio capability of the network element heterogeneous, but the network is unified in the air interface and mobility management. So we can leverage the global ecosystem and achieve the economical scale. Up to date, the uplink budget is still the bottleneck of non-terrestrial network. There are several new and interesting capabilities enabled by the very low Earth orbit satellite constellation. First, on the left-hand side of the chart, we can see the cloud edge computing can transmit to the band-pipe satellite and to bounce the signal directly to the car. The autonomous driving can be controlled and operated by the edge cloud, where there is no cellular coverage. Another scenario is the smart grid, where low latency service can be applied to the bandpipe satellite to broadcast control command to all the stations and the smart grid with a minimal delay. Second, the video satellite constellation can deliver minimal latency service in intercontinental communication scenarios. It is faster even than the dedicated fiber because the speed of optical transmission is about 70% of a free space light speed. The third is the integrated terrestrial and non-terrestrial satellite. The mobile device can use the dual connectivity mode to avoid the coverage holes. This is a chart I used for the GlobalCom in 2018. In this chart, I did a quick analysis of the capability of a video constellation. This was before the SpaceX announced the Starlink. Now it is almost become a reality. The key disruption is the reusable rocket will dramatically bring the cost of a satellite constellation down. I'm very confident that that in 5 to 10 years, this type of a non-terrestrial network will be economically viable. The quantum technology will play a big role in future communication. The foundation is the Bell inequality to that Bell that prove the long-distance entanglement of the qubits. It is not difficult to understand with the quantum entanglement. We can re-examine the encryption and the network routing. One of the challenges for the quantum key distribution is the limited to 2 users so far. To generalize to use many users case for networking purpose, if we use the multiple qubits entanglement, it remains an open problem and a huge technical challenge. Here we present our work in this topic. Essentially, we use a pair qubit entanglement technique in combination with a BB84 protocol to generalize to many users. We consider this result is a breakthrough. For the routing, we can use the concept of entanglement pair qubits chaining techniques as shown in this chart. It is also called quantum repeater. It is basically applied quantum measurement between the 2 pair and chain them together. Well, with the flexibility or even programmable of the quantum measurement, we can program the routing and set up the data path. Since the end-to-end is entangled, the information can route from point A to point B. In my opinion, MIMO is an excessive studied area for communication community. It is also a hugely successful technology, although we still have many engineering and optimization challenges. What is more desirable is the new technology for MIMO. Some of the new proposals are still questionable for their practicality and to be widely adopted by industry. I would like to share my view on the MIMO aspect. From the industry point of view, the MIMO technology can be categorized into 4 parts. The first part is classical MIMO. The 4G LTE standards capture almost all the research results for MIMO. Here, every smartphone is implemented with 10 MIMO modes. However, these designs are not scalable to the higher frequency bands above 2.6 GHz. For 5G, we developed the massive MIMO technology for 2.6 GHz to 5 GHz bands, and the hybrid beam forming for above 26 GHz millimeter wave bands. As we can see, MIMO technology is heavily dependent on the channel propagation characteristic. The next technical problem is to study the solution for the bands above 5 GHz and below 15 GHz, where the MIMO channel property shows a strong Rayleigh characteristics with a typical, for example, 16 antenna on the smartphone factor. Here, there are a lot of work need to be done. The reconfigurable intelligent surface is now a hot topic for the research community. It generates a lot of enthusiasm. The proposed merit of the RIS are around passive surface with no active radiation, steerable reflection to improve the coverage, large surface to achieve higher gain, the intelligent steering to control the interference, high capacity gain with low cost surface. In the reality, it is not the same as Archimedes' mirror. There are several key practical issues need to address. For example, the need to control subsystem and fix the backhaul near the G node B to gain the strong reflection power, site selection and installation as a base station. The fast and dynamic control surface could be difficult. The site acquisition and additional O&M elements will make it complicated. I would like to plead academia researchers to look into those aspects. In 1943, Shannon proved that for Verdun one-time pad key scheme, once both data rate and key update rate approach the Shannon channel limit, such communication is a secure one. For 6G, we can realize this by introducing full duplex radio communication by using the random channel as a security key. On the left-hand side chart, it shows the one-time pad key scheme concept that is basically is a symmetrical encryption. The secret key is operated at the same data rate as the information rate. It has two problems in reality. First, we will have to reserve half of the channel capacity for a secret key transmission. The second is the symmetrical key delivery has a high risk to be intercepted. The solution will have to address how to generate the symmetrical key delivery mechanics. Our proposal to the solution is to retrieve the random channel with a full duplex radio such that with the same channel reciprocal property and both the encryption and decryption end part, we can apply identical random channel to achieve one-time pad key security. We have successfully conducted a real-world field trial for full duplex radio, as shown in this chart. The multiple UE is in the same sector can be allocated to run full duplex transmission. Furthermore, we also show achieved the so-called bandwidth part full duplex. In other words, it is a hybrid full duplex and TDD-FDD in the same frequency bands. And the full duplex subband can be flexibly assigned. The number 9 topic is the in-network computing. The convergence of communication and computing will generate new research topics to look at how to integrate distributed computing with the communication networks. In particular, for the efficient AI service, how to split the computing of an AI model at different parts across the network, how to architect the neuron center and the neural with the pools of computing resources, how to orchestrate the neural resources. In 6G, we will have a huge amount of data with several magnitude order larger compared to today. These massive data sets are just used for deep learning and generate the AI model purpose. We don't need to transfer this type of data set around the world and share. We have to make this data set to comply the local regulatory requirement as well, such as the GDPR in Europe. The AI model is more important than data. The data can kept at the local, the model can be exchanged over the networks. And this requires in-network deep learning, in-network computing as a fundamental requirement for 6G. The distributed learning and distributed inferencing will be the dominant computing for the future wireless communication network. To support the low latency inferencing with distributed computing, it is always desirable to compute a small model at the device or network edge to achieve low latency with less computing effort. However, in many cases, we have to make a trade-off for computing of a huge model to achieve good performance. The inferencing computing with small model and medium model and a large model is not a trivial task. The partition of the model is also associated with the model training and the model creation process. In this chart, we give an interesting example for that is the early termination. In the decision exam at the fully connected layer for convolutional neural networks, if the confidence of early termination is not high enough, then we need to perform the inference computing at next level. In this case, the previous level of computing result is not wasted, and we can use the weight sum of loss function to assist the next level decision. One of the most recent work on the network coding for the inferencing is very interesting. Since the neural network is nonlinear function, the linear code for multiple inferencing input vector cannot be easily reused for linear network coding concept. However, by using additional smaller neural networks as an encoder and the decoder as well, we can achieve the network coding effect, meaning even some of the inference computing is failed or encountered a large delay, we can still successfully decode the inferencing result. The number 10 topic is green communication. Green and sustainable development are the core requirement for network and terminal design for 6G, which is a 6G time window. It is also the time window for controlling the global warming. By introducing green design concepts, 6G should aim to improve the overall energy efficiency by 100 times across the network, while also ensuring optimal service performance and experience. As the core infrastructure for digital economic, 6G will make a unique contribution to the sustainable development for humankind. Two big drivers for energy efficiency for 6G. The first is a deep learning computing demand is doubling every 3 months, and the open source software has difficult to sustain. The second is a low latency for millimeter wave RF amplifier. The single digit efficiency of a power amplifier and yet to overcome additional 20 dB propagation path loss. These two are long-term research problem for the research community and to look for the new solution and disruptive innovation. To summarize, we talked about 10 enabling technologies, and they are critical for the development of 6G wireless system. We are excited that the research community can look into these challenges areas and make breakthrough. With that, I conclude my talk. Thank you very much.
Thank you, Dr. Wen Tong, for that very interesting presentation on 6G enabling technologies. And now we will move on to the question and answer segment. Now, Dr. Wen Tong, we've got a couple of questions from our audience right now. The first question that we have for you is this. What is the difference, or what is the difference between cognitive and semantic networks? Don't they refer to AI-based network intelligence? What is your answer or your thoughts to that?
Yeah, sorry, can you hear me?
Yes, we can hear you loud and clear.
Okay, yeah, so this is a question need a further discussion, because the AI today is a very generalized term. So it means a lot of things to a lot of people. But when we come down to the communication, and the specific AI that is implementable from industry point of view, which is a deep learning. So deep learning is not, so far cannot cover all the AI aspect or humanity, the human cognition as well. So for example, the AI as of today, they don't have a causality, meaning that they cannot reasoning. So the thing like this is for the communication, especially we go to what is the meaning or intelligence level of communication, the semantic level. So we need to put some kind of a scope to in order to proceed a right architecture at this time frame, let's say 10, 20 years. So in that case, system 1, system 2 is a better way to clarify what is can handle by machine learning and what is yet not can handle by machine learning. And that portion need a communication. So I guess that's what I'm trying to say here.
Thank you, Dr. Tong, for that answer. And I hope that managed to address the that question from our audience. We have another question for you. And this is, when we are speaking about modern development and changes of communications and communication systems, according to your opinion, how will new forms and technologies of communication influence interface and relations between people? What do you think?
Oh, yes. So this is a very good question. The interface, the human to human interface, human to machine interface, let's say not machine to machine interface. This is a very big step as every step we go for the communication. For example, the success of an iPhone is the interface with a touch of the screen. So in that case, make many things possible and more convenient than the interface we have before with a feature phone or even desktop, desktop phone. So ultimately, you want to have an interface. First of all, can understand your emotion, your gesture, let's say that level. I think that will be feasible in the next five to 10 years if somebody need. This is our engineering innovation and optimization that we need to do that. And then second, further down the level, that the interface that you can understand the meaning of your communication parties in order to do that. That is neither. This is the part of my discussion of the AI. That means you have a memory, you have some familiarity of your party. So before you communicate, you already have understand quite a bit, either semantic context or that kind of thing.
Thank you so much, Dr. Tong. That was a really comprehensive response to that question. I'm sure our audience members are truly enjoying all of this. We have one more question. Is there time? Yes, there is. Great. Now, this next question, Dr. Tong, is this. Is extreme side link similar to the concept of integrated access backhaul? What do you think?
Some of them, yes. That is a portion of this sort of excessive side link. The distinction is backhaul is long distance. Typically, the side link is short distance, 10 meters or let's say 50 meters longer, not longer than that. The second one is backhaul typically are fixed. That means point A and point B is for long time is a fixed connection. But side link is a very, very dynamic because you move, environment change, you are entering different room and with different people, etc. So that the dynamic part is very different than the backhaul.
Thank you so much, Dr. Tong. And of course, that answered the question on side link and backhaul. We have another question. I got to say, we have lots of questions from the audience. And this is another one. Due to the unique benefits of in-network computing, does it make sense to see more of its applications in mobile edge computing? What are your thoughts on this?
Yeah. So where to compute is typically depending on the application, especially on the latency. Yes, mobile edge is one of them. That is from technology point of view. But now we have the governance of the data. That means the regulatory will control the data. That means the data may not go to certain country or certain region because of privacy and because the ownership of the data. So that's where the trends need to break down the computing into different portions and yet to respect those regulatory aspects. And as well, there will be some recent good research show up that federated learning, that means the learning not shipped into one, let's say Google gigantic data center to compute AI, rather than spread a lot of places. That is a green approach, meaning that total consumption of the power and the energy and the carbon emission, reduce the carbon emission, these are good. So there are other factors as well, indicate the trends that need, the in-network computing, in, let's say general, that term will be beneficial.
Thank you so much for that answer. And we still have 10 more minutes, and I got to see the questions are just getting longer and longer. Lots of questions for Dr. Tong. Everybody's taking advantage of this time. Here's the next question for you, Dr. Tong, and it's this. Can you comment on efficacy and urge of fog-enabled vehicular edge computing, especially in context of collaborative autonomous vehicles or CAV? Your comments on this, please.
Yeah, so these are the terminology aspect. For example, is it the fog, is it the egg or age, or that. But in the essence, this especially for the vehicular thing is a distributed. Maybe they have a temporary anchor, but it's fundamentally is a distributed. And it's very dynamic or ad hoc in that nature, but they do that way because there are many for the autonomous driving need and for the communication need, because the sensing require them to do this, or they might be the technology to overcome none of the side communication when you do not have a network. That way will help you. Yeah, so the answer is yes.
Thank you so much. Still have some more questions. The next question for you, Dr. Tong, is this. How high is the reliability bent pipe supported by NTN?
The reliability for that, this is a question that we need a really field test. So far, it looks pretty good because of there are a good way. For example, the low orbit satellite fly very fast, and when you do this band pipe thing, acquisition, successful acquisition, and compensation, all the mobilities aspect seems feasible. Okay, so we have some trials that are very successful, but hopefully it will be reliable as well because these are the 2 millisecond latency up and one down and up, so that you can basically send your command to anywhere on the coverage area. For example, the radius as 500 kilometers. It's very more reliable than the cellular network because there may be somewhere they don't have cellular coverage or network coverage, but satellite covers.
Thank you so much, Dr. Tong. Still have a couple more questions. Next one is this, a follow-up from the last one. It's, will connectivity to NTN now consume more power in UEs? What do you think?
Yes, could be because the UE power is a limitation for the speed in terms of uplink. If you want a direct connect to satellite, that is desirable. Basically, that is a revolution. So far, this is a unsolved problem.
Our next question is about Huawei's involvement in the VLEO revolution, and it's this. How active is Huawei's involvement in the VLEO revolution? Dr. Tong, can you elaborate?
Yeah. So we do research, and we need we there is a we do research. We're sort of support and promote this type of research because this is a technology, a very promising one. But I think at this stage, it is not yet on a commercial, viable level. The economic, as I said in the presentation, the economic feasibility is remains a question. But there's for example, SpaceX is very successful in terms of
Wonderful. Do we have one last question? Is this the last one? All right. Oh, there's still some more. Great. Fantastic. I got to say, this is a real treat for our audiences here. And they have so many questions for you, Dr. Tong, and they're enjoying every second of this. This next question is, what is your opinion about 6G information security, especially under the US-China trade war situation? Very interesting. Dr. Tong, your thoughts?
Yeah, let's take it two parts. One is a geopolitics aspect. The other is a technology aspect. So the information security, the network security, those are for the technology side. It will continue progressing. There will be technology innovation in 6G timeframe. But the key for the technology community is how develop a security technology which is quantum resisted, meaning in the next 20 years, the highly likely the quantum computer will become viable. And then this is a challenge for any security system for any country. So as a technology community, I think we need find a solution to make it feasible in that time frame, so that the technology provide the security.
Thank you so much. Here's another question that really looks into the future, and this is the last question for our session, and it's this. What do you think are the key topics for wireless research in the next 10 to 20 years? What do you see in the future, Dr. Tong?
Oh, yes. I talk about as a big opening. I talk about technology in the balancing of two aspects. One is the industry challenging. There are even theoretically mature, but we have a long way to make a technology work and to make a technology commercialized. This is a one set of technology. I hope the academia people can appreciate that. The other is the new communication theory or new communication technology. Yes, I have to say, for the past 20 years, that area is a bit dry. Not as something in the 70s, 80s, and even 60s. There are many theoretical new theories, new concepts created. These days are not, compared to the productivity at that period, that time frame. I think that's where we need. I would like to, promote the research and the put more funding on the research to, to do fundamental and generate a fundamental concept and fundamental technology so everybody can benefit from that.
Thank you so much, Dr. Tong, once again for your exciting presentation on 6G enabling technologies. And I got to tell you, there's still some more questions and we could go on, but we are out of time. But it's been such a treat for our audiences having you right here live, answering so many of their questions. Thank you so much once again, Dr. Tong.
Thanks.
And I believe...
Thank you.
Thank you so much. And I believe we are now ready for our journey towards 6G in 2030, which is coincidentally the title of our next talk. Now, the market demands of 2030 and beyond will likely introduce new applications with more stringent requirements in terms of ultra-high reliability, capacity, energy efficiency, and low latency. And to share more about 5G evolution, his views about 6G and the future communications program at SUTD, I would now like to introduce our next speaker. He's an IEEE Fellow and received the 2008 Philip Yeo Prize for Outstanding Achievement in Research, the 2012 IEEE William R. Bennett Prize, the 2020 IEEE Stephen O. Rice Prize, the 2020 Nokia Visiting Professor, and the 2016 to 2020 Clarivate Analytics Highly Cited Researcher. Ladies and gentlemen, let's welcome Director, Future Communications Program, Head of Information Systems Technology and Design, or ISTD Pillar at SUTD, Professor Tony Quek.
Okay, thank you. Thank you, MC. I will share my slides. Thank you, Dr. Wen Tong, for setting the stage of 6G. I think it's exciting to really see so many interesting topics, and I think the promotion of there's a lot of fundamental topics that are still open to us. We need a lot of work in this research area, especially some of these topics will overlap with some of the topics I will go mention later. I hope we can complement the vision and hope to promote this, especially for both international and for Singapore. So I'm going to step back a bit to look at 5G, then I hope to bring the journey slowly to 6G. We know 5G has just been deployed in around Asia for Singapore. Our deployment is based on the release 15. You think of most of the applications is about higher data rate. In the context of a 5G standard, it's actually called EMBB. What it wants to bring is actually have a high data rate for different type of applications. For example, mobile video, high definition video, mobile VR and AR. So this is one aspect, but there are actually two other aspects of 5G. They open up the vertical services. We talk about Internet of Things. We talk about even satellite just now in Dr. Wen Tong's talk. There's a lot of huge amount of applications that we hope 5G and 5G evolution can bring us, because this will set the stage to 6G. Because the question we want to answer is that with all the different technologies, how does the different technologies in the end serve the different vertical services that can help us, because ultimately it's about improving the society and for sustainability of the earth. So to elaborate a bit more on this 5G standard, in the standard, there's a standard board is called 3GPP. What we actually have been deployed is release 15. There's a 16, 17 for those who are interested and look at different technologies evolution. Particularly 17 will have a lot of use case on 5G or 5G evolution. Release 18 has just has a recent meeting on this month. So if you look at the current standard itself, I'll just, you can look at the slide. This slide is actually also from Huawei. In the release 15, a lot of emphasis on eMBB. So to serve essentially a higher data rate. Then as we evolve, I think, so that's an important part of evolution. So as we start to implement, let's say release 16, 17, then we will actually see the other features, the features that we are looking out, like the massive machine type communications, the ultra reliable low latencies communications that we hope to see in all more of the different use case. So I'm going to bring hopefully to the audience and to community that actually there's a important evolution. There is this 5G evolution for that is from 2020 from now to 2025. In the standard context, that's like from release 18 onwards. These are also areas of research, areas where the community should also to think about as they look at how to invest subsequently in for 6G, because as you see, there's a lot of different topics. But I think it's a progression process, especially for different depending on different companies, agency, or even the researcher. So I would just like to bring about a few trends we see, for particularly especially for Singapore context. I think one thing we really want to look at is the use case, the 5G use case. So there are a lot of use case, as I mentioned, release 15, 16, 17, depending on whether eMBB, whether it's for massive machine type, ultra reliable latency, the different use case. The different use case, for example, for healthcare, for your hospital, for even for port and so on. When 5G comes in, what is the benefit or that it brings about compared to some of these services are using 4G? So you will take a few years to look at that, and what kind of new services or new innovation that we can actually bring about in this. So this is one stage, especially for Singapore context, to actually really look at this 5G use case. Then there's a few other areas which is very exciting. I'm going to talk a bit about this a trend called Open Radio Access Network Alliance, is Open RAN. Which are so the main concepts of this is essentially that if you look at the current ecosystems of whether it's 4G and 5G, there's a few big vendors that dominate the base stations. So with these base stations, the current system is a very closed system. So when you have a current system, a lot of times when you deploy, if you talk about vertical services, then you actually have to rely on a particular sort of vendor from end-to-end system. But there's a trend to look at this open open RAN community, open RAN alliance. So the advantage, of course, currently is to reduce the deployment cost, to reduce the operating costs, where you make the 5G, let's say the base station or the end-to-end system, to be an open platform where it's modularized. So once you're modularized, actually you have the different companies that can come in to produce, to serve different parts. Then you integrate, it becomes a 5G end-to-end system. So system integrated is important. Of course, although it brings flexibility, there's also challenges, security challenges. How do you ensure different module or different module can actually be interoperability? So there's of course there's challenges, but that's a new exciting area that I will elaborate a bit more on that. And continue on that, we also see another trend in 5G evolution, particular around the Asia region, is this concept of a private network. So in the standard, they do have a band, they do have several bands that actually allocate for this private network for N79 or N78. I think in US and in Japan, they're using N79. So it's essentially is to speed up this push of vertical services. So in time, in some of these applications, for example, in a factory, they may not want to, because of maybe data privacy, because they want to have their own network, because the requirements will be different. They are, for example, the requirements on data rate, the requirements on latency, the requirements on reliability will be much different. So they may not want to rely on a mobile network operator to deploy for them. So they want to have their private network. So there's ways of doing that. Of course, one way is I can have a mobile operator that provide this through network slicing. So network slicing is one technology to do that. I can have a private slice for this. That's one model to operate. Another model is actually have your own private network. And that is sort of a business case for this Open RAN consortium, where they want to push, we want to deploy such a private network at a much faster and a lower cost. This could be one proposition. So there's one direction to look up for. Another direction is the unlicensed band. So there's one direction, if you look at the trend, even Dr. Wong talked about going up to higher band. But even at nothing's for free. When you go up to higher band, you will see that basically your coverage essentially is going to be much smaller. You will not have a larger coverage. So in the sub 6 GHz, where you have a much better coverages, you want to actually see the possibility of using unlicensed spectrum. So how does in the 3GPP, there's also a trend to look at unlicensed spectrum. So this is one direction in this 5G evolution to look at. If you want to use unlicensed spectrum for your particular service, how do you ensure it doesn't hurt the services of the unlicensed? For example, you want to use, even you want to Wi-Fi, you don't want to ensure you cause any too much interference to Wi-Fi services and so on. So I think that's an important area in this 5G evolution to look at. So to make the point more specific, particularly for those who are working in this area, as I mentioned, the new spectrum to look at in sub 6, for example, at 6 GHz, to look at the possibility of use sub 6, to look at 6 GHz for another candidate for 5G evolution. So there's a few band. Of course, this has to go through standardization, but you need to do channel measurement. You need to understand the properties of 6 GHz and how does and to think of that. So in the future, if you have 6 GHz, you have around 3.5 GHz, and you have probably some regions would actually second generation or third generation will phase out. You have actually much lower than below 2 GHz. So you have a few band. So when you have a few band, then you have to look at in your system. In your system, how do you ensure at your system level, when you have this 3 band, how do you operate this 3 band in an efficient manner? For example, your services for handover, even to bring in AI, how could this help you to ensure you have this very efficient spectrum access? So this is also related to this fast and efficient spectrum utilization. Massive MIMO as is one important technology as we see in 5G. FDD is still very because the advantage of using FDD is that uplink and downlink are different frequency band. Uplink and downlink, of course, the disadvantage you have to do a lot of channel measurement, but with massive antenna, there's too many channel measurement you need to do. So can we exploit this partial reciprocity using AI to do that? So and I think 5G evolution, we could see some of this. Sub 100 GHz fast and efficient spectrum utilization. So we still see in the community there's a lot of interest to from millimeter wave move up to terahertz. But I think my general sense, we see that depending on the different, some people want to go up to 300 or 200 and so on. a few questions I think we need to really carefully answer that. First of all, it's essentially the market. Essentially, the business model needs to be clear as we go up so high. What is because you have a shorter range. Imagine you will have to deploy a lot of these terahertz type of network. And once you deploy, it's not about radio access, it's also about your backhaul connecting to them. So the deployment is very, very important. The deployment, the economic model is have to be rethink carefully. Second is why particular band. For example, there's news you can see recently, there's results at 140 gigahertz, there's different, and why particular that band? Of course, we need to really understand in terms of the channel measurement. Of course, at the standardization body, they also have to go through the standardization, but also, of course, also related to materials. So at this point, I think if you want to go up to such a high band, in terms of feasibility, maybe at the sub 100 or below 100, I think there's still available quite a big bandwidth to look at. Looking at that and also looking at the materials aspect, the ADC aspects, and how to actually, if you have that band, how to use that fast, efficient spectrum utilization. As I talk about use case, why use case is very important. There's a lot of interest in this AR, VR user experience. I think this pandemic, if you have a chance to be quarantined in hotel for many days, like 14 days or 21 days, I think staying alone in a hotel is a miserable experience. I think if you have the technology to have this immersive experience or AR, VR, holographic, have another person or virtual person talk to you, have meetings, I think the experience will be very different. So the question is that if you have all this AR, VR, the user experience, then I think the question is that, of course, you will expect that all this service will utilize a huge amount of resources. So how do we do resource allocation or user experience optimization? And we may have to actually step back from what we have done conventionally using, for example, channel capacity or using. So what is the right measure for that? Because a lot of all these measures is related to your user experience, right? Your user experience, how do you actually measure that user experience and capture that in your objective function or in your function to ensure this service really is aligned? So I think that's a very important question. So I think the way forward, the KPI should not be a single metric, but it's going to be a bag of metric, and that bag of metric is mapped to your use case. So which means that the way forward is about use case. So identify the right use case and to map back to a bag of KPI and the technologies. I think if that is very clear, then it's for industry point of view, or even for MNO, then they're very clear what type of technology they should invest in. I think Dr. Wen Tong also talked very important about this network assistant. That means the use of this side link where user cooperation, because if you look at a few trends that we can see currently in terms of the UE, we see that even in the release of the Apple phone, the new Apple phone has the possibility of ultra-wideband. It's not just for localization. It's also can be used for D2D, user collaboration for coverage and capacity. We'll see that, but that is not network assisted. So what we can see in the future is that your network, whether it's at the small cell level or your base station level, need to be coordinated in this user cooperation, which is not a very easy process. It is essentially, you imagine that if you have such many links and all the links are very dynamic and they do not last very long, very short. It's very dynamic. It's not a fixed link. And to get the network to be assisted, also you want to reduce the overhead. So it's a trade-off of that and how to manage this in an efficient and sustainable model. I think there are questions we need to answer that. Massive machine type IoT applications, high throughput IoT applications is very important. So we talk about IoT for many years, but if we think about the IoT, a lot of very exciting IoT applications may not be where the human populations are a lot, because in a lot of contexts, you see IoT, you need coverage. So the current base station terrestrial network provide the coverage, but some applications are not where all the base stations are, cellular base stations. For example, applications related to the sea, out in the sea. You need that. You need IoT applications, but of course the base stations is not there. This is one. So which means that satellite will be very important, right? So the integrator of the satellite and terrestrial, I think, is one very exciting area that can actually provide where the base stations are not covered. So you actually want the communication to be actually close to where the machines are and not to where the human are. So it's just very different between where we have done, have deployed our cellular context. So satellite will play a very important role in this satellite IoT. I think in the standard, they are looking at that. Then we have massive, but if when you're high throughput, then I think the low LEO will be exciting area to look at. Autonomous vehicle, 5G for V2X, I think we are all, there's in the standard, there's a lot of development on that. I think at the end, we will have to see a lot of mass deployment, because once we have a mass deployment, I think will be a lot of new challenges that we look at, because the use of, because a huge amount of data need to upload to your radio site unit, your base station. Then I think that is also something to look out for, especially for this 5G evolution, which I think is important. I've mentioned a lot of use case and use case study and deployment, mainly because if you look carefully of how all this generation has been involved, whether from 2G, 3G, you always have this chart of this KPI. And we see that the KPI chart is actually growing as you go for one generation to another generation. Is essentially you're actually pushing to the limit. So as you push this limit, so what will happen, since nothing for free, is essentially you imagine that you're actually creating a systems that is going to be more expensive. Your systems that actually going to meet all these very extreme KPI, but at the end of the day, what is the use case? Some of these use case may only need a few of them, and may need only maybe 50% of this particular KPI, or even 20%. So essentially, what is the best operating point for particular service? So which means that I think one evolution as we move towards 6G, especially we need to take care of this 5G from 2020-25 evolution, is this use case study deployment, trying to understand that, so that you guide us in the future how to, even in the standardization or in the technology we choose, how do we design particularly well for particular use case so it's sustainable? If not, I think it's a bit difficult, because it's actually some conflicting interest. Then of this open RAN and private network, which I mentioned before. So I'll elaborate on this. So this is something you can look at LinkedIn or internet. These are some of these areas, some of these recent news, whether it's Intel is also moving into this area. Rakuten deployment in Japan has been based on this O-RAN concept. There's working with overseas vendor. Then in 3GPP, there's also movement to incorporate this community inside. Nokia as a company that traditional vendor of a closed base station systems are also looking at that. But of course, this is one area to look at. Of course, at the end, it will be the business that drive whether this technology will be the mainstream, but it's something actually to look out for. So since this is a technical talk, I'll just give a glimpse of what it actually looks like. For your interest, if you're interested, you actually can download from this Open RAN Consortium. This is a white paper. So this is what the base station would look like. So essentially, it's modularized. So you have a radio unit. It's like an antenna element. You have a data unit. Then you have a control unit. So there are interfaces connecting to them. Some of them are fiber. All these are actually indicated in the standard, so that for vendor to actually deploy this. So that what interestingly, that there's actually two very important modules that you can like this near real time RAN or radio access network intelligent controller RIC. Then there's a non-real time radio RIC. So this is where possibility the use of your machine learning, or you can call it machine learning or you call AI. I think machine learning is more appropriate. Machine learning tools to be there. So having that, whether you want to do it for scheduling, whether you want to control for your interference management or even your slicing capability, there's possibility that actually you can actually create that and to implement. Even in your, if I want to deploy this as a private network. So we can see that, oh, there's a chance to actually, and not going through a single vendor closed system. So something to look out for from my perspective, okay? So that hope that set the stage of 5G and 5G evolution so that it's important that there's a lot of things that I think we should actually do in this 5G evolution that can help us to better understand what 6G or what we should invest. So I think the work of 6G is actually, the next few slides will be easier. I think Dr. Wonton has really set the stage well for me, and a lot of topics actually has overlap. I think trustworthiness is important. We want actually a communication, whether computing or communication for a particular service, you want to ensure that privacy is ensured, your data is protected. New services, new demands. What it is, something to look out for, whether it's for AR, XR, new sensors, integrated of sensors. I think connectivity is going to be very important. I think there's also an interesting talk later of the day on holographic. I think holographic will be very exciting. Sustainable, I think with all the trend of sustainability, you want to ensure your deployment, because particularly as we see the trend of moving to a higher band means the cell is going to be very smaller. If you deploy more power, it's going to consume power at different level, processing power, computing power, so there's different. So you have to ensure that actually it's sustainable while you enable your society with new services. The use of AI, I think AI is going to be very big. So that the services that, because we have a huge amount of data, you have to process your data. The use of new learning models, I think is important. Deep learning, of course, is one way, but the general trend that you look at that you require to crank a lot of data, but sometimes essentially the feature that you actually can extract only exists in a small set of data. So essentially you waste a lot of computing power actually to do that. So incorporating new type of models to ensure that this is sustainable actually is important. I think federated learning is of course one direction to have a smaller models and distributed. So in line with that, so 2030 is sort of the stage that a lot of in the community or in the 3G community has said, okay, in 10 years time, 6G will be deployed in 2030 or maybe earlier, depending on how fast the standardization will go. Likely in the current status, release 18, I think this year we have started 2021. So we see that the standardization of 6G will likely be around end of 24 or 25, maybe around that time, which means that if we are looking at the research, I think in parallel with 5G evolution type of development and research, from now to 2025 or 2024, these are the time when you really want to do your pre-investment on 6G research, because the working item will actually be identified for standardization about end of 2024 or 2025. And another important point to look at is this spectrum. So there's two very big events, WRC 23 and 27. So these are the likely event where standardization of the spectrum will be done, whether it's a 6G spectrum, the higher band spectrum, or particular your satellite, your low orbit satellite or your inter-satellite communication, or even your drone aerial platform. What is the spectrum you're going to standardize? So this is very important, because this will drive the kind of technology and the investment that whether that industry or agency will actually put. So there's a lot of initiatives on 6G. ITU has said this. Hot topics around the world. Many information you actually can find on the internet. Even the first talk by Tuan, it's exciting with all the different technologies. Different around the region has invested a lot. In China, they started in 2019. Finland Academy of Finland has a 6G flagship. It's an 8-year program. Taiwan, Japan, Korea. Singapore will launch a related initiative and will be announced in July. So I think from a Singapore context is that I think we have to be a part of this, because as you see, what's very clear is that connectivity and communication is going to be more than just a pipe, provide all our vertical services. So having that capability would put us in a stronger position to be a big part of this whole ecosystem and industry. So I'll just share some of these activities around the region. Of course, due to time constraint, I cannot do for all. I'll just show a few. So this is activities in China. So there's this IMT 2030 promotion group. So it's a consolidated national effort. So there's a different, which is very clear. So you can actually find all this information. So there's a requirement working group, tech working group, network working group, spectrum standardization, and there is so it's a very holistic and effort at the national level, where university level, chipset system operator, research institution, and I think they do identify some of these technologies they look at through grant call and so on. If you're interested, you can look at the website MIMO. So there's also international partners inside all this initiative. In US, likewise, the same Next Generation Alliance. They started look at the 6G. In the NSF, there's also grant call related to this. So interesting companies, you'll see Facebook, you'll see Google, all these are also interested in this area. As you see, why particular, it's not just constrained to this telco, because as you see, what is important, 5G is the first step. You see in the next generation, it's all connected to all the vertical services. So you see communication, computing, all integrated. You see sensing integrated. You see all the new services. EU, likewise, I think this is a new project. It's called HexaX. What is exciting, you see, is that the definition of this 6G, they define as a digital world, physical world, human world. So you see that is something that why XR, AR, VR, immersive experience, the cognition experience will all come together. And actually, when you come together, this is essentially, it pushes the limits that is beyond communication. So you really need to understand the context. What are you transmitting? The sense will come in. So it's an exciting, really new area. A lot of open problems for people to look at. Trends in 6G vision. If you're interested, there's many materials out there around the region, around the world. So it's an exciting period for people who will work on this area. Okay, yep, some KPI in this 6G flagship. I just for your interest, this is not confirmed at the ITU. It's just a table that I got from this 6G flagship white paper. So what is clear, as I mentioned just now, that so this is one trend we see, that in the 5G you have this KPI, different KPI, peak data rate, spectral efficiency, for example, connectivity, energy efficiency, and so on. So so this is one, of course, this is one approach that we see in different groups are looking at, is to push this limit. But if you carefully look at this limit, let's say 1 terabyte, some of this service, let's say in a manufacturing, I may not want to have such a peak data rate. My reliability, yes. Latency, yes. So I think, so that is a question that I think the community need to think about. How do we have a flexibility or programmable sort of system able to adapt and not be fixated by trying to push all this limit? If not, we will create a very expensive type of a network. This exciting, some key technologies, I think I just want to particularly bring about. One of them is called Internet of Senses. So interesting, I think Dr. Wen talk about this integrated sense and communication. It's exciting because if you think of it, how do you actually communicate your sense? Yeah, because humans have all these senses. How do you actually, if all these senses of your sense and your friends or your social network can be able to communicate, what is the architecture? And what is that network, whether it's from network architecture, what is that technology that able to create that? Because once you able to actually create that, you actually solve a lot of these problems we have in this pandemic, where you need to lock down, all these isolation problems, all these stress problems, where you're not able to connect with other people. That, because at the end, humans need this social communication. You need this community. And hopefully 6G can build these key technologies to prepare us, so that if happen that another pandemic comes in the future, actually we are well prepared with all this technology. Many topics, I will not go through all of them. I will just, due to time constraint, I will just elaborate a few of them, okay? So short range connectivity, as I briefly mentioned, so it's very clear in the standard now, we can support up to like 52 gigahertz, and we see even in the trend of future release, we will move up to a higher band, terahertz band. So this is something if to look carefully at, because this is closely linked with hardware. As you go up higher band, the challenges on the materials, the challenges on your AD will be tougher and tougher. The right materials, the cost, the deployment, which actually band to look at. We really have to think carefully on that. And related to that, I mean, propagation loss, as I mentioned, is a very key factor. So your proper, careful channel measurement, all this, and the use, I think antenna technology is going to be very important. Your integrated antenna, your programmable antenna technologies will be very, very key in this particular area. So hardware will be going to be very, very important. The analog communications, because you may not want to do everything on digital, hybrid type of hybrid technology, hybrid beamforming will be important. So back to this analog type of communication will be actually very important to look at. And deployment, we have to always think carefully as we try to deploy, whether it's for reflective intelligent surfaces or this high short range connectivity technology. Deployment is very important, because at the end we have to look carefully at the constraint of this technology, because all this technology will have a smaller coverage. So where to put them, where the needs are, where to put them, and you cannot massively deploy, because that will have an implication on your backhaul. Backhaul, if you're going to have whether it's wired or wireless, it take up resources. Scalability, you want to integrate, you want to ensure your access and the backhaul is an integrated type of design. Your capacity could be a limit, because imagine you have such a high data rate at your access. The bottleneck cannot be at the backhaul. So the backhaul also has to keep up with that requirements on your data rate. So all these are important issues. Intelligence will be important into this configuration, the handover, because of the fact that it's a very, very small coverages, the seamless handover. And the questions that for different agencies or even the operator to carefully look at, as we move up to this higher band, if all the operators wants to have such a huge amount of bandwidth, do we have that sufficient bandwidth for all of them? So what is the policy or what is the mechanism to do spectrum sharing? Because at the end of the day, you think of it, not some of these cell may not have much traffic, so you're actually wasting that spectrum. Something to look out, and how do intelligence play a role in managing this sharing will be very important. I've done some preliminary work which look at some small cell backhaul, but I will not elaborate, but we need to look at that. Wireless backhaul, I'll just go directly to some of these topics due to time constraint. So access backhaul integration, as I mentioned, talk about deployment operation is important. The type of backhaul technology not necessarily fixed. What type of, we could have wireless, what type of backhaul we can actually use millimeter wave also. So which means that there's also possibility of autonomous backhaul selection and configuration. how to actually do that depending on your weather, depending on the different weather conditions, on different depending also on your requirement and your demand. So aligned to what I've mentioned before, massive deployment, density, scalability is in the design, infrastructure, spectrum sharing can reduce costs. So how do we actually look at that? Is O-RAN and a good solution for that, something to actually ponder, although we don't have actually radio unit with that capability yet. As I mentioned, integrating intelligence to that dynamic access backhaul will be very key, because we know that traffic will be the key to look at the utilization of this. Definitely, depending on some of these applications, we definitely see that downlink uplink traffic will be highly asymmetric. If you're highly asymmetric, how do you actually deploy way advanced? So some of this dynamic intelligence will be very important to help us to actually design something more sustainable. What I will not just mention this, I will just continue so that I can complete on time. So massive IoT, massive URLCC. So in the current standard, we do have massive IoT. URLCC is not actually massive yet. So, but if you think of autonomous vehicle as a good applications of using URLCC, ultra reliable, low latency. So imagine down the road, let's say 2030, where we have a lot of autonomous vehicle. It's a massive URLCC. So in our current development of URLCs, can we actually support that? Maybe not. We need to be better than that. What are the new technologies and understanding to do that? How to enhance latency, positioning, connectivity? How do we efficiently use the higher band to do that? Some of these massive IoT applications, power is important. The use of energy harvesting, the backscatter sensors, the sensor, and we see the trend of integrating sensors and communication. So we have a huge amount of sensors, so energy will be very important. At the end of the day, when we talk about IoT, all these applications, if you look at the protocol itself, it's actually a lot is based on random access. So, but fundamentally, if you have random access under massive connections, and a lot of these applications have delay constraint, and it's a challenging problem because a lot of current protocol will not be able to accommodate this, and you will cause a lot of problems in terms of performance. So essentially, if you think of it, site information will be very key. So site information of your position, information of your traffic, information of semantic, information of that will help all this even protocol to actually efficiently utilize their resource. So definitely we want to imagine that in the future, your user, your UE, your handphone, and your base station, where the access point will be more intelligent and more powerful. There's possibility to exploit this capability to help us to solve all these access problems. And end of the day, you think of that, there's a lot of fundamental theories that we do not understand. So there's a lot of room for the community to really think carefully, right? All this trade-off, energy, delay, capacity, reliability, the fundamental system level trade-off is not well understand. So we have to look at that large system type, because a lot of problems we face will be based on large system. There is traffic is dynamic. There's different form of intelligence. The interference is also dynamic. How to actually have a framework to understand that is something for the academia to carefully to look at that. I will skip that and I will go to continue to look at interesting area. Software-defined radio will meet software-defined network. We see the trend of this slicing programmable at the core network. We will see that because of the applications we talk about, the future, you want to have flexibility, you will see that the radio or the access point will be more programmable. We will see software-defined radio incoming, O-RAN, you see some of this trend coming in. So likely you will see that this will meet together, the software-defined will, because then it will end up become a very highly flexible agile network. So to actually move to that stage, a few challenges we need to tackle. So one challenges to look at is this virtualization. So the integration of this network and RAM virtualization. It's a challenge problem because the advantage of just doing network slicing and not do so much RAN slicing or RAN virtualization is that because the amount of parameters that you can tweak and the amount of information you have. So once you do this integration, you have a very challenging multi-time scale, multi-large scale optimization problem. You have a big area you need to control. How would AI and how would intelligent controller come into play? An intelligent controller that is smart enough to translate the key parameters or the key information back to the network slicing part. So I think that is something to look out for. Incorporating machine learning to all these optimization or resource allocation problem, we have huge amount of data, but we cannot afford to do the conventional approach of trying to crank all the data. How do intelligent technique to actually help us to reduce the search space? How do we efficiently incorporate this model-based and knowledge model or knowledge-based and data-driven method together to ensure our system is actually sustainable, it's still robust, and we still can understand the results that all these machine learning crank out. And service multiplexing, because at the end of this day, this technology is to provide services. So some of these services you may want to multiplex with that. Okay, I heard the first bell, so I'm going to skip network intelligence. I won't skip that. I just want to maybe emphasize just one point. So federated learning, I think we have mentioned this a few times. So as we want to bring machine learning as example into the communications, we actually also need to think about the constraint. So as example, if you want to bring this federated learning down to the access point or the user side, the effect that we are going to transmit this over a wireless communications link, the effect of interference, the effect of power constraint, all these constraints needs to come in. So this need to incorporate into my machine learning design. I think that's important so that my scheduling mechanism are well designed, tailored for that. Something for community to look at. Internet of Sensing, I think Dr. Wen Tong talked about that. So this is a very exciting area to look at a lot of fundamental problems that are missing. So sensing control integration, you imagine there's a lot of noisy and massive feedback. And if you bring security in, there's a lot of issues. How do you actually automate through AI, but then you don't overtrain, and that's something to ponder. Semantic communication, I think, is an exciting area that now we look at. This is actually one way to actually redesign our communication so that in the future, because we understand the context, the semantic that we are, and if there's a certain service that the transmitter and receiver only communicate based on a certain context because they understand the context well. So then the way you design this communication could be very different. It could be based on a common codebook. If it based on a common database, and that will help us to reduce the way the reduced amount of redundancy that we injected in our conventional communication. This is my last slide. So it's an integrated space terrestrial. It's a very exciting area to look at because it's beyond just ground and satellite. So there's also an airborne network. So it's a multi-layer heterogeneous network. So there's airship, there's aircraft, there's UAV. You could have, so imagine the notion of this side link could be in here. This will be a truly global coverage, anytime, anywhere, connectivity. But the challenge is highly complex because you have to integrate across different type of network, different channel conditions, different constraints, different power constraints, and it's across the globe. So it's a very exciting open area to actually look at. And I'm on time, so this is my last slide. So from particularly, I want to mention that really, we look at whether 6G or 5G evolution, connectivity and communication will be a backbone, especially as for Singapore context, as we want to push for smart nation, digital economy. So, and the journey to 6G starts now. And thank you for listening. Thank you very much.
Thank you so much, Professor Quek, for taking us on that engaging journey towards 6G And we will now move on to the question and answer segment. For those of you who are watching right now, don't forget to enter your questions into the Q&A tab or box, all right, in the platform. Now we have this question from Shmuel Yerushaimi, and the question is, what exactly are the advantages of 6G in relation to 5G, and how will 6G technologies improve the functions of different systems? What are your views?
So I think it's a good question because first of all, we do not know what is exactly 6G. So that's why I think what's important is this evolution that will help us to actually really understand what we will see. So this is sort of the first attempt when compared to 4G that a generation, let's say 5G, we talk a lot of use case, vertical services. So once we actually, this evolution, understand the different use case, we will understand the different limits of that. Once we understand the different limits of new services, new requirements come in. And that will set up what 6G is. At this stage, we see a few, let's say, service that cannot be done. Let's say Internet of Sense. How do you actually exchange sensors? Right? You want to, if you are quarantined, you want to talk to, how do you actually translate this emotion? I don't think 5G can do this. So a lot of exciting things that are still open for us to do.
Thank you so much, and I hope that answered your question. We have another question from our audience, and this question is there a role for TV white space in the 5G evolution? That's part one of the question. And there's a second part that says, do you see a role of Singapore scientists in pushing the LEO or LEO 6G frontier forward?
Okay. I think the first question, I briefly talked about this unlicensed spectrum, right? So as we look at the different services, so as we explore the different use case from now to in 2025, we will actually will likely face a scenario where certain services will require the long distance coverages of TV white space, because a few of these bands that they have are very good for coverages. So the use of unlicensed spectrum, I think, is important to actually look at. Of course, the question is how do you have a system to actually efficiently able to spectrum access that, and to ensure that because of extensive coverage has advantage and disadvantage, because it could cause issues to our neighbors because so close to a lot of neighbors. So something that is at the policy level. So that's one thing to actually look at from both technology and the political policy level. So the second question that I have is on the role for Singapore is let me see.
Can we have that question back again so we can see it one more time?
I can see.
Yes, the question is, do you see a role of Singapore scientists in pushing the LEO 6G frontier forward?
Yes. I definitely see that Singapore has a huge potential. Mainly because I think we are at least in the equator. So I think we have potential to set Singapore as a future satellite hub. So because once you are a future satellite, we can actually serve a lot of services around the Southeast Asia region. And a lot of times when we talk about this satellite or this stage, there's all this standardization body, and I think Singapore has always been a very neutral player. We want to serve a lot of all our neighbors, essentially also to help our economy. So from a political and motivation, I think we have that potential to do that. And we do have a lot of local companies starting to look at that. We do have our even government agency. I think EDP has an Austin program that look at that. So I think we have many parts that can come together so that we can contribute in this direction. So I'm positive that we can actually contribute in this particular area in the long run.
That truly sounds very, very exciting. This next question, Prof, comes from Melvin Kwan. And the question is, how will cybersecurity be embedded in the 6G design and architecture? And how would the trade-off with performance be handled? What do you think of this?
It is a very difficult problem. First of all, we do not know the architecture of 6G, right? But what is very clear with the current trend that we look at what 5G talk about, with all the issues of security and not trustworthiness, one key factor that we can foresee as we move forward to 6G is that the requirement of openness and trustworthiness in the system will be important. So that's one. And another area why there's also a trend to push this open platform, because it's based on open architecture. A lot of this is not a closed box. There is also one way to look at how it can, there's another direction. Of course, it really have to depend on how the business, how the industry will look at that. So that is an approach that the security, of course, can come into this open system because it's a very open platform. But 6G, I think, is still an open problem for us to look at that. Yeah.
Very good. So some more questions. I got to tell you that this whole discussion is really exciting, and we've got lots of questions from our audiences. The next question is from William Lau, and it says, is Li-Fi, L-I-F-I, Li-Fi already a form of 6G? Is it?
A form of 6G. I think Li-Fi technologies is already exists. I mean, we do have Li-Fi technologies. I think at the end, why I always mention services, right? Because at the end of the day, whether I'm 5G or 6G or whether I'm 4G, it actually is the services as a service provider, or even my or even the industry, I really at the end don't care. It cares about my cost, my deployment, and my efficiency of my delivery of services, whether it's 4G, 5G. Li-Fi has its advantages, right? It has a downlink. You know, lights are everywhere. Indoor is one. Outdoor is an issue. Then once you have multi-light, the interference issue. So a lot of technologies has these different advantages and disadvantages. I think at the end of the day, what we definitely see is that the use case and system integrator will be the key. Once we understand the different use cases, then there's a whole bag of technology. At the end, what I see is that at the end, I care about what is the key KPI, not just one, a bag of them. Eventually, to meet that, what is the best integration of the different technology that come together to serve this at a low cost? I think that's what we see. So Li-Fi is definitely one of the technology, but I do not say that it's going to be 6G because a lot has been done now in Li-Fi.
Fantastic. Yep. We've got about under 8 minutes to go, and we'll see if we can squeeze in just 2 or 3 more of the questions from our audience. This next one is by Diana R. And the question is, what is the future of CRN SDR? What do you see, Prof?
So what is, let me see, what is
CRN?
Oh, there's a lot.
The future of CRN SDR.
Oh, okay. So it's about connective radio and software-defined radio. All right. So I think so connective radio actually is a term that has been out there for many years, right? Some people interpret this as AI for communication. You can interpret that. As I mentioned, AI is going to be a big part of our evolution down to 6G because of the context of the massive of data. The network is going to be very complex, so the intelligence will be there. So you'll see definitely a part of that. Software-defined radio will be there because you want to have some programmable capability at your node, adapting to different services. So I briefly mentioned about a possibility of software-defined radio together with my software-defined networking. Hopefully come together, but complexity is an issue lah. Once you become so open and so programmable, many things you need to optimize. So it's actually a lot of trade-off. Yeah.
Thank you so much for that answer to that question. Here is another one from Shruti Dave. And the question is, for 6G, will transmit antenna selection with massive MIMO work to achieve higher energy efficiency? What do you think?
I think this is probably a 4G type of or 5G type of question. Basically, in a 6G context, I think they will be looking more than this lah. I think if you think about massive antenna, whether you want to do transmit antenna selection or so on, I think yeah. So there's many schemes that propose to do that. But a lot of massive MIMO challenges that we see currently now is actually when you deploy this type of technology, the cost is very expensive, right? So in terms of the ADC requirement and also to do the alignment and so on, I think these are the challenges. But this is just one scheme lah. Because to think about energy efficiency, also need to carefully think about the hardware. Yeah.
That's very true. Yeah. And we have some more questions coming in. This time, Prof, this is from Sadiq. And Sadiq says, this might be a concern for some people out there. And he asks, does 6G impose any health problems on society?
Okay. First of all, we do not know which spectrum that 6G will be actually allocated. So I think there's no connection to health problems. We do not know actually. I think there's a lot of even arguments on 5G deployment in Europe, where they don't want the base station to be very close. But what we can see is that as we move from one generation to another generation, the power consumption or the transmission power is actually it's actually going down lah. It's actually we see that the energy efficiency is actually improving at a factor of 10 or more than depending on the deployment. And if we go to, for example, if we go to a higher band with a smaller coverages and with very sharp beam using antenna technology, direction antenna technology, I don't see that will be a big issue lah. But this is something too early to discuss at this stage. Yeah.
Thank you for expounding a little bit on that, Prof. One last question, that's all we have time for. And this last question is from Muhammad Ilyas Katak. And the question is, regarding wide-scale commercial deployment of collaborative autonomous vehicles or CAV, how much collaborative autonomous vehicles is commercially deployed till date worldwide?
I have to say I have no answer for that. Yeah, so I do not have the figures on that, and yeah. So but what I can see currently is that there is some trend of doing a lot of trials. What I understand, there is trials in a lot of especially in Asia, because a lot of regulation is easier. It's not just one vehicle. We see a lot of activities, particularly in China, a few highways, Hangzhou, trying to do large-scale highway or different region of this large-scale autonomous vehicle deployment. So I think at least for the next few years evolution until 2025, we will be able to see really large-scale sort of deployment. Not a single like the pathway for the bus type lah. So it's actually on the highway, particularly in Asia. That will actually use some of this 5G or the V2X type of technology. So it's exciting to actually look at that, to look at what the challenges that they have, and so that it will guide us as we move forward to the future generation.
Thank you so much, Professor Quek, for your presentation and, of course, answering all those questions of our fellow explorers who are keen on embarking on that journey towards 6G. And I feel all ready to take on 2030 right now, with this morning's talks giving us a roadmap into the future. But before we do that, let's go for a little lunch. That's right, plenty of food for thought to digest after the morning's presentations on 6G. And we're going to get you, or let you, get recharged for the afternoon's sessions, which will start with talks on blockchain-empowered networks and chip-to-chip communications. We'll see you back here in about an hour's time at 12:45 p.m. sharp. See you at 12:45.
Design is many things to different people. Most would associate it with art, fashion, and graphics. But that is only one facet of this multi-dimensional concept. Design, more importantly, is also the creation of human-centered solutions. They can be solutions to everyday challenges that make life easier, like adding wheels to your luggage to create the modern four-wheel suitcase. Or they could be solutions to global challenges that affect the lives of millions, like the creation of a shared network where information can be exchanged at any time by anyone at any location, what we now call the Internet. Design is the sum of ideas and expertise from different fields to create an effective, efficient, and sustainable solution. Nurturing design innovators is crucial to the continued advancement of humankind in a world bombarded by unprecedented challenges. They will transform our lives, drive innovation, grow economies sustainably. And at Singapore University of Technology and Design, also known as SUTD, our mission is to nurture the future generation of design innovators. Inspired by the evolution of design thinking, SUTD is revolutionizing design and leading the charge towards a new era of innovation. Students, of which 40% are female, are trained in design innovation and are immersed in a collaborative learning environment where they can easily go from concept to prototype, programming and testing. An interdisciplinary curriculum brings together 5-degree programs for more holistic and creative innovations, be it in education or research. We are united and inspired by a single-minded goal of improving lives and safeguarding our planet. We call this a better world by design. From autonomous systems that can learn and adapt to new innovations in sustainable materials, design with the power of AI can help build smarter, more enjoyable cities, unlocking breakthroughs beyond our wildest imagination. It will also help power our economy to stay competitive into the future. Design powered by technology and AI truly is here to help us build a better world.
We produce 300 million tons of plastic every year, and 90% is actually missed, it's not recovered. It ends in oceans or ends in landfills. Plastic per se is not bad. I mean, plastic was invented in the 1930s, and since then, actually, most of our development, in the last century cannot be understood without the benefits that plastic brought into society. The problem is actually also how society has become added to this material and the amount that we are producing and this lack of integration into the natural systems. We are not trying to remove plastic. We are not trying to go back 100 years on technology. What we are trying is completely the opposite. What we are trying to do is to bring materials that are they outperform plastic in many senses. They open like new possibilities and they enable to make engineering in a society that moves around biology, and by definition that society will be sustainable. So take for example the case of FLAM, right? The material that we made in collaboration with Stilianos. So this material is not only strong, but again, since we never modify the composition, like respect the natural molecules, it's actually perfectly integrated in the ecology of Earth. So phloem is made out of cellulose and chitin. They are like the most abundant and second most abundant organic polymers on Earth. Cellulose is well known for everybody, is everywhere in green plants, right? Chitin is less known because of the lack of industrial uses. Chitin, for example, is the cells of the insects. The protective exoskeleton of the insect is made mostly of chitins. Same thing for molluscus and the sea cells. Actually, they are also made of chitin. So it's a molecule that nature is using in very different areas to make strong protective materials. In the Fermat lab, the lab that I lead in SUTD, we focus on the integration of biology in other engineering fields. We are setting the ground to what we call the biomaterial age, where biology will link and integrate with other engineering fields to bring them to the next level. In the case of plastic, what we are determining is to actually break this cycle of production and consumption of plastic in a non-sustainable way. And what we're trying to do is to set a new paradigm that is based on biological materials, where your materials are produced, manufactured into products, and degrade in closed regional areas. And actually they have like this kind of circular economy society embedded into the material itself.
So people need three things to survive on Earth: food, energy, and water. In our research group, we are targeting two of these fundamental challenges: water and energy. And we want to use low-dimensional nanomaterial to solve these two challenging issues together. Usually, in the research community, some research group they are targeting on solving energy issues, and some group they are working on water treatment. However, in SUTD, we are focusing on one very unique area. We are trying to find one solution for these two challenging issues together. So in one of our projects, it's called the desalination battery. Basically, we desalinate seawater, ocean water, remove the sodium and chloride ions from the seawater. At the same time, we utilize the sodium and chloride ions to store energy. So we desalinate the water and store energy, making that two steps together. With these new solutions, actually we can supply fresh seawater, desalinated water to everybody in Singapore. At the same time, we can have low price energy storage being available to everybody. My big vision for this project is we can turn the entire ocean into a big desalination battery, a huge desalination battery. So everybody can enjoy the desalinated water and free power from this huge desalination battery. We are also looking at to recycle valuable resource from the seawater. For example, as we all know, lithium metals is one of the natural metal we can find in seawater. We're also looking at ocean mining to recycle those very valuable metal ions from seawater and then utilize them as battery electrode to store battery or for other purpose. I think by that way, we can maximize the natural resource we can achieve from the ocean.
Advances in material science often lead to huge increases in productivity and advancements in society. If you think about it, it's like the Stone Age, Bronze Age, Iron Age, they're all named after materials. And more recently, silicon and glass optical fiber led to the computer and the internet. And so you can see that these technologies have had a profound impact on the way that humans live and behave, and also fueled the economy to a certain extent. And therefore, it's very important that we continue to design, discover and develop new materials. So we're studying chalcodrenide materials. These are materials that substantially consist of sulfur, selenium and tellurium, and they have fascinating properties. One of the properties I like and study the most is their phase change property, so they can exist in multiple states at room temperature. This is very different to most materials. Here we have an opportunity to switch them and use those to make devices that have switchable properties. So you might have experienced chalcogenides, especially if you're my age, when we were recording most of our data onto DVDs and CDs. They were actually the active layer in the rewritable CDs in the 90s and noughties. These materials have a number of applications aside from the technological applications that we're looking at in Actalab. For instance, chalcogenides are often used in solar cells, and they're used in thermoelectrics, also semiconductor devices as well. So in our group, we're moving away from some of the more traditional chalcogenide materials that other groups are looking at for data storage, and rethinking some materials that were once discarded for data storage applications and applying them to photonics. One of the big advantages of our group is that we can go through the whole process from conceiving an idea for a material, simulating it, testing it in the lab, or trying to create it and test it in the lab, and then fabricating a device. So we don't only do device design and we don't only do materials design, we do the two things in conjunction, and this gives us an extra degree of freedom because we're no longer limited by off-the-shelf materials or pre-existing designs. We can design the materials and design the devices synchronously for a specific application. We've recently found a material that has a very high transmissivity in the visible spectrum, and this is really useful for display technologies. We're currently working with A*STAR, other universities in Singapore, to create holographic displays and beam steering devices based on these materials. And hopefully one day we'll all have a chalcogenide holographic display in our living rooms.
Some people may feel that the flipped classroom may not be such a good idea because you are unable to consult the prof in real time whenever you're in doubt.
It's mostly us learning by ourselves without much guidance from our professors.
Some students might think that there's no class, I can just watch the video at home.
Since it's learning on our end and we still have school, we kind of take it as something extra, like extra work for us to do.
Flipped classroom means that you're actually bringing some of this learning back to the students. We transform an hour of actual physical lecture into a flipped classroom. And this is usually done in a way that it is a pre-activity. So the students are expected to learn certain concepts through the lesson material online, outside of classroom, before they come to the classroom. And when they come to the classroom, these concepts will be further explored and applied in the classroom. Having spent more than a decade doing actual physical lab research, right? So this was my research in bone tissue engineering. When I switched fields, now that I'm a lecturer and I went to class, somehow the passion for research was still in me, which is why I decided to embark on a full-on research, pedagogical investigation about the effectiveness of the flipped classroom. From the research that we did at SUTD in 2015, this was just a flipped classroom model but without peer instruction. So I didn't have the assessment component, neither did we have the peer-to-peer discussion. And we found that it didn't work so well. And so in the following year, and this is after the talk by Eric Mazur, we decided that we will try putting in some things that he has said. And so this quiz, peer-to-peer discussion and a quiz again, reduced the anxiety that the students felt. They actually looked forward to learning, and we find that from our experimental results, actually 80% of them received a full score for the second quiz, which means that the peer-to-peer discussion really made a significant difference and that they learned very well from each other. Many institutes have tried flipped classroom, but sadly all they do is they throw in some videos and then maybe a quiz. And so for our students at SUTD, for the flipped classroom, they actually have, I would like to call it a package, a flipped classroom package, where they get the video recordings, the PowerPoint slides, as well as a keyword list. When we actually prepare flipped classroom lesson material, we take many things into consideration. So for example, we ensure that we break each lecture into maybe 4 to 5 mini lectures, which are about 10 to 15 minutes long. The other thing that we've included is this thing called concept quiz. So every time a concept is taught, so at the end of every mini lecture, there are a few questions that directly assess the learning objective. Because we've been testing them on a weekly basis, that by the time it comes to the exam, right, they are maybe desensitized, or you can say completely prepared. So we did see an increase in exam scores that was significant over the years after the implementation of flipped classroom with peer instruction. We also saw that the students were punctual for class because we made sure that the quizzes were, it starts at the beginning of class. They were actually present, right? So that helps with absenteeism as well. So the rationale for designing a flipped classroom is really the fact that we wanted to push some of the learning back to the students. We want them to have this self-directed learning skill. Every time we run this course, we actually collect feedback to make this learning experience better for the students. One of the things that we are also exploring is to see if we can use certain gamified lab simulations. So we are interested to see how we can use this or even games as a pre-activity, which I'm sure the students will find fun and engaging.
For flipped classroom, the e-learning, you are able to digest the information at your own pace.
It encourages self-learning.
I feel that flipped classroom is actually a good idea because it allowed us to go back and check all those concepts that we couldn't catch in class.
We are constantly talking about the rising levels of the ocean, and us being within an island, we need to think about which futures we will be inhabiting and how to design for those futures. A future where the water has risen so much that the new structures need to float within the water in order for the kind of community to be able to migrate towards this island. Our research lab is called Form Axioms. It is based in SUTD. We have used the topic of interest in Form Axioms to also develop the work with the students in the various option studios, always regarding an exploration of the oceans and the conditions that the oceans will provide us in, say, 100 years through all the climate crisis that we are very much discussing right now. The Shenzhen Hong Kong Biennale is of particular importance for SUTD because this particular Biennale is called The Eyes of the City and is about the inclusion of new technologies into the way in which we live. And within those, there is one particular district that has a topic that is about water. So I think it's a very appropriate place for our school to be embedded into it, in this kind of a conversation. The big task of the design was how to include in it models of different scales, of different option studios, AR, VR, and also videos and projections. And so we created a big plinth, which is about 180 square meters. Is almost like a floating, very sculptural piece that cantilevers, and it has recesses for all the models. The piece is completely painted in black because the space is also be darked out. So the idea is that all the models will feel almost like floating within the space. It really pushes us to think about architecture and architectural design, urban design, not as being now and here, but it kind of requests from us that we think about a future.
I like hawker center because I like to hang out with my friends and my family. We like hawker centers because it's affordable and there's a wide variety of food available there.
I like the hawker center because of the local kopi.
I like hawker centers because of the food that gets passed down generation to generation through their recipes.
In Singapore, food is very important, and hawker centers is the place where people celebrate food in community. So we think this is a subject of study for us, and we think that hawker centers could be further explored and incorporate new things to make them more exciting and more relevant in the future. Hawker centers now are under the pressure of the food courts and the malls. So the question would be, how can we make them relevant again? How can we incorporate new things? How can we change and tweak the existing spaces so that they are relevant and attractive for people and to face the new challenges that Singapore is undergoing? So part of the research I'm doing in SUTV is related to sustainable space making by using digital tools. So digital tools for architecture is the way that we can integrate data with design intentions. So we can merge very objective information with our intuition to really create sustainable spaces. So we can actually design geometries that are self-shaded and create cross-ventilation that are utilizing more our resources, natural resources and energy, and to address more complex challenges. The challenges in the future, I think, would make the hawker centers be more integrated and articulated with society. So it's not a room where people go, it's more a space that is more connected, more open, and also more sustainable. So I see the hawker centers like something closer to a park than a room within a building.
Many people are concerned about recycling in Singapore today. I think one of the main reasons is people see that the landfill on Semakau will be full very soon in 2035, and they're worried about that. However, what people are often less aware about is the role the informal sector plays in recycling. And some statistics show that informal recyclers, which includes Karanguni and charities, collect as much as 90% of the waste recycled by households. At the same time, we've found in our own social research that the informal sector is facing different kinds of challenges today. One area is because of changes in the built environment, it's difficult for Karanguni to connect with households. Also because of people's changing work schedules when they're at home. So we took that insight from our research and tried to put that into a design project to look at how we could utilize technology to redesign the informal sector rather than the way that technology is often used, which is to disrupt or displace traditional systems like this. From that design research project, we developed an app for smartphones, which we called Henk. We then piloted the app in 3 neighborhoods in Singapore with over 200 users and 3 Karanguni. From that, we found a new series of challenges that were unexpected for us. In particular, we found that Karanguni rely on various ways of aggregating materials, and our app did not provide that. So what we're looking at now is how to combine aggregation with the app, either through something like a smart bin system or through social institutions like maybe a neighborhood committee.
Transportation is responsible for 1/4 of the world's global CO2 emissions. This is a greenhouse gas that contributes to global warming. About 3/4 of that is due to road transport. This means the cars and trucks that we use to get our goods and to move around. The world vehicle population is about 1.3 billion vehicles today, and it's expected to grow to 2 billion vehicles by year 2050. Freight transport demand is expected to grow 3 times around the same time frame. So the challenge is really how to address this growth in demand. How can we make sure that we fulfill these travel needs sustainably? So my research at SUTD looks at sustainable urban mobility. We are interested in different ways to reduce the environmental impact of transport in our city. One of the most recent projects we did was to look at freight transport or the movement of goods in the city. And we're thinking of different ways to optimize the movement. So one thing we found out through the research study was that trucks actually idle quite a fair bit and also are not fully loaded most of the time. And these are signs of inefficiencies that we're trying to correct. There are several things that we can do as an individual to reduce the environmental impact of transport. First is to avoid car travel wherever possible. So this means adopting virtual meetings instead of physical meetings, or walking, cycling, and taking public transport like the bus or MRT. If we were to take taxi or private hire rides, we can consider sharing the rides. The average car occupancy is only about 1.7 passengers, which is fairly low. A car can actually take on more passengers, so share the ride when you can. Another thing we can do if we were to opt for car travel is to consider using smaller or lighter vehicles that's more efficient than bigger and heavier ones, or even consider the use of hybrid vehicles, which are more efficient. In terms of online shopping, consumers can also make a difference by choosing maybe not so urgent deliveries or having their delivery sent to delivery lockers. So this reduces the risk of missed deliveries and extra trips that have to happen. So small choices like that can actually make a difference as well.
Design is many things to different people. Most would associate it with art, fashion, and graphics. But that is only one facet of this multi-dimensional concept. Design, more importantly, is also the creation of human-centered solutions. They can be solutions to everyday challenges that make life easier, like adding wheels to your luggage to create the modern 4-wheel suitcase. Or they could be solutions to global challenges that affect the lives of millions, like the creation of a shared network where information can be exchanged at any time by anyone at any location, what we now call the Internet. Design is the sum of ideas and expertise from different fields to create an effective, efficient, and sustainable solution. Nurturing design innovators is crucial to the continued advancement of humankind in a world bombarded by unprecedented challenges. They will transform our lives, drive innovation, grow economies sustainably. And at Singapore University of Technology and Design, also known as SUTD, our mission is to nurture the future generation of design innovators. Inspired by the evolution of design thinking, SUTD is revolutionizing design and leading the charge towards a new era of innovation. Students, of which 40% are female, are trained in design innovation and are immersed in a collaborative learning environment where they can easily go from concept to prototype, programming and testing. An interdisciplinary curriculum brings together 5-degree programs for more holistic and creative innovations, be it in education or research. We are united and inspired by a single-minded goal of improving lives and safeguarding our planet. We call this a better world by design. From autonomous systems that can learn and adapt, to new innovations in sustainable materials, design with the power of AI can help build smarter, more enjoyable cities, unlocking breakthroughs beyond our wildest imagination. It will also help power our economy to stay competitive into the future. Design powered by technology and AI truly is here to help us build a better world.
We produce 300 million tons of plastic every year, and 90% is actually missed, it's not recovered. It ends in oceans or ends in landfills. Plastic per se is not bad. I mean, plastic was invented in the 1930s, and since then, actually, most of our development in the last century cannot be understood without the benefits that plastic brought into society. The problem is actually also how society has become added to this material and the amount that we are producing and this lack of integration into the natural systems. We are not trying to remove plastic. We are not trying to go back 100 years on technology. What we are trying is completely the opposite. What we are trying to do is to bring materials that they outperform plastic in many senses. They open like new possibilities, and they enable to make engineering in a society that moves around biology, and by definition that society will be sustainable. So take, for example, the case of FLAM, right? The material that we made in collaboration with Stilianos. So this material is not only strong, but again, since we never modify the composition, like respect the natural molecules, it's actually perfectly integrated in the ecology of Earth. So FLAM is made out of cellulose and chitin. They are like the most abundant and second most abundant organic polymers on Earth. Cellulose is well known for everybody, is everywhere in green plants, right? Chitin is less known because of the lack of industrial uses. Chitin, for example, is the cells of the insects. The protective exoskeleton of the insect is made mostly of chitins. Same thing for molluscus and the sea cells. Actually, they are also made of chitin. So it's a molecule that nature is using in very different areas to make strong protective materials. In the Fermat lab, the lab that I lead in SUTD, we focus on the integration of biology in other engineering fields. We are setting the ground to what we call the biomaterial age, where biology will link and integrate with other engineering fields to bring them to the next level. In the case of plastic, what we are determining is to actually break this cycle of production and consumption of plastic in a non-sustainable way. And what we are trying to do is to set a new paradigm that is based on biological materials, where your materials are produced, manufactured into products, and degrade in closed regional areas. And actually they have like this kind of circular economy society embedded into the material itself.
So people need three things to survive on Earth: food, energy, and water. In our research group, we are targeting two of these fundamental challenges: water and energy. And we want to use low-dimensional nanomaterial to solve these two challenging issues together. Usually, in the research community, some research group they are targeting on solving energy issues, and some group they are working on water treatment. However, in SUTD, we are focusing on one very unique area. We are trying to find one solution for these two challenging issues together. So in one of our projects, it's called the desalination battery. Basically, we desalinate seawater, ocean water, remove the sodium and chloride ions from the seawater. At the same time, we utilize the sodium and chloride ions to store energy. So we desalinate the water and store energy, making that two steps together. With these new solutions, actually we can supply fresh seawater, desalinated water to everybody in Singapore. At the same time, we can have low price energy storage being available to everybody. My big vision for this project is we can turn the entire ocean into a big desalination battery, a huge desalination battery. So everybody can enjoy the desalinated water and free power from this huge desalination battery. We are also looking at to recycle valuable resource from the seawater. For example, as we all know, lithium metals is one of the natural metal we can find in seawater. We're also looking at ocean mining to recycle those very valuable metal ions from seawater and then utilize them as battery electrode to store battery or for other purpose. I think by that way, we can maximize the natural resource we can achieve from the ocean.
Advances in material science often lead to huge increases in productivity and advancements in society. If you think about it, it's like the Stone Age, Bronze Age, Iron Age, they're all named after materials. And more recently, silicon and glass optical fiber led to the computer and the internet. So you can see that these technologies have had a profound impact on the way that humans live and behave, and also fueled the economy to a certain extent. And therefore, it's very important that we continue to design, discover and develop new materials. So we're studying chalcogenide materials. These are materials that substantially consist of sulfur, selenium and tellurium, and they have fascinating properties. One of the properties I like and study the most is their phase change property, so they can exist in multiple states at room temperature. This is very different to most materials. Here we have an opportunity to switch them and use those to make devices that have switchable properties. So you might have experienced chalcogenides, especially if you're my age, when we were recording most of our data onto DVDs and CDs. They were actually the active layer in the rewritable CDs in the 90s and noughties. These materials have a number of applications aside from the technological applications that we're looking at in Actalab. For instance, chalcogenides are often used in solar cells, and they're used in thermoelectrics, also semiconductor devices as well. So in our group, we're moving away from some of the more traditional chalcogenide materials that other groups are looking at for data storage, and rethinking some materials that were once discarded for data storage applications and applying them to photonics. One of the big advantages of our group is that we can go through the whole process from conceiving an idea for a material, simulating it, testing it in the lab, or trying to create it and test it in the lab, and then fabricating a device. So we don't only do device design and we don't only do materials design, we do the two things in conjunction, and this gives us an extra degree of freedom because we're no longer limited by off-the-shelf materials or pre-existing designs. We can design the materials and design devices synchronously for a specific application. We've recently found a material that has a very high transmissivity in the visible spectrum, and this is really useful for display technologies. We're currently working with A*STAR, other universities in Singapore, to create holographic displays and beam steering devices based on these materials. And hopefully one day we'll all have a chalcogenide holographic display in our living rooms.
Some people may feel that the flipped classroom may not be such a good idea because you are unable to consult the prof in real time whenever you're in doubt.
It's mostly us learning by ourselves without much guidance from our professors.
Some students might think that there's no class, I can just watch the video at home.
Since it's learning on our end and we still have school, we kind of take it as something extra, like extra work for us to do.
Flipped classroom means that you're actually bringing some of this learning back to the students. We transform an hour of actual physical lecture into a flipped classroom. And this is usually done in a way that it is a pre-activity. So the students are expected to learn certain concepts through the lesson material online, outside of classroom, before they come to the classroom. And when they come to the classroom, these concepts will be further explored and applied in the classroom. Having spent more than a decade doing actual physical lab research, right? So this was my research in bone tissue engineering. When I switched fields, now that I'm a lecturer and I went to class, somehow the passion for research was still in me, which is why I decided to embark on a full-on research, pedagogical investigation about the effectiveness of the flipped classroom. From the research that we did at SUTD in 2015, this was just a flipped classroom model but without peer instruction. So I didn't have the assessment component, neither did we have the peer-to-peer discussion. And we found that it didn't work so well. And so in the following year, and this is after the talk by Eric Mazur, we decided that we will try putting in some things that he has said. And so this quiz peer-to-peer discussion and a quiz again reduced the anxiety that the students felt. They actually looked forward to learning, and we find that from our experimental results, actually 80% of them received a full score for the second quiz, which means that the peer-to-peer discussion really made a significant difference and that they learn very well from each other. Many institutes have tried flipped classroom, but sadly all they do is they throw in some videos and then maybe a quiz. And so for our students at SUTD, for the flipped classroom, they actually have, I would like to call it a package, a flipped classroom package, where they get the video recordings, the PowerPoint slides, as well as a keyword list. When we actually prepare flipped classroom lesson material, we take many things into consideration. So for example, we ensure that we break each lecture into maybe 4 to 5 mini lectures, which are about 10 to 15 minutes long. The other thing that we've included is this thing called concept quiz. So every time a concept is taught, so at the end of every mini lecture, there are a few questions that directly assess the learning objective. Because we've been testing them on a weekly basis, that by the time it comes to the exam, right, they are maybe desensitized, or you can say completely prepared. We did see an increase in exam scores that was significant over the years after the implementation of flipped classroom with peer instruction. We also saw that the students were punctual for class because we made sure that the quizzes were, it starts at the beginning of class. They were actually present, right? So that helps with absenteeism as well. So the rationale for designing a flipped classroom is really the fact that we wanted to push some of the learning back to the students. We want them to have this self-directed learning skill. Every time we run this course, we actually collect feedback to make this learning experience better for the students. One of the things that we are also exploring is to see if we can use certain gamified lab simulations. So we are interested to see how we can use this or even games as a pre-activity, which I'm sure the students will find fun and engaging.
For flipped classroom, the e-learning, you are able to digest the information at your own pace.
It encourages self-learning.
I feel that flipped classroom is actually a good idea because it allowed us to go back and check all those concepts that we couldn't catch in class.
We are constantly talking about the rising levels of the ocean, and us being within an island, we need to think about which futures we will be inhabiting and how to design for those futures. A future where the water has risen so much that the new structures need to float within the water in order for the kind of community to be able to migrate towards this island. Our research lab is called Form Axioms. It is based in SUTD. We have used the topic of interest in Form Axioms to also develop the work with the students in the various option studios, always regarding an exploration of the oceans and the conditions that the oceans will provide us in, say, 100 years through all the climate crisis that we are very much discussing right now. The Shenzhen Hong Kong Biennale is of particular importance for SUTD because this particular Biennale is called The Eyes of the City and is about the inclusion of new technologies into the way in which we live. And within those, there is one particular district that has a topic that is about water. So I think it's a very appropriate place for our school to be embedded into it, in this kind of a conversation. The big task of the design was how to include in it models of different scales, of different option studios, AR, VR, and also videos and projections. And so we created a big plinth, which is about 180 square meters. Is almost like a floating, very sculptural piece that cantilevers, and it has recesses for all the models. The piece is completely painted in black, because the space is also be darked out. So the idea is that all the models will feel almost like floating within the space. It really pushes us to think about architecture and architectural design, urban design, not as being now and here, but it kind of requests from us that we think about a future.
I like hawker center because I like to hang out with my friends and my family.
We like hawker centers because it's affordable and there's a wide variety of food available there.
I like the hawker center because of the local coffee.
I like hawker centers because of the food that gets passed down generation to generation through their recipes.
In Singapore, food is very important, and hawker centers is the place where people celebrate food in community. So we think this subject of study for us, and we think that the hawker centers could be further explored and incorporate new things to make them more exciting and more relevant in the future. Hawker centers now are under the pressure of the food courts and the malls. So the question would be, how can we make them relevant again? How can we incorporate new things? How can we change and tweak the existing spaces so that they are relevant and attractive for people and to face the new challenges that Singapore is undergoing? So part of the research I'm doing in SUTD is related to sustainable space making by using digital tools. So digital tools for architecture is the way that we can integrate data with design intentions. So we can merge very objective information with our intuition to really create sustainable spaces. So we can actually design geometries that are self-shaded and create cross-ventilation that are utilizing more our resources, natural resources and energy, and to address more complex challenges. The challenges in the future, I think, would make the hawker centers be more integrated and articulated with society. So it's not a room where people go, it's more a space that is more connected, more open, and also more sustainable. So I see the hawker centers like something closer to a park than a room within a building.
Welcome back. Hope you had a good lunch and we are so excited to get going with our third keynote of the day, which will be on blockchain-empowered networks for IoT. Now, blockchain technology has led to a significant interest in managing databases in a decentralized way without the security concerns that stem from centralized platforms. Now, in this session, we will explore how we can leverage blockchain for IoT and discuss whether blockchain is suitable for latency-sensitive applications by analyzing the data freshness in the blockchain-enabled monitoring networks. We'll also talk about future challenges of blockchain-enabled networks for IoT. And to address all of this, I'd like to introduce our next speaker from Korea. She received the 2020 Haidong Young Engineering Researcher Award, the 2020 IEEE Communication Society Young Author Best Paper Award, the 2017 IEEE Communication Society AP Outstanding Paper Award, and the 2014 IEEE Communication Society AP Outstanding Young Researcher Award. Ladies and gentlemen, let us welcome from the Department of Information and Communication Engineering, Taeku Kongbu Institute of Science and Technology, Associate Professor Jemin Lee.
Okay, thank you for the kind introduction. Let me share my slides first. It is very nice to see all of you today, and I'm very happy to participate in this event today. Today, I will talk about the blockchain-enabled network for IoT. So this is the outline of today's talk. So I will briefly introduce the blockchain technology and then also discuss about how we can define the blockchain latency and see what kind of blockchain parameters are affecting the latency. Finally, we will see the impact of the blockchain parameters on the monitoring IoT networks. I think all of you heard about the blockchain before. Because basically the blockchain is the immutable distributed database, which has a sequence of blocks that are linked and replicated on multiple nodes. So as shown in this figure, the blocks are linked in this way. First of all, each block has multiple transactions, and then we can get the value from those transactions, and then also using the hash of the previous block, we generate the new hash values. And these new hash values are used to link the next blocks and so on. So because of this structure, if someone wanted to change certain data in this transaction 1, then it is almost impossible because they need to change all the hashed value of the previous blocks. So that's why, because of this structure, the blockchain can guarantee the data integrity. So when we consider the distributed system, there have been many issues, including the data integrity and consistency issues. This is related to whether the data in this database is the right one, and also which has not, that means actually whether it is not modified at all. And also whether this data is exactly the same as the one in the other distributed servers. To overcome those issues, the blockchain technology can be used. So by using this blockchain technology, we can solve the security concerns since it is impossible to modify the data. And also we can have the transparency for the transaction processing. Also, we have the consensus-based data verification. Blockchain is now used in many applications and services. So I want to introduce certain use cases in here. The first one is the blockchain-based core verification service for bank. This is developed by Samsung SDS and used in Korea for 16 banks now. So until now, the banking customers have to go through all the inconvenient process of the renewing their digital certificates every year for each bank. However, this bank sign manages the certificate information using blockchain and shared with other banks. So we can access the banking service of multiple banks using a very simple verification only. And second one is the Walmart food supply chain, which is developed by IBM. So by placing the supply chain on the blockchain, it allows making the process more transparent and traceable. So people can have more trust on their information, especially for the origin of a certain fruits or meats. They can have more trust on this information. And next one is quite recent one, which is the blockchain-based COVID-19 vaccination verification system. This application is now we are using this application in Korea now. After the vaccination, people can get the certificate from this app using their personal information. And this certificate can be used to get some exemption from social restrictions. So once they show this certificate at a certain restaurant and so on, then they can get in the restaurant with a large number of groups and so on. So although many applications of blockchain exist, when people see or hear about the blockchain, they usually come up with the Bitcoin, which is the digital currency. This Bitcoin and Ethereum, another blockchain system, are the public blockchain. The public blockchain is based on open point-to-point networks, so that means anyone can join or leave these blockchain networks anytime. Because of this anonymous participations, intensive consensus process is required to commit blocks to the chain, such as like mining in Bitcoin. So due to this reason, it takes a very long time for the block commitments. However, there is another type of blockchain, which is a private blockchain. Some examples are Hyperfabric and Reaper and so on. This private blockchain is type of blockchain networks where only a single authority or organization has control over the whole network. So for this type, only a lot of people can participate in this network. So they have very strict membership management. So that's therefore, because of this, complicated consensus process is not required at all. So it becomes more efficient. For example, the processing rate for one transaction, it becomes like 500 times faster in private one compared to the public blockchain one. So, when the company, they wanted to use this blockchain technology for their service and applications, they usually wanted to safeguard their sensitive information. So they generally use the private blockchain. So the previous use case one that I introduced before is also based on this private blockchain. So I also focus on this blockchain, private blockchain as well, and then use this Hyperfabric. Among the private blockchain systems, one of the most popular one is this Hyperfabric. Hyperledger is an umbrella project of open source blockchains and started by Linux Foundation in 2015. And now many companies are participating in contributing to this project, including IBM and Intel and so on. So they provide the modular architecture with a smart contract execution and configurable consensus and membership services. And also we can download the code for the implementation of Hyperfabric in the following links. So we also use this code from this website for the implementation, and then we'll talk about more details later. I will now describe how the generated transactions become the blocks and commit to the ledger in Hyperfabric. This is about the transaction flow. First of all, in the Hyperfabric networks, there are multiple nodes, like a client which generates the transactions, and then endorsing peers and ordering peers and committing peers that has the ledger. So I will describe the whole process that of the transaction flow in 3 phases. The first phase is the endorsing phase. So the clients, they generate the transaction proposal and send it to the endorser. Then this endorsing peer endorser check whether this proposal is okay. Basically, they check whether this proposal requests a certain change in the current version, not the old version, and so on. So if this proposal is okay, endorsing peers give the endorsement. If the client receives the endorsement from multiple endorsers enough, then they transmit this transaction to the ordering peers. Then in the ordering phase, the endorser endorsed transactions is ordered chronologically. Then the ordering peers generate a block that contains multiple transactions. Here, there are 2 important parameters affecting this ordering service. First is the block size. This is a maximum number of transactions in a block. And another one is the block generation timeout. For example, if the block size is 10 and timeout is 2 seconds, when the number of transitions in a block become 10, within 2 seconds, it becomes a block. When the block is now fully filled within 2 seconds, I mean within the timeout, then the block is also just generated after the timeout. So like this, those two parameters are affecting the latency of this ordering phase. We will discuss it later again. And the last phase is validation phase. So each peers with the ledger receive the generated block from ordering peers and verify whether this transition in the blocks are correct ones. Mainly, they do the verification system chain code to investigate whether the endorsement in each transition is valid. Secondly, they do the multi-version concurrency check. This is mainly to check that whether this version of the key captured during the endorsing phase is the same as the current version in the ledger. So if some transitions do not pass those validation, they become invalid and do not update the ledger. Then let me talk about the challenges in utilizing the hyperledger fabric. As talked before, the blockchain has many benefits, especially in the aspect of security. However, there are some costs we need to pay, which is the additional latency. So I believe this latency can be a main drawback in the utilization of the hyperledger fabric, especially when we use this blockchain for real-time or latency-critical applications and services. Hence, in the following slides, I would like to discuss about this blockchain latency. Specifically, I would like to answer those 3 questions like how long the blockchain latency will be, and how do the hyperledger fabric parameter affect the latency, and then how we need to design the blockchain-enabled network. So next part is to answer the first question, how long the blockchain latency will be. So this part is based on our recent paper, which is emerged in arXiv now. So you can find more details, more information easily in this link. So now, let me define the latency in hyperledger fabric networks. We have defined 3 phases for transition flow before. We have now defined the latencies for those 3 phases. First is the endorsing phase, so which is the time taken from the transition generation at the client until getting the endorsement from the endorsing peers. And the second one is the ordering latency. This is the time taken from the time that a transition enters an ordering service and until it gets out as a block. And the last one is the validation latency, which is a time taken to validate and to commit this new block to the ledger. So all transitions in the same block are validated sequentially, but they are committed to the ledger or together as a batch. So all the transitions in the same block have the same validation latency. So the total latency will be the time taken to process all those phases, and we define this latency as the ledger commitment latency here. So to design the blockchain-enabled networks, we need to know about those latencies. For that, we can measure them by implementing the hyperledger fabric, but also it is important to analyze the characteristics of those latencies. This is what we have done in this work. To measure the latencies, we first implement the hyperledger fabric version 1.3 here in the machine with those specs. Also, we use the Kafka zookeeper-based ordering service and consider 1 endorsing peer and 2 committing peers and so on. We measure the latency with changing hyperledger fabric parameters, including the transaction generation rate at the client's block size and block generation timeout. This is the measurement result. Based on the measured latencies, we plot the histogram first, which is the blue bars here. So we then, based on this shape of the histogram, we then find the probabilistic distribution which match well with this histogram. So we found that for inducing recency, the exponential distribution match well. For the validation recency, the GEV gives the best fit. And for the inducing ordering recency and total recency, we found that the gamma distribution fits very well. Regarding the total recency, the best fit distribution is the gamma distribution, so which has the PDF in this form. They have alpha and beta here, which are the shape and the rate parameters. So based on this histogram, we found, based on the histogram that we obtained before, we found the alpha and beta that gives the best fit to those histograms. So you can see here that even we change the transition generation rate from 8 to 11, the gamma distribution fits well. To check whether it does really fit well or not, we have also done the KS test. So KS test is a statistical test that evaluates the goodness of the fit. So usually the test returns the KS statistic values, and if this value is smaller than critical value, which is 0.05 in our setting, we can pass the test. So as you can see in this table, we can see that for all cases, the KS statistic value were less than the critical value, so that means they all passed the test. We also plot the CDF of the total recency. So as you can see here, although they are not exactly the same, but they are very similar each other. So for different settings, such as different values of timeout and block size and transition generation rates, we also provide the alpha and beta that gives the best fit. You can find more information about this kind of data in our paper. So we expect that people can use those results for their own research without having the difficulty in implementing the hypertrophy. However, I also need to mention that the fitting not always works well. For certain cases, we cannot find any distribution matches well. So we also investigate what those cases are and found 2 cases that does not have any best fit distribution. The first case is the timeout dominant block generation environment. For example, when the transition generates very slowly, then blocks are hardly filled out within the timeout. Then most of the new blocks are generated by timeout. So in this case, the ordering recency becomes equal to the time of the ordering recency become equal to the timeout for a large portion of the transitions. So this is why we have some peaks in the histogram like here and here. And in this case, they does not have any similar probabilistic distribution. And the second case is the block size dominant block generation environment. For example, when the transition generated very fast, then most of the new blocks are generated with the maximum size before the timeout expires. So in this case, the blocks are generated very fast, which gives a large load at the validation phase. So each block needs to wait very long time at the validation phase, which will provide this long tail in this histogram like this. So this case also does not have any similar probabilistic distribution. So for those cases, the fitting doesn't work well. But however, I think those cases are the ones that have very unreliable hypertrophy setting, so that we might not have in real applications or service. And now let's see what kind of blockchain parameters affect the recency. This part is also based on our paper, which is published in this year. So you can find more information in this paper. So for this part, we have shown the effect of those key hyperfabric parameters. When the transactions is generated at the IoT device, we need to go to the hyperfabric networks, networks. So that's why we also need to consider this successive transfer probability as a key parameter in hyperfabric. So not only with the block size or timeout or transition generation rate, we also consider this successful transition probability. So because the generated transition, when they reach the hyperfabric network, the communication can be unstable or fail. So it might not arrive at the hyperfabric network successfully. So this probability is to show that the probability that the transition is successfully delivered to the hyperfabric network. And also, we also need to see the impact of the number of indexing and ordering periods, which is related to the hyperfabric network design issue. So based on, so first we see the impact of block size and block generation timeout. So here, x-axis are block size and block generation timeout. And you can see the red curve in those graphs, red curve showing the blockchain latency. So here, we need to first know that as the block size and timeout increase, the block generation rate decrease. Because block size, when the block size is smaller, then block will fill out very fast, and timeout is smaller, then they also generate the block very fast. So based on this understanding, for when the block size and block generation timeout are small, the blocks are generated very fast. So it gives long latency in the validation phase. So the latency can decrease as the block generation rate decrease. However, after some value of the block size and timeout, the total latency increases because this is because the ordering latency increases as the block size and the timeout increases. So it is important to set up the block size and timeout properly and carefully to lower the latency. Next, we see the impact of transition generation rate as well. So as the transition generation rate of the certain key value increases, we can have a frequent update on the target key value. But this can cause the MBCC verification failure because the version they used in the indexing phase can be changed before they commit to the ledger. So then they become the invalid. So the total latency increases as the transition generation rate increases. The next one is the impact of the successful transmission probability. So as the successful transmission probability increases, the latency decreases first because the higher transitional labor makes the block generation faster. However, after a certain point, this higher transitional labor gives higher load at the hyperfabric networks, so the latency increases. We also see the impact of ordering and indexing nodes. So here, the ordering nodes is K here, and the indexing node is E here. As we increase the ordering nodes or indexing nodes, we can see that the latency increases. So, however, actually, if we have a more ordering nodes and more indexing nodes, the hyperfabric networks become more reliable. So there is also some trade-off between the latency and the system reliability in hyperfabric networks. As a last part, we will see the impact of blockchain latency on monitoring networks. So this part is also related to our recent paper, which is uploaded in archive now. So you can find more information in this paper as well. Blockchain-enabled IoT networks can be shown like this figure. So each IoT device transmits transactions to the hyperfabric networks, and all the data are managed in the ledger. As a one example, what we are going to see here is the blockchain-enabled monitoring networks. Here, each sources and sensors distributed in the network, they sense the information of its surrounding area and generate the packet and with the observed information. And this packet is transmitted to the nearest base station and delivered to the hypervisor fabric by this base station. The packet is then in this network, there can be two types of latencies. The time first is the transmission latency. This is the time taken to transmit this packet to the base station. And also we will have a lecture commitment latency because these packets need to be processed in the hypervisor fabric network to commit to the lecture. Here we consider the age of information to see the impact of blockchain latency. This is this age of information is the elapsed time since the information was generated. So that's why the age is used here. So when the sensor measures something like 5 minutes ago, then the measured information have the age of 5 minutes now. So this age of information is also related to the accuracy of the information because the older information usually gives different information to the current one. So this is actually quite important measurement in machine learning as well, since the old information can give the wrong decision in machine learning applications. So in the sensor network, in the database, they receive the data and update the information. So the age of information in this database can be seen as the AY paths like here. So for example, when we have the updated data at this point, TU1, then the age of the information drops, and then the age become increase linearly as time goes, and then they drop again when they have another updates of the information. So we use this age of paths to measure this AY related performance, such as the AY violation probability here. So AY violation probability is the probability that the AY is being larger than this target AY. This is actually due to the target accuracy that we wanted to have. So this probability shows the portion of the time that we have less accuracy than target accuracy for certain information. In the blockchain-enabled network, we also need to consider the MVCC verification carefully because actually not all the transactions update the information in this network. Only the ones past the validation can update the information of the lecture. For example, let's say the packet is generated at this point, GK-1 for the version 1, and they transmit this packet to the hypervisor fabric, and they arrive at this point, K-1, and they do all the processing to commit to the ledger. And then after this point, at a certain time, this UK1, they can update this packet related information, and the version will be changed to the version 2. However, before this update happened, they can also generate another packet at the sensor. And at this point, they can also generate for the change of the version 1. However, when they arrive at the hypervisor fabric, the version is already changed to the version 2. So this packet can be invalid. So when we consider this age of information and so on, we only need to consider the packets that gives the valid updates. So that's why we call it as the effective packets in this work. So all the details about the AI performance and then mathematical analysis, you can also find more information in this paper. So here we simply see the impact of network parameters in this AU age of information aspect. First, we can see that as the block size increase and timeout increase, as we can see before, the AY also decrease first and increase later. So this is also related to the validation latency and order latency and so on. And so here we can see that there exists the optimal block size and optimal timeout that provide the best performance in terms of AY and AY violation probability. So those optimal values can be changed according to the different network setup. So here, this optimal value, so based on this result, we can set up this optimal block size and timeout according to their own network setup. And also we see the impact of target successful transmission probability as well. So having higher successful transmission probability means communication environment is reliable, and usually in the wireless network, having higher successful transmission probability means is always good, because always good. However, in this blockchain-enabled network, this higher successive transmission probability is not always good, as we can see, as you've shown it before. So this is why the AY decrease first and increase as the successive transmission probability increases. So when we design the blockchain-enabled network, we need to carefully consider the blockchain latency because the design need to be changed according to the blockchain parameters and the communication parameters, which is different to the conventional networks. So as a summary, in this talk, I just focus on the latency in the blockchain networks, which is random and can be modeled by gamma distribution. This additional latency cannot be avoided when we use this blockchain applications and blockchain for the applications and services. So it is essential to design the blockchain-enabled network or systems by considering this ledger commitment latency. Especially for the real-time applications and services, this latency will be very critical. So when we bring this blockchain in those applications, especially we need to carefully design the blockchain network. And this blockchain and IoT and AI are the technologies that can be combined in multiple dimensions. So because the blockchain by using the blockchain technology, we can provide the trustedness in the data in like IoT and so on. Also, it can provide the trust on the training model for the machine learning because they provide the trust in the data they use for the training of the certain machine learning applications. So however, when we use this destructive blockchain technologies, we also need to think about the cost we need to pay. So this is the additional latency is definitely the one of the costs that we need to pay in here. So I want to emphasize about this latency issue in blockchain technology in this talk. And this is the end of my talk. And thank you for listening. Thank you.
Thank you so much, Associate Professor Lee, for that presentation on blockchain. And we have some questions for you right now as we go on to the Q&A segment. For those of you who are watching over there, do remember to type in your questions into the Q&A box or Q&A tab on the platform. And we've got quite a bit of time, so feel free to ask more questions. Now, first question that we have for you, Associate Professor Lee, is besides the additional latency, what are the challenges of applying blockchain to IoT? Associate Professor, what do you think?
So besides the latency, I think there is also important issues that we need to consider. That is the load balancing. Actually, I didn't introduce the concept of a channel in this talk, But actually, there are some concept of channels in the hypervector fabric. So in each channel, actually, they manage the vector separately. So, and then we also see that as we increase the transition generation rate, which means the transition generates very fast, then the latency increase very fast as well. So by this, we need to distribute this latency at the transitions over the multiple channels so that we can reduce the latency to commit to the blocks. So this order balancing will be one of the issues that we need to carefully consider in the blockchain design.
Thank you so much for answering that question. I hope that addresses the question from our audience. There is another question here that we have. It says, what kind of applications matter in the age of information? Associate Professor, what do you think?
Yes, so age of information is actually very important measurement, I think. This is actually a matter for all the applications that control the system based on the sensing data and so on. For example, in the autonomous driving case, when we do this, we need to have all the sensing information in the real time. And this accuracy of the sensing information is very important because when they can affect our action and decisions. So based on this, actually, it is very important to have the data, the fresh data, which has a low age of information. So I think we can develop some technology for those kind of system and applications. We need to consider this age of information concept, I think.
Thank you so much. We have a third question over here, and this time they're looking for a user case. So Associate Prof, they say, can you share a user case, if any, of blockchain technology used in federated learning for 5G in Korea? Do you have something like that?
Oh, this is actually a bit difficult question. But actually, I do not know any user cases that apply this blockchain for the federated learning. But I think we can definitely use it because in the federated learning case, we also need to share this learning model between the nodes. So to have the trust on this model, we need to use the blockchain technology, of course. Yeah.
Thank you so much. Let's see what is our next question. Next question is, a blockchain network itself needs to be monitored. Can this blockchain method be self-monitoring? What do you think?
Blockchain networks, yeah, so private blockchain network need to be monitored, and actually it's monitored by certain organization and authority. But actually, I cannot understand what the self-monitoring means here. But the private blockchain is need to be monitored by authority. Yes.
Okay, our next question, Associate Prof, please. In your talk, you have shown the effect of blockchain parameters on the blockchain latency, such as the effects of block size, timeout, and the transaction generation rate, and so on. How can we use those results in real implementation of blockchain to lower latency? How can we do that?
Yes. So in this talk, actually, I want to emphasize the latency in blockchain design. So as I shown before, the block size and timeout, they affect the latency critically. So based on the applications and then the system that you wanted to bring this blockchain, you need to determine those parameters very carefully. And also, as I shown before, this transition generation rate also affects the latency a lot. So as I explained before, we also need to use this result to distribute this transition route to over the channels and so on.
Thank you so much. Now, we've still got quite a bit of time, so if you're watching over there, do feel free to drop in more questions into the Q&A tab. Our next question over here is Is there any study on the energy consumption impact if blockchain technology is widely used for all forms of commercial transactions?
Energy consumption, you mean?
That's right. Can we see that question again? Is there any study on the energy consumption impact if blockchain technology is widely used for all forms of commercial transactions? So is there any study on the energy consumption impact?
As I know, there is some work, but usually the energy consumption is matter for the public blockchain case. As I explained before, there are two types of blockchain, public and private. For public blockchain case, I think all of you know about the mining process, right? So anyone can mining and then can attach to the block for the transactions. So for this mining process, actually, we need to use a lot of computation power and also energy and so on. So this is quite a matter. However, in a private blockchain case, actually this the ordering service is matching to the mining process in a public one. This ordering service requires very small computation only. Actually, what they do is they just collect all the transactions, enter the ordering service, and they, if the number of transactions become like block as much as the block size, then they generate the block. So this is very simple process. So for a private blockchain one, I think the energy consumption may not be that issue. Yeah.
Thank you so much for addressing those concerns, and we hope that addressed some of the concerns they have about energy consumption. Next question is, are there any blockchain-empowered cases in the manufacturing sector? What can you tell us?
Use cases in manufacturing sector?
That's right.
Manufacturing sector. That's
Not really?
It's a bit broad question. So, but manufacturing one, of course, I think blockchain can be applied in any places they need to manage the database and they require the integrity. So integrity means we need to make sure no one changes this data. So of course, I think applications in manufacturing sector, they require this. They can use this blockchain technology, of course. Yeah.
Great. Hopefully this next question will be something more specific. And the question is, which one do you think might be more promising in the applications of 6G? Private blockchain or public blockchain? What do you think?
As I actually, in my opinion, own opinion, I think private blockchain is more important. And I mean, the application of a private blockchain will be more various. So especially for the 6G as well, I think. So especially in the 6G, as I think the Tony also mentioned about the 6G requirements and the system and so on. But among them, actually, one of the important thing is the machine learning based control and management in 6G. So to do that, actually, we need to train this machine learning model. And the data is also very important. But if they use the different wrong data for the training, then it will be a big problem. So we can use this blockchain technology to manage the database and then provide the trust on the data they use in the training and so on. So I think the private blockchain will need to be really works do the more jobs in the 6G and so on.
And there you have your answer. It's private blockchain. Coming up next, we have another question over here, this time about telecommunications, and it's specific to Korea. It says, how active are Korean telcos adopting blockchain technology in their 5G architecture?
As I know, they are not specifically adopting this blockchain for 5G communication one. But as I know, they also developing certain applications that require the blockchain and so on. So I think not yet they apply this blockchain for the communication architecture and so on. Yeah.
Okay, let's see if we have any more questions. Do we have another one? That's it. Okay, we have finished all the questions from our audience. And with that, I want to thank Associate Professor Lee. Thank you so much for joining us from Korea with that empowering presentation on blockchain and for answering all those questions from our audience. Thank you so much.
Thank you. Thank you very much.
Thank you. Okay, just to let you know, there's a small little message over here that the video that you are watching right now will actually be available on the SUTD website. So you can actually look out for that. All right, I believe it will be available probably sometime next week. And you can actually watch all the replay of all the talks next week. And we're actually going right now for a short 5-minute break. So we'll see you back here for our next session in about 5 minutes time at 1:45 p.m. Welcome back. Hope you're enjoying all our sessions so far. Now, coming up next, we are going to dive straight into chip-to-chip communications across a galvanically isolated barrier. Now, sending a signal across a galvanically isolated barrier is a common requirement in many aspects of modern electronic machinery. The application of wireless communication in isolation device is still based on relatively simple mechanisms and signaling schemes, and opportunities exist to explore and develop better chip-to-chip wireless communications for future products and applications. Our next speaker is the co-founder and microchip architect of MPIX Innovations, which specializes in custom analog circuit design and manufacturing. He has more than 20 patents in the field of analog circuits and isolation technology, and his current interests involve the design and development of new and novel methods of signal communications across galvanically isolated barriers in multi-chip modules, and he has filed a patent for a new isolation method suitable for broadband power devices such as GaN and silicon carbide. Ladies and gentlemen, let us welcome Mr. Richard Lam.
Hello. Yes, thank you, and good afternoon to everybody. So let me just share my slides first. Screen mode. Okay. So first, I'd like to give a short introduction to myself. I am currently running a startup company in Singapore, focusing on various kind of semiconductor design, with special interest in the area of isolation technology, right? And prior to starting MPIX in October 2019, I was formerly the Senior Director of R&D for Broadcom's Isolation Products Division, where I kind of spent the last 2 decades working on all kinds of isolation devices needed for the modern electronic industry, right? My special interest, primarily, I started my life in electronics as an analog mixed signal IC designer. And progressively, as I work in the area of isolation device, I come across the need to be able to design semiconductor devices in multi-chip modules and also in system-in-package kind of development, right? Right now, of course, besides minding my new startup, I will try to dream of new products and also focus on training some of my younger designers in terms of the technology as well, in terms of the skill of doing analog design. And one of my personal hobbies is photography, but given the COVID situation, can't really travel to all over the world to take nice, beautiful pictures, so I'm kind of limited to doing that only in Singapore. Now, first, when I was asked by Prof. Yeo to give this topic, to basically present in this communications seminar, one of the questions I have for Prof. Yeo was that, well, I am not in the mobile phone or the wireless world. Would my topic be relevant to the audience, right? So Prof. Yeo assured me that no, my workshop and seminar is about communications, not just about mobile phone. So I was looking back at what I've been doing for the past 20 years and realized that in some sense, all the activities that is done on isolators are based on some form of communications, right? And here perhaps I take this opportunity to kind of explain what a galvanic isolation barrier means, right? And what is it that determines a product to be called a galvanic isolator? And why do we really need to send signals across it, right? So before we get into the technology specific, isolation components actually is found all over the world, all right? In fact, all around us to be exact, right? You can call it ubiquitous, just like McDonald's, every corner you see something. And but most of us kind of take this technology for granted, and we probably don't even know that we interacted with such technology almost on a daily and perhaps even hourly basis, right? So you can see that isolation technology exists in as simple applications like elevators. It's also found in wind turbines, robotics, industrial cranes, right? The high-speed trains that you go on, the electric trains, they all require this kind of technology. Factory automation, and of course, more recently, in the area of renewable energy and electric cars, isolation is actually one of the very key components that make such technologies available. Right? So today's topic, I'm just going to cover a brief overview what semiconductor isolation devices are, right? Where isolation is used and why is it important, right? Getting robust digital signals across isolation barrier is really the key to making this successful, right? So what are the applications that we go into? I've already listed some, but maybe we'll go into specific details of which application, or more importantly, which emerging applications such technology will be very useful for, right? And then going a bit forward, what is needed to be a good device? What are the existing devices? Where are the research areas, the new development that basically charter new grounds and of course new opportunities for us as far as this technology is concerned. And last but not least, I will cover a bit about what we are trying to do in MPICS in terms of providing a new form of isolation technology for the future. Yeah. So give you a history of isolation semiconductors, all right? Maybe the word, I shouldn't use isolation semiconductor because in the early days, isolating signals started up with transformers, right? Maybe the first transformers are used to isolate power, but very quickly people realized that you can actually use transformer to also signal across an isolation barrier, okay? Now, the concept of isolation barrier means that it is a substrate or a media whereby you allow signals to go across, but you ensure that there's really no electrical signals in the form of high voltage potential that actually can go between the primary and secondary side, right? So transformers is definitely in terms of the evolution, the beginning of when people start to have voltages on both sides of the transformer being at largely different potentials, and yet you're able to bring information, or maybe in the case of a power device, bring power across the transformers, right? Now, then of course, besides transformer, you can also use capacitors to basically use it as a media to signal across a application where, again, the potentials on both sides of the applications are drastically different, right? And sometime in the 60s, towards the 70s, when the LED was invented, this is kind of going back to the history of HP, optical isolation device start to appear in the marketplace, right? And in this case, the technology can be as simple as a light source, primarily that's an LED, and a detector, mainly a photodiode. And in order to send an electrical signal across, you would basically energize the LED. The photodetector will simply receive the light, and all this happen inside the package, right? So this is like a device with both the LED as well as the photodetector inside the same package. Of course, in between the LED and the photodetector will be some form of transparent media. Okay, but this transparent media is unique in that it can hold off thousands of volts between the primary and secondary, right? But more recently, since around the 80s and 90s, right, non-optical solutions start to become commonplace, right? So you have all kinds of newer ways of bringing signals across a galvanic isolation in terms of using non-light-based solution, right? So generally, in the market today, there are two types of commonly used technology. One is magnetic signals. Of course, magnetic signal can go past a galvanic isolation device, as well as capacitive, where you actually try to bring signals across from one chip to another chip using capacitors, right? And on the picture here that you can see, actually this is a analog device part. You can see that there is a primary chip on the left. Towards the center is where they actually have magnetic coils over some kind of a insulator material. That's really what galvanic isolation means, right? And in these coils, the signals is transmitted magnetically and then received by the secondary chip, which is on the right side, and reprocess the signal so that essentially you try to replicate what is from the primary into the secondary. I mean, in basic terms, that's what isolation devices are all about. Okay, right. Now, one thing I was looking at this and this evolution, and I like to think about it as a continuum in terms of the isolation technology. So in some sense, it started as discrete transformers, it went to optical, and now it actually went back to transformer, but in a much more miniature scale, right? So the interesting thing about this market is, unlike, let's say, mobile phone, today you probably do not hear of what you call that, the older 2G technology is completely superseded by 3G, which will eventually be completely superseded by 4 and 5G and so on. In the world of isolation semiconductors, you find that even though the technology has evolved from discrete to optical isolation and package to now more like non-optical magnetic and capacitor isolation, you do find that all these technologies are still coexisting today. And none of this technology actually went through the whole process of completely eliminating or obsoleting an older technology. So this is something I felt was a very unique characteristics of this market. And today, you still have pulse transformer used in Ethernet wired communications. You have lots of optical communications device used in lifts, in electric cars, and all the place. And you also have magnetic and capacitive single chip-based solution like the stuff of analog device that is all being used today. So the market is actually growing, but the market is not having one technology replace another technology. Okay, so why is galvanic isolation so pervasive? And why is it so critical for us, right? So if you look at it today, electrification of human activities is a very big activity, right? Everything that you can think of that a human used to do or wants to do is now being electrified, right? So for example, right, in the past, we used to drive a gasoline. I still drive a gasoline vehicle, but now you have electric vehicles, right? So one of the interesting things about electric vehicles is that the moment you go to a full electric vehicles, right, it almost causes everything else to be electrified, right? So in a gasoline vehicle, for example, the aircon system would be driven with a belt from your petrol engine. But the moment you go on an electric vehicle, where's the petrol engine that provides you the energy to drive the aircon pump, right? So so things have changed. So even the aircon now needs to be 100% electrified, right? Now, of course, semiconductor galvanic isolation now is undergoing a very interesting dynamics in terms of the semiconductor process versus the needs of the application. So on the one hand, you'll find that Moore's law and Moore's law scaling, voltage scaling, dictates that intelligent and control engines like DSP, microcontrollers, and all the smarts that you have in your system board are being fabricated or being designed in smaller and smaller geometry because you want to put in a lot of computation and processing power to it. And in doing so, the geometries of the semiconductor that's being used to fabricate such devices are getting smaller, right? And recently, TSMC just announced that they are in production at 3 nanometers and will go on to 2 nanometers. And if you think about it in terms of voltage scaling, such devices operating at very, very low voltage, definitely sub 1 volt. Now, on the other side, we have the new power devices. In an electrical system, you need both. You need the intelligent part, and you need the part where it drives the motors, for example, the power and energy. And in that area, you find that the technology is trying to push voltage higher and higher, right? So, simple reason, if I can switch things at higher voltage, technically I can reduce the ohmic losses due to copper losses and things like that, right? So you find that there's this distension in terms of the direction at which power devices are going and at which intelligent control is going, right? However, in all modern power electronics or electrical machinery system, you find that it's all being digitized. All the algorithms to control the motor, everything is all done in using digital computation. But this information needs to be relayed safely to the power side. And in order for that to do so, the one of the safest and best way is to introduce a galvanic isolation in between, meaning you keep the two domains separate, where there is power, there is large switching noises, there's huge EMI. You keep it separate from where there's intelligence, where the signal processing needs to be running at high speed, needs to be operated at low voltage, but at the same time, it's so easily disrupted and also very noise sensitive, right? So in some ways that looking at the way the technology in semiconductor is evolving, these two directions is never going to come together, meaning the power device are ever going to operate at higher voltage with faster switching speed, which generate more noise. At the same time, the intelligence portion, which needs to control the power device, is actually going towards a higher amount of computation and going towards lower voltage, right? So that's why never the twain shall they meet, right? So, and in some ways, this makes the galvanic isolation technology a very unique technology that needs to sit inside these two mega trends. Okay, right. So, give you an example of what actually happens when we transfer signal across a galvanic isolator. In this case, I give you an example where this is a gate driver. A gate driver is a piece of electronics, we call it a power device driver, which actually drives, let's say, an IGBT or silicon carbide or a GaN switch. Right? Of course, the GaN switch just does one function, turns on and turns on. And when it turns on, it can sing maybe tens of amps to thousands of amps of current. And when it turns off, we want it to be purely in the off state, but when it's in the off state, it needs to be able to handle pretty high voltages, maybe in the range of 600, sometimes thousands of volts, right? So that's the power device. But preceding the power device, you would have the driver itself. Now, this driver, invariably, the input is some kind of logic signal where when it is logic high, if you turn on the switch, and logic low, you turn off the switch. It's as simple as that, right? But however, this decision of turning on and off this logic switch, right, has to come from some intelligence. And on the primary side, where we have the control system and interface, typically that's where you also have the human interface, right? That's where you have the man-machine interface and perhaps system-to-system communication interface. But right before the isolation device, the galvanic isolation device, you would have the controller DSP. And this is the heart of all the algorithms, the heart of how and when you turn on switches, the timings and the feedbacks that's required to basically, in this particular example, maybe turn some motor or convert solar energy from DC to AC, for example. Right? Now, that is on the drive side. And typically, if you were to drive a power device, there are a lot of hazardous things that are happening on the power device side. Like things can go wrong or go wrong very badly. right? So for example, you would have a situation where, let's say a power device goes into an overcurrent situation. And that, if you don't shut off the device in a nice controlled fashion or quickly enough, it may cause it to burn out and completely destroy the system, right? You wouldn't like that to be happening when you're driving your electric car, for example, right? So in other words, there's also a lot of needs for sensors on the isolator side, on the power side. Sensing current, like if in the case of motor, sensing torque, for example, sensing temperature to make sure that things don't get overheated. And such information, of course, has to be relayed back to the primary side, whereby the DSP would then process and make decision how to handle the situation, right? So you'll find that in a typical application, yes, we would send signals from primary side to secondary side of the galvanic isolator, and yet there will be essential signals related to feedback and diagnostics that will come from the secondary side back to the primary side to make the decision, right? So this separation is very clear, and sitting right in the middle will be a galvanically isolated device, in this case, a galvanic isolated driver. Okay, let's going deeper a bit. Let's take a look at what it really looks like. So what we shown earlier was the isolated gate driver that I've shown you earlier, right? And in this case, we have a classic three-phase inverter motor driver, a variable frequency three-phase inverter motor, right? And let's say that each of the phases are driven using a PWM signal. That means there will be two power devices, a high side power device and a low side power device, where they will switch on and off to generate a three-phase signal in order to drive the motor, right? And this control algorithm is all sitting on the digital signal processor on the primary side. So you can see that in such a case, that the controller side may be operated, let's say today, 3 volts, 5 volts. In the future, it will go down to 1.8 volts, but in the industrial market today, 3 and 5 are still common voltages being deployed. But on the other side, the bus voltage are going from maybe now 600 to 1,200 volts, and in the future, they need compliance up to 1,700 volts, especially with the newer silicon carbide device, right? So you can see in a typical system, let's say a three-phase system, there will be quite a number of signals that's actually going from primary to secondary. And there's also quite a number of signals going from secondary back to primary as well, right? And the reason why such a configuration is done is that you will find that on the secondary side, when the motor switches, for example, it will generate a lot of ground noise, right? And also the magnetics will create a lot of EMI, right? And this EMI might be large enough to actually corrupt signals that is coming on the primary side if you don't provide isolation. So in some sense, isolation provides the ability to reject what we call common mode noise, right? So yes, you are sending signal across, and yet when the power electronic side will make large noises, the primary side is totally impervious or immune to it, right? So that makes the system pretty robust in terms of control and diagnostics, right? Now, there is a secondary requirement, a very important one too, is that the galvanic isolator must be able to hold off thousands of volts. And this is governed by regulations, right? So there are IEC safety standards that actually ensures that the galvanic isolation does not suddenly break down and you have hundreds of volts coming into the primary side. And because if that happens, most likely the primary side will get destroyed, but there's also a safety problem should some human being who is operating the controls on the primary sides get hurt or worse, get killed, right? So there are safety standards related to isolation device, and these are national bodies like or international bodies like IEC. There's international bodies. IEEE also has certain standards related to isolation and safety, as well as certain country level standards like BE and so on. Yeah, so a bit about what is the problem with the noise between the primary site and the secondary site, right? So in terms of our ability to send signal across the galvanic isolation, which is a non-ohmic media, maybe that's the right word to use, that we cannot really put a wire across and send a signal across the isolation barrier. It must be through one of the non-conductive methods. For example, in this case, it could be a magnetic signal, it could be a light signal, optical signal, or it could be a magnetic signal, right? So these are generally the three ways where we bring signal across from one end to the other end. But on the other side, you'll find that when the power electronic switches, right, very often we are talking of motors that are in the kilowatt range. For example, in your Tesla car, right, going from 0 to 100 in 3.5 seconds, really needs a very powerful motor, right? And when this motor switches, if you look at the PWM signal that's driving the three-phase of the motors, these are relatively fast switching on-off signals, which means that the magnetics are actually going to see zero current on one cycle and maybe several tens or even hundreds of amperes on the on cycle and so on. And this tend to generate a lot of noise in the ground portion of the power electronic side, right? Now, this ground noise is to be kept isolated on the power device side, right? So that it doesn't actually affect the primary side. But in reality, all isolation devices do have this thing called leakage capacitance, or maybe sometimes even leakage inductance, that certain amount of these signals can actually flow from the secondary side to the primary side. And this becomes a big challenge in deciding how to choose the right media, right, in order for us to bring the signal across, right? So for example, just take an example, if I have two PCBs, one holding the DSP on the primary side, goes through a series of isolators. You saw that in the earlier example, we have quite a number of so-called isolation device, and each of these do have leakage capacitance, right? So let's just take the example that we are able to design such that the total capacitance within the primary and secondary sites, right, has only a leakage capacitance of 1 picofarad, right? And some of these high voltage devices are switching at rates of 100 kilovolts per microseconds, right? And when in doing so, you find that simple CdV by dt will dictate that you really have common mode currents of 100 milliamps going from the power side to the primary side, and this can actually disrupt signals quite a bit. Right. Right. So if we review a typical specification isolation device, I just put some of the typical solution that we have today. You'll find that I kind of listed what we think, or we can find state of the art in the marketplace today, where the highest speed they are, what kind of high voltage rejection in terms of common mode noise you can do, as well as key specs like latency and power signaling and so on, right? But I would say that the top three would be the important specs, right? One, how much data can you get across? Secondly, how much noise can you reject? And thirdly, how fast can you get the signal across? Because invariably, we are dealing a lot with NRZ signals today. At least today, most of the solutions are based on NRZ signals, right? Right? And of course, if you look at it, generally speaking, optical technology tends to be a bit slower, right? Tends to have poorer noise rejection. Latency, they are also somewhat slower, right? But they have other benefits, like, for example, they will have very little effects on noise because optical isolation tends to be very good at isolating the ground noise from the primary to the secondary side because of the very low capacitance that you can do. Whereas magnetic structures and capacitive structures, they may be able to switch faster, lower power. They use more sophisticated modern techniques like on-off keying or some of them edge control. However, they do have certain limitations in terms of the fact that maybe the EMI is a bit more, and then we will also have to basically operate them in certain environments. Okay, so we do have a wish list. I think everything has to be better, right? Higher speed, higher noise rejection, lower latency, and so on, lower power, and the rest of it, right? Now, so in terms of isolation device, you'll find that generally today, they are constructed mainly based on what we call multi-chip module. And like we have shown you this analog device part, is actually integration of logic transmitter. The isolation device now is an island in the center. It's just a piece of silicon with a isolated transformer. And then the receiver device, which also integrates the gate drive technology, right? So this is generally the current state of the art. Most of these devices are actually found inside typical packages, like SO packages, where the leads are on both sides of the package. And between the primary and secondary side of the package, you can actually hold, let's say, several hundreds to several thousand volts. Yeah, so where do we find the use of such technology? In fact, like my first slide, everywhere, right? But of course, right now, there's a lot of interest in the use of isolation technology, especially in electric vehicles, right? This is the new market for a lot of companies, and even telecoms firms, communication firms like Huawei are now getting into the game, right? If I'm not wrong, last month, Huawei actually started selling their first electric car, right? And you find that isolation products exist in the powertrain, in terms of the gate drivers, the sensors, in aircon systems, again, you need a motor for the aircon. In the chargers where you have AC to DC converters or maybe DC to DC converters, in the braking system where you actually recover energy from the braking back to charge the battery, for example, right? And also there's isolation needs in terms of the control buses. Okay. Yeah. So what I've described earlier on is very devices that are relatively simple, which means that we have an NRZ signal on the primary side, and then we generate an equivalent NRZ signal on the secondary side, and it does its job. But increasingly, people are looking for more integration. So for example, having to drive the gate drive is not sufficient. Having the gate drive provide some kind of a feedback in terms of, let's say, the status of the power device, temperature, overcurrent, some kind of fault is more important, right? So devices in terms of the functionality has increased, and people are actually putting more and more into it. And one of the purpose is to reduce the number of isolators found in such device. Yeah. And driving these needs is really also certain so-called design methodologies that requires us to ensure that system designs are not just functionally correct, but they are functionally safe, right? So functional safety in automotive, functional safety in isolation technology is becoming very important. And generally, these are governed by ISO and IEC standards. And in very simple terms, it kind of means that when you want a system that's functionally safe or that it meets functional safety, you must either make sure that if there is a failure, it doesn't cause any subsequent catastrophic damage. So the amount of diagnostic, the amount of sensing, the amount of control, the redundancy of control are going to be increased. And some of these are becoming very important because there's going to be a lot more interaction between humans and machine. In the case like coexistent robots, you actually have a human being working smack next to a machine. And also that in the areas of like electric cars, right? You do not want to be driving your electric car. There's a functional safety and it subsequently causes you accident. But you'll be okay if there's a potential safety, there's a little warning message that predicts that the engine is going to fail and asks you to safely move your car to the side so that the service people can come and do the work, all right? So all these are actually driving the needs for more isolation device, right? So back to the isolator device, One of the key specs, of course, is data latency, right? And if you look at everybody that is doing a good isolation device is trying to says that my device has the lowest latency, like I am able to replicate the signal across safely in 20 nanoseconds, 10 nanoseconds, and so on. So getting the signal across quickly is definitely important, right? Getting the signal across error-free is even more important, because if you want the power switch to turn off and it's actually turned on, that will create a lot of problems, right? Now, this causes a lot of today's isolation device to compete on transmitting signals with the lowest latency possible. But because such latencies are so short, there's actually no chance for you to do any signal conditioning or source coding or error correction, because you simply can't do that in 20 nanoseconds and expect the data to be replicated on the other side, right? So in some ways, today's system will rely on the DSP to actually control all this timing, and the isolation device just have to operate as fast as they can, right? Now, so here is an example, and you can see that, let's say we take this three-phase system. You'll find that there's a lot of isolators. Each will have its own latency. And the timing for the latency is actually done on the DSP itself. One example would be when you turn on a high side power device, you must make sure you turn off the low side first. Otherwise, there's a crowbar current and you get a short circuit condition. And all these timings today is actually controlled on the primary DSP, right? And you can find that because all these isolation devices are their own device, there will be some variation in terms of the data latency. And all this has to be guard banded and accounted for in the DSP algorithm. However, if you look from the evolution of the power electronics device, actually the amount of power device that is being deployed is actually also increasing. So a typical two-level PWM system will have 6 IGBTs. Increasingly, multi-level systems are being deployed, which means that there will be more IGBTs or more power devices. And indirectly, this also means more power devices. And more power device also means that the cost is going to increase, and also your ability to control timing is going to be more challenging. The DSP has to do a lot more to ensure that all these devices are operating at the right timing that they are supposed to do, right? But there's a benefit, and there's the real reason why people want to go towards multi-level or more sophisticated type of power electronics. One of the value proposition with that, when you generate a two-level PWM signal, eventually you still have to filter it so that it's a three-phase sinusoid signal. But if you go to a multi-level system, it's a lot easier to filter. And some of these power electronics filters are actually very big inductors and capacitors. So there is a benefit in going towards multi-level, which increase the electronic cost, but it will reduce the magnetics needed to filter it before you drive the motor. All right. Yeah. So over here, we talk a bit about what is the current state of the art, which means that it is really a parallel structure. The DSP will control every single driver with one line, literally one logic line, and goes through the isolation to the driver. And the timing is all controlled by the DSP. So DSP not only control the state of the device, but control actually the timing in between states as well. So all the information is embedded in the timing control. Right. Now, if we are able to, perhaps, so this is something that we are working towards, is that what if we can resynchronize some of this data that goes through the isolation at the secondary side precisely, which means that the DSP will only control state but not timing. But when we bring it across isolation, the edges will be resynchronized. And when we do that, we find that it is actually possible to allow some latency, because at the end, the motor control loops are not really at the nanosecond rates. They are probably closer to the kilohertz hundreds of kilohertz rate in terms of the loop control mechanism. So it is actually possible to have some degree of latency, right? It could be a couple of microseconds, and the system will still operate well with the DSP doing all the controls. However, we need to be able to resynchronize the timing across isolation, right? And to do that, it will be very costly if such technology is not embedded inside the isolator, right? However, if we do such technology where the isolator can basically packetize, serialize, bring the information across, and resync the necessary states, it also means that every driver, every high side power, every low side power device is aware of each other's state. And when you do that, there is certain advantage when you reach situation where there's a fault and you need to shut down the system in a graceful manner, right? Which goes back to the reasons for functional safety, right? So this kind of approach requires us to really upgrade the way we do communications across isolation device, right? Not just processing NRZ signals, but processing more than NRZ signals. And of course, one benefit would be that if we can also have the isolation device basically handle not just one directional, but bidirectional, not just half duplex, but full duplex communications. Yeah, right? So, of course, sending signal is not just the only thing we need to do. We also need to send power across. Because if you look at a typical, let's say a multi-level, single phase or multi-level stage, you will find that we need to actually energize the gate driver because there's no nice power supply there for you to energize the gate driver. And invariably, this gate driver will be sitting on the source or the emitter of the power device. And when the power device switches up and down, you will actually find that this power supply is kind of like a floating power supply following the direction of the PWM signal, right? Now, this kind of power transfer will make system design very complex if you have many of these isolated floating power supplies needed. So if the power device, or rather, sorry, if the isolation device is also able to provide power, so not just send the signal across, but also send some power, we are looking at not very high power, power sufficient to enable a gate drive, and it could be in the range of maybe 2 watts or 3 watts, depending on how much gate charge is needed for you to turn on and off the power device, right? So for a complete solution, it's not just sending signal, we also need to send power. Yeah, so this is a fairly new product that we see on the market today. This is a Texas Instrument device. And if you look at the X-ray of the device, you'll find that they actually have on the primary side digital isolation. Texas Instrument actually does capacitive isolation. So in this case, you see there are 5 channels of data being sent across. It's not serialized, it's parallel, right? And on the primary side, they actually integrated a power transformer. It's a coplanar transformer capable of about 0.6 watts. So this is a bit lower power than what we need for gate drivers, with efficiency of maybe about, I think it was quoted in the data sheet, about 50%, right? So in some ways, when you deploy such a device, you only need to provide power on the primary side, and the secondary side will self-generate the power. I won't say self-generate, generate the power from the primary side to power whatever electronics you need there. And then the secondary side can simply be floating on whatever high voltage it needs to be. Yeah, so right now, the company that we have started, one of the development that we do here is to basically relook at all this optical, capacitive, magnetic, and ask ourselves a question: is there a better way of doing it, right? So currently we are still in the concept and prototype phase. We did file some patents regarding the ability to couple signals across microchips from one side of the isolation to another side, right? One of our goals is to really provide such isolation at very, very low leakage, right? And invariably, we are going towards the RF kind of transmission within the package, right? Now, we also try to do it such that you don't need special proprietary technology such as special high voltage capacitors on CMOS to basically allow high voltage isolation and yet close enough to send signals across. So this will basically make the cost of the product much lower. And most importantly, we are able to still put it in that little tiny package, have multifunctional, multi-chips in there. Yeah. So this will be our goal, right? So today, we do see quite a bit of multi-chip modules from power electronics maker. What you see on the left, where the sources are TI, SD microelectronics, and Infineon kind of product. These are packages, power packages, but most of them are still without the isolation. The isolation is kept outside of the chip, right? Now, what we can do is that with our kind of technology, we can enable kind of RF isolation from the primary chip to the secondary chip, and yet have the secondary chip actually also drive, let's say, a gallium nitride switch that is also embedded inside the same module, right? And in this case, there are many things that we need to focus on to develop. So for the power side, we need to have low inductance interface to the outside world as the switching gets faster. The isolation, of course, it needs to be good. We need to have true galvanic isolation that meet not just the noise standard, but also the safety standards, right? And then most importantly, we need to have thermal management as well, because now the switch and the ASICs or the A to D converters and the drivers are all sitting on the same packages to gather the isolation. So chips have to operate at relatively high temperature as well. All right, so this brings me towards the last of my slides. So I would say that one of the things that spurs me to keep looking in this area is that we find that isolation is really one technology that is irreplaceable. That means as human activities get more electrified, you will find that you actually need to use more isolation device, not less, right? So on the other hand, if you look at the kind of communications technologies that's being used to signal across isolation, in some ways we can say that it's relatively primitive, right? Like signaling simple things like FM signals, or sometimes like in the case of optical, even NRZ on-off signals. So there's definitely much more room for innovation in this area. And the good news is that the market is driving the growth of such technology. But perhaps maybe many researchers and many industry have not really put a lot of focus in this area. So there's still plenty of room for innovation. And we are pretty upbeat about focusing on this area as one of the core technologies for our company, right? Right. So so that's my last slide, and I thank you. If anyone want to reach out to me, you can scan the QR code and or email me. It's up there, and if there's any question, I'll be glad to answer.
Thank you so much, Mr. Lam, for that really comprehensive presentation. And of course, we do have some Q&As, so we'll be moving on to the question and answer segment right away. And the first question that we have for Mr. Lam is this. Given that there are many major players such as ADI and TI and Broadcom in this field, is there room for new players with new technology? What do you think?
Well, as I've stated in the beginning of my talk, you'll find that this is a very unique marketplace, right? We still have technologies that are very, very old today, used in large quantities, right? So it will mean that the competition like ADI, TI, Broadcom, they would be still doing relatively good business with whatever technology they have today, right? So in some ways, I feel that such companies will be reluctant to try to create very, very novel, brand new technologies. Yes, they are innovating, but maybe incrementally and not in a very revolutionary way, right? So definitely because of this, we believe that there is ample space for a small startup company like us to carve a niche for ourselves. But having said that, it is also a hurdle to change the mindset how people want to deploy such technology. I mean, the new technologies, because they're so used to having one isolator do one function, right? Being able to put many isolation functions together on a single chip and process it in a more futuristic communications fashion does present new challenges in terms of adoption. So, of course, for MPICS, we are working with some potential customers whereby we explore new architectures, not just new components, but we think that new components can be new enablers because the world of electrification is still evolving and evolving at a very rapid pace. And this is really driven by the fact that the new power devices like silicon carbide and GaN can do so much more in terms of efficiency, quality of control, and so on. Yeah.
Thank you so much for that answer, Mrs. Lam. For those of you who just joined us, we are with Richard Lam from MPICS, and we're talking about chip-to-chip communications. Please feel free to type in your questions for him while he's here with us. Now, our next question is, which applications, products, or industries would benefit most from what you have? Why? And how big do you think this market is?
I think right now, the most important market that will make a difference for isolation technology companies, including the incumbents, right, would be electric vehicles, right? Very simply stated, right, electric vehicles actually gone through a kind of revolution. The traditional automotive makers are actually people who are more savvy in the mechanical aspect rather than the electronics aspect, right? But because of the electrification, you find that there is a lot of new players entering the fray. Tesla is probably the best example, right? I mean, you can never compare Tesla, for example, with Ford. They are totally different companies with very different R&D, different technologies. So to companies like Ford, electric cars would actually be a threat, but to Tesla, it's a new core business, right? And more recently, you find that even the companies like Xiaomi, Huawei, I would say even companies like Google or even Apple, for example, are getting into the electric car one way or another. And this definitely drives the market. And when it drives the market with new players, it also means that people are more open to adopting new ideas, right? And when new ideas become commonplace, then I believe that that there'll be greater opportunities for everyone. Yeah.
Thank you so much for that answer. And we have a third question here for you, and this is it. How does your technology benefit new applications? Mr. Lam, could you elaborate?
Yeah. So I would say that what we are trying to do is actually to also change the mindsets. Like today, if you look at any typical power electronic system, you'll be dealing with really a multitude of isolation devices, each performing its own task, right? So in some ways, we feel this limits the system designer's ability to innovate on the power electronic side, because at the end, you'll be kind of limited by who's the middleman who sits in between the intelligence and the power electronics, right? So if the middle guy is not doing a good job, then there's really so much we can do, right? So we believe that that's where we will find a niche. that's where we will want to work with system people to come up with new ideas and new topologies that will actually make such system configuration much more efficient, much more configurable, for example. And definitely from a cost performance point of view, we believe that we can definitely drive that performance matrix as well.
Thank you so much, and we hope that answered that question. We have another question here, and this time it's from a gentleman called James Ong. James would like to ask, which market in which country presents the greatest growth opportunities for your technology? Mr. Lam, what do you think? Which country?
Okay, I have to answer this in two parts, right? Part one is that we have to first look at who are the incumbent players, right? You find that if you Google isolators, optocouplers, or things related to isolation technology, invariably you only find mainly American and European companies. And you saw my slides, right? You're talking of very big names like Analog Devices, Infineon, for example, European. But generally in Asia, you do have some, yeah, but they generally belongs to older generation of technology. Like for example, Toshiba still sell a lot of optocouplers, optical-based solution. I would say that if I were to suggest which country would we want to target most, I would think China and maybe emerging markets, where they do not have maybe certain historical baggage to deploy existing topologies or existing solution, and perhaps more willing to try new innovative ideas.
Thank you so much. Let us take a look and see if there are any more questions, any final questions from the audience. All right, I think we have finished all the questions that come in. Of course, we're also just nice, good for time. And with that, I want to thank you so much, Mr. Lam, for that comprehensive look at chip-to-chip communications and, of course, helping to give such wonderful answers to our audiences with their questions. Once again, thank you so much, Mr. Lam.
Okay, thank you, everybody. Thanks for your time.
Thank you. Truly enjoyed that presentation. And of course, this afternoon has been a really illuminating voyage into the future of wireless communications, which we will continue with a session on holographic MIMO communications after a short break to refuel before we take off once again. Do be back in your seats with your seat belts fastened in about 15 minutes time at 3 p.m.
Design is many things to different people. Most would associate it with art, fashion, and graphics. But that is only one facet of this multi-dimensional concept. Design, more importantly, is also the creation of human-centered solutions. They can be solutions to everyday challenges that make life easier, like adding wheels to your luggage to create the modern four-wheel suitcase. Or they could be solutions to global challenges that affect the lives of millions, like the creation of a shared network where information can be exchanged at any time by anyone at any location, what we now call the Internet. Design is the sum of ideas and expertise from different fields to create an effective, efficient, and sustainable solution. Nurturing design innovators is crucial to the continued advancement of humankind in a world bombarded by unprecedented challenges. They will transform our lives, drive innovation, grow economies sustainably. And at Singapore University of Technology and Design, also known as SUTD, our mission is to nurture the future generation of design innovators. Inspired by the evolution of design thinking, SUTD is revolutionizing design and leading the charge towards a new era of innovation. Students, of which 40% are female, are trained in design innovation and are immersed in a collaborative learning environment where they can easily go from concept to prototype, programming and testing. An interdisciplinary curriculum brings together 5-degree programs for more holistic and creative innovations, be it in education or research. We are united and inspired by a single-minded goal of improving lives and safeguarding our planet. We call this a better world by design. From autonomous systems that can learn and adapt, to new innovations in sustainable materials, design with the power of AI can help build smarter, more enjoyable cities, unlocking breakthroughs beyond our wildest imagination. It will also help power our economy to stay competitive into the future. Design powered by technology and AI truly is here to help us build a better world.
We produce 300 million tons of plastic every year, and 90% is actually missed, it's not recovered. It ends in oceans or ends in landfills. Plastic per se is not bad. I mean, plastic was invented in the 1930s, and since then, actually, most of our development in the last century cannot be understood without the benefits that plastic brought into society. The problem is actually also how society has become added to this material and the amount that we are producing and this lack of integration into the natural systems. We are not trying to remove plastic. We are not trying to go back 100 years on technology. What we are trying is completely the opposite. What we are trying to do is to bring materials that are they outperform plastic in many senses. They open like new possibilities and they enable to make engineering in a society that moves around biology, and by definition that society will be sustainable. So take for example the case of flam, right? The material that we made in collaboration with Stilianos. So this material is not only strong, but again, since we never modify the composition, like respect the natural molecules, it's actually perfectly integrated in the ecology of Earth. So flam is made out of cellulose and chitin. They are like the most abundant and second most abundant organic polymers on Earth. Cellulose is well known for everybody, is everywhere in green plants, right? Chitin is less known because of the lack of industrial uses. Chitin, for example, is the cells of the insects. The protective exoskeleton of the insect is made mostly of chitins. Same thing for molluscus and the sea cells. Actually, they are also made of chitin. So it's a molecule that nature is using in very different areas to make strong protective materials. In the Fermat lab, the lab that I lead in SUTD, we focus on the integration of biology in other engineering fields. We are setting the ground to what we call the biomaterial age, where biology will link and integrate with other engineering fields to bring them to the next level. In the case of plastic, what we are determining is to actually break this cycle of production and consumption of plastic in a non-sustainable way. And what we're trying to do is to set a new paradigm that is based on biological materials, where your materials are produced, manufactured into products, and degrade in closed regional areas. And actually they have like this kind of circular economy society embedded into the material itself.
So people need three things to survive on Earth: food, energy, and water. In our research group, we are targeting two of these fundamental challenges: water and energy. And we want to use low-dimensional nanomaterial to solve these two challenging issues together. Usually in the research community, some research group, they are targeting on solving energy issues, and some group, they are working on water treatment. However, in SUTD, we are focusing on one very unique area. We are trying to find one solution for these two challenging issues together. So in one of our projects, it's called the desalination battery. Basically, we desalinate seawater, ocean water, remove the sodium and chloride ions from the seawater. At the same time, we utilize the sodium and chloride ions to store energy. So we desalinate the water and store energy, making that two steps together. With these new solutions, actually we can supply fresh seawater, desalinated water to everybody in Singapore. At the same time, we can have low price energy storage being available to everybody. My big vision for this project is we can turn the entire ocean into a big desalination battery, a huge desalination battery. So everybody can enjoy the desalinated water and free power from this huge desalination battery. We are also looking at to recycle valuable resource from the seawater. For example, as we all know, lithium metals is one of the natural metal we can find in seawater. We're also looking at ocean mining to recycle those very valuable metal ions from seawater and then utilize them as battery electrode to store battery or for other purpose. I think by that way, we can maximize the nature resource we can achieve from the ocean.
Advances in material science often lead to huge increases in productivity and advancements in society. If you think about it, it's like the Stone Age, Bronze Age, Iron Age, they're all named after materials. And more recently, silicon and glass optical fiber led to the computer and the internet. So you can see that these technologies have had a profound impact on the way that humans live and behave, and also fueled the economy to a certain extent. And therefore, it's very important that we continue to design, discover and develop new materials. So we're studying chalcodrenide materials. These are materials that substantially consist of sulfur, selenium and tellurium, and they have fascinating properties. One of the properties I like and study the most is their phase change property, so they can exist in multiple states at room temperature. This is very different to most materials. Here we have an opportunity to switch them and use those to make devices that have switchable properties. So you might have experienced chalcogenides, especially if you're my age, when we were recording most of our data onto DVDs and CDs. They were actually the active layer in the rewritable CDs in the 90s and noughties. These materials have a number of applications aside from the technological applications that we're looking at in Actilab. For instance, chalcogenides are often used in solar cells, and they're used in thermoelectrics, also semiconductor devices as well. So in our group, we're moving away from some of the more traditional chalcogenide materials that other groups are looking at for data storage, and rethinking some materials that were once discarded for data storage applications and applying them to photonics. One of the big advantages of our group is that we can go through the whole process from conceiving an idea for a material, simulating it, testing it in the lab, or trying to create it and test it in the lab, and then fabricating a device. So we don't only do device design and we don't only do materials design, we do the two things in conjunction, and this gives us an extra degree of freedom because we're no longer limited by off-the-shelf materials or pre-existing designs. We can design the materials and design the devices synchronously for a specific application. We've recently found a material that has a very high transmissivity in the visible spectrum, and this is really useful for display technologies. We're currently working with A-Star, other universities in Singapore, to create holographic displays and beam steering devices based on these materials. And hopefully one day we'll all have a chalcogenide holographic display in our living rooms.
Some people may feel that the flipped classroom may not be such a good idea because you are unable to consult the prof in real time whenever you're in doubt.
It's mostly us learning by ourselves without much guidance from our professors.
Some students might think that there's no class, I can just watch the video at home.
Since it's learning on our end and we still have school, we kind of take it as something extra, like extra work for us to do.
Flipped classroom means that you're actually bringing some of this learning back to the students. We transform an hour of actual physical lecture into a flipped classroom. And this is usually done in a way that it is a pre-activity. So the students are expected to learn certain concepts through the lesson material online, outside of classroom, before they come to the classroom. And when they come to the classroom, these concepts will be further explored and applied in the classroom. Having spent more than a decade doing actual physical lab research, right? So this was my research in bone tissue engineering. When I switched fields, now that I'm a lecturer and I went to class, somehow the passion for research was still in me, which is why I decided to embark on a full-on research, pedagogical investigation about the effectiveness of the flipped classroom. From the research that we did at SUTD in 2015, this was just a flipped classroom model but without peer instruction. So I didn't have the assessment component, neither did we have the peer-to-peer discussion. And we found that it didn't work so well. And so in the following year, and this is after the talk by Eric Mazur, we decided that we will try putting in some things that he has said. And so this quiz, peer-to-peer discussion and a quiz again, reduced the anxiety that the students felt. They actually looked forward to learning, and we find that from our experimental results, actually 80% of them received a full score for the second quiz, which means that the peer-to-peer discussion really made a significant difference and that they learned very well from each other. Many institutes have tried flipped classroom, but sadly all they do is they throw in some videos and then maybe a quiz. And so for our students at SUTD, for the flipped classroom, they actually have, I would like to call it a package, a flipped classroom package, where they get the video recordings, the PowerPoint slides, as well as a keyword list. When we actually prepare flipped classroom lesson material, we take many things into consideration. So for example, we ensure that we break each lecture into maybe 4 to 5 mini lectures, which are about 10 to 15 minutes long. The other thing that we've included is this thing called concept quiz. So every time a concept is taught, so at the end of every mini lecture, there are a few questions that directly assess the learning objective. Because we've been testing them on a weekly basis, that by the time it comes to the exam, right, they are maybe desensitized, or you can say completely prepared. We did see an increase in exam scores that was significant over the years after the implementation of flipped classroom with peer instruction. We also saw that the students were punctual for class because we made sure that the quizzes were, it starts at the beginning of class. They were actually present, right? So that helps with our absenteeism as well. So the rationale for designing a flipped classroom is really the fact that we wanted to push some of the learning back to the students. We want them to have this self-directed learning skill. Every time we run this course, we actually collect feedback to make this learning experience better for the students. One of the things that we are also exploring is to see if we can use certain gamified lab simulations. So we are interested to see how we can use this, or even games, as a pre-activity, which I'm sure the students will find fun and engaging.
For flipped classroom, the e-learning, you are able to digest the information at your own pace.
It encourages self-learning.
I feel that flipped classroom is actually a good idea because it allowed us to go back and check all those concepts that we couldn't catch in class.
Welcome back. Hope you had a good break. And we are now going to take off with our next session right now with holographic MIMO communications. Now, today, massive MIMO is a mature technology. Its advantages in terms of spectral efficiency, energy efficiency, and power control are well understood and recognized. Now, this talk considers arbitrary, spatially stationary scattering and provides a representation that captures the essence of electromagnetic propagation and allows to evaluate the capacity of holographic MIMO systems. And to tell us more about this is a speaker who received the 2018 Marconi Prize Paper Award in Wireless Communications. His expertise and general interests span the areas of communications and signal processing. Ladies and gentlemen, let's welcome all the way from Italy's University of Pisa, Associate Professor Luca Sanguinetti.
Thank you very much for the introduction. Thank you very much for the invitation. It's a pleasure to be here and present my latest work in the context of MIMO communications. So let me share my screen. Okay, let me go full screen. Okay. Can you see my slides? Okay, I think we are good. Okay, the topic here is MIMO communications, and more than that is what I call holographic MIMO communications. I'll try to clarify the concept beyond the keyword holographic during the talk. Okay, for those of you that are not familiar with MIMO communications, let me quickly introduce you the concept. I mean, MIMO communications stand for a system with multiple transmit antennas and multiple receive antennas. And the coupling between the multiple transmit antennas and the multiple receive antennas is taken into account by complex coefficients, which I call here H and M. They represent the channel gain between the source antenna N and the receive antenna M. Now, MIMO communications have been around for a long time. So we have investigated so many possible MIMO configurations during the last 20 years. You can, if you search in the literature, you can see MISO communications where you have multiple transmit antennas and a single receive antenna, SIMO communications where you have a single transmit antenna and a multiple receive antennas, or you may have multi-user MIMO, which stands for multiple user equipped with multiple transmit antennas and multiple receive antennas. Now, the latest implementation of a MIMO technology is massive MIMO. Massive MIMO is one of the key technologies for 5G networks. And we are now looking for what is next. For example, cell-free massive MIMO is considered as the evolution of massive MIMO, and it's basically a massive MIMO technology where there are no more cells. All the access points, base stations, will serve jointly the users which are active in a given coverage area. Even cell-free massive MIMO has been around for a while, and there is a lot of research going on this topic. What I want to do today is to introduce you a different concept, which is what I call holographic MIMO communications. Now, to get even more familiar with the MIMO model, so no matter what you have in between the transmit antennas and the multiple receive antennas, you can come out with a very simple discrete representation of a MIMO communication system, which is which is this one basically, where Y is the receive vector, H is the channel matrix collecting all the channel gains, X is the transmitted symbol, and then you have the thermal noise. Now, if you want to assess the realistic performance of any MIMO technology, the key is to have a proper model for the channel matrix H. If you don't have a proper model, you may not be able to assess the ultimate performance of the MIMO technology that you have in mind. So modeling the channel is one of the major research problem in any MIMO communication system. So there are many different MIMO channel models in the wireless literature. They can be basically classified in two categories. One category is given by deterministic channels. The other one is given by stochastic channels. The deterministic channel models, they're very common in electromagnetic theory, and they have good advantages because they're very accurate for any given specific scenario. The way they are built is by using ray tracing approaches, recording channel measurements. So in this way, by using these approaches, you can come out with a deterministic channel model, which is very accurate for the specific scenario. The disadvantage is that you cannot use this model to measure the performance of the system, to assess the performance of the system in a different scenario. That's why in communication theory, we like to have stochastic models. They are based on different approaches. They do not depend on a specific scenario, and this is the advantage of stochastic channel models. The disadvantage is that there are several disadvantages, but the most critical one is that it's not very easy to build a stochastic channel model which is able to capture the essence of electromagnetic propagations. Let me give you an example. There is a very common channel model in MIMO communications, which is valid whenever you have line of sight propagation conditions, which means that you have a source, a receiver, nothing in between, and there is a line of sight connection between the source and the receiver. So in this case, the MIMO channel matrix takes this form where beta is the path loss, and then these two vectors are basically the array response vectors, the receiver and the transmitter. So the model is very simple and is composed, each array response vector is composed by plane waves in a very simple, it can be computed in a very simple way on the basis of plane waves. So if you use this model to evaluate the capacity of the MIMO system, the capacity takes this form, where these are the number of antennas at the receiver, the number of antennas at the source, beta is the path loss, P is the power, and sigma squared is the variance of the noise. As you can see in this case, the channel matrix is a rank 1 matrix because it's given by the two vectors. So we can achieve the full array gain of the system, which is given by the product of the number of transmit antennas and number of receive antennas, but we only have one degrees of freedom in the system, which means that we can only transmit one stream, one data stream. And the reason is why, the reason is because the channel matrix has rank 1. And this doesn't depend on the number of antennas that you employ, the transmitter and receiver. No matter how many antennas you have, you can still transmit one single data stream. But is this right? It is under the conditions for which the channel model is valid. Indeed, if you change the condition, and if you consider a more realistic setup, you can prove that by using very simple tools in electromagnetic theory, you can prove that whenever you have two surfaces that are communicating in a line of sight propagation scenario, the degrees of freedom of the system is given by the area of the receiver, the area multiply the area of the source divided by the wavelength square and the square distance between the transmitter and the receiver. So for example, if you have a transmitter with these dimensions and a receiver with these dimensions, so you have a 2x2 square planar surface, and the distance between the source and the destination is 10 meters, then the DOF, the degrees of freedom, the number of multiple data streams that you can transmit from the source to the receiver is not 1, but is 16 if you operate the system at the carrier frequency of 30 gigahertz, is 1,600 if you operate the system at the frequency of 300 gigahertz. So from these results, it's clear that there is much more to gain. In a line of sight scenario, by using classical channel models in wireless communications, we have only 1 degrees of freedom. We can only transmit single data stream. But if we use more accurate models from electromagnetic theory, we can gain and transmit many more data streams. And when I say many more, it depends on the frequency you are operating the system. So why we are not able to exploit the DOF of the system when we use, for example, the classical line of sight MIMO channel model. The point is that the classical MIMO channel model is not taking into account that when you increase the size of the receiver and you decrease the wavelength by operating the system at higher frequencies, we do not operate in the far-field Fraunhofer region of electromagnetic propagations, but we operate in the Fresnel near-field region of electromagnetic propagation. This is the condition to operate in one region or in the other region. So, for example, if you have a surface which is 1 by 1 meters, so if you operate the system, the frequency of 3 gigahertz, the distance above which you operate in the far field region and the classical MIMO channel models are valid is 20 meters. So if you are 20 meters away from the source, then you can use the classical MIMO channel models, which rely on the far field approximation. But if you increase the frequency of your system, then the distance grows. For example, if you operate the system at 28 gigahertz, the Fraunhofer and Fresnel region, they happen at the distance which is approximately 200 meters, and even more if you go up in frequency. So these near fields can occur at any frequency, depending on the distance. But even if you consider, for example, the sub 6 gigahertz frequencies, you see here that we can really enter in this near field region, and there is a lot more that we can exploit to improve the performance of the MIMO communication system. And this is precisely the objective of what we are doing in my group in these days in the context of MIMO communications. Since we are operating at high frequencies and we are operating with large arrays, we had to develop, revise the classical MIMO channel models, which are based on the far field approximation, to basically exploit all the potentials that the electromagnetic propagations can provide us. And this is precisely the concept of holographic communications. We want to come up with a system which is able to fully exploit the propagation characteristics offered by electromagnetics. In this way, this is the only way to exploit the ultimate performance of the system. Okay, so the holographic MIMO system, an holographic MIMO system is a system which relies on a channel model which is able to capture the essence of electromagnetic propagations. And then according to this model, you can build a system, a wireless communication system, which is able to exploit all the degrees of freedom of the channel itself. Okay, now we get into the more, let's say, technical part of the talk, where I'm going to introduce you the latest results that we have in this contest. I'll try to keep it simple. You can, if you're interested in the details, you can check the references that I'm going to list you in the slides. So, but if you think anything is missing, just let me know. Okay, so just to wrap up, the idea here is to have a MIMO communication system with a given number of antennas, the sorts, which are distributed over a planar surface, and then a given number of receive antennas, which are distributed over a receive planar surface. And the idea is to come up with a channel model for the MIMO channel matrix, which is able to capture the characteristics of electromagnetic propagations without leaving out some particular very important characteristics which are not taken into account by classical stochastic channel models. To do that, we simplify the system and we consider monochromatic and scalar waves. So we assume that the information is exchanged by using scalar waves, and which are transmitted at a given frequency. And then we assume that the scattering mechanism here is such that the electromagnetic MIMO channel can be assumed to be zero mean and spatially stationary Gaussian random field. So under these assumptions, we are going to develop a channel model which is approximately exact. I will clarify what I mean with approximately exact, but which will be simple to manage in the order to come up with a MIMO communication system which is able to exploit all the potential benefits of electromagnetic propagations. So the starting point is this observation. So any physically meaningful stochastic models must be based on plane wave expansions. Why? Because the plane wave expansion is a natural eigensolution of the Helmholtz equation, which is what is driving electromagnetic propagations. Now, plane wave model has been used in the wireless literature, but they have been used and developed under the assumption that the source and receiver are very far away. So in this case, you can approximate the wavefront as approximately planar over the entire array. This is the far-field approximation that I have talked about before. But since we are operating with very large antenna arrays and we are operating at high frequencies, this assumption is not valid. For example, this assumption here was used in the virtual channel representation pioneered by Said in 2002. However, this model here is valid only in the far-field region. So in this work, which we have recently submitted to Transactions on Information Theory, we show that under arbitrary spatially stationary scattering conditions, so you can take any scattering condition between the source and the receiver, the plane wave representation can be used to exactly represent wave propagation, no matter what is the distance between the source and the receiver. So the main result of this work is that no matter if you are operating in the far field region or in the near field region where there is a lot to gain, no matter of that, the plane wave representation can still be used to exactly represent wave propagation between the source and the receiver. Thanks to this result, we can come up with a quite simple representation of the channel between the source and the receiver, continuous representation of the channel between the source and the receiver, between any point at the receiver and any point at the source, which takes this very simple form, where AS here is the source response, which is basically the array response towards a particular propagation direction, which is indexed by this vector kappa. Then we have the receive response from a particular propagation direction, k. And then we have the angular response in between, which maps every incident direction, kappa, onto every receive direction, k. So these three components are enough to characterize the entire channel between point source and a point receiver side. And the integration here is not over the entire wave number domain. This is the wave number domain, but is over a disk which depends on the wave number of the system, which is basically a function of the wavelength of the system. Now, the angular response here can be decomposed in two terms. One is the power spectral density, and the other one is a Gaussian random field with 0 mean and variance 1. And the power spectral density is what we use to basically describe how the power is distributed in the angular domain. So if you want, in the wave number domain, between directions kappa and k. And the beauty of this model is that you can decompose, you can decouple the effect of the array geometries and the scattering. Why? Because the array geometry is basically represented by the source and receive responses and is a deterministic effect. The stochastic effect is entirely embedded into the angular response, which, as I said, is going to tell us how to distribute how the power is distributed angularly between the directions, the receiver, and directions, the source. And this power spectral density, if you start from the first principles of electromagnetics, is a precise structure which is given by this one. I'm not going to tell you why this is the structure. The important thing is that everything here is defined, is properly defined, except for this spectral factor here, which is arbitrary and which can be used to model any propagation conditions in the system. So if you have seen here, we have a representation which is given in terms of integrals. Integrals are good, but in communications or in signal processing, sums are better. So instead of using this representation, which is exact but given in forms of integral, we can actually look for a different representation, which is given in terms of sums. And the way to obtain that is quite simple, because it's like passing from a plane wave representation, which is continuous in the spatial domain, to a plane wave series, which is discrete in the wave number domain. So as I told you, I'm not going to tell you the details of these steps, because they are simple but tricky at the same time. What is important here is that we can get something which is very much accurate, but instead of being instead of being given in terms of integrals, it is given in terms of sums. And when I say the approximation is good, the approximation is good as long as the size of the array is bigger compared to the wavelength, which is the operating regime we are targeting in future wireless communication systems. And the important thing here is that the number of discrete plane waves that should be used to represent the channel, which is basically the cardinality of the sets here, is finite. Is finite and given by these two numbers. This is the number of finite discrete plane waves that should be used to represent the source, and this is the number of finite discrete plane waves that should be used to describe the receiver. So as you can see, they are like in the, if you remember, like in the line of sight conditions, they are a function of the area of the surface divided by the square of the wavelength. This is for the source and this is for the receiver. So we have a finite number of discretized plane waves that can be used to describe, to approximate the channel between any point at the receiver, any point at the source. Now, with this model, which is kind of simple because it is basically given by the array response, the receiver, the array response, the source, and then in between you have random coefficients, which are called coupling coefficients, which are Gaussian distributed with a variance, which is given by this expression here. So, as I said, mathematically speaking, it is simple, but the way to get to these results is a bit tricky. So let me try to give you some physical interpretation of this result. Okay, first of all, as I told you, everything here is fixed because this is given by the geometry of the array, the receiver. This is given by the geometry of the array and the source. In between, you have these coefficients, which are called coupling coefficients. So they play the key role here in this representation. Let me try to show you what they represent. They basically represent the coupling between two different angular sets between the source and the receiver. So basically, you transmit some power within this angular set, then there is a scattering mechanism, and then you receive some power at the receiver along different angular sets. So the coupling coefficients are basically measuring how much any source angular set is coupled with any received angular set. And of course, I mean, the strength of these coupling coefficients is not all equal, because it depends on the structure of the array, geometries, and on the scattering mechanism in between. The important thing here is that if you measure these coupling coefficients, you can understand two important parameters, key parameters in any MIMO communication system, which are basically the number of parallel channels, which are basically the degrees of freedom of the channel, and the level of diversity. To let you understand, so assume that I'm transmitting from these angular sets, and I'm receiving power at the receiver by over these three different angular sets. This means that the level of diversity is 3. So I transmit from a single angular set, and I'm receiving power from 3 different angular sets. So the level of diversity is 3. At the same time, I'm transmitting from different angular sets and receiving power from different angular sets. No matter what is the level of diversity, the different number of colors that they have in a network is basically giving us the degrees of freedom of the MIMO communication system, which means it's giving us the number of multiple data streams that they can transmit over the MIMO channel. Just to give you an example, this is what you get in the isotropic propagation conditions. Isotropic propagation conditions means that you're receiving power from everywhere in space. So if you consider the receiver only, and you assume that this is the ratio between the sides of the receiver and the wavelength, these are basically, this is the power that you get over in the angular domain when you have when the sides is, when the ratio is 10, and this is what you get when this ratio is 13. The reason why, as you can see, I mean, the number of angular sets increases as you increase the sides of the array is because you are basically increasing the sides of the array compared to the wavelength. So you're increasing the resolution, spatial resolution of the array. So in this case, we have more than 300 degrees of freedom. In this case, we have 3,000, approximately 3,000 degrees of freedom in the system that can be exploited. If you consider non-isotropic propagation conditions, the situation is different. You're not receiving power from everywhere in the angular domain, but you're only receiving power from particular directions, like in this case. But the situation is the same. If you increase the size of the array, you increase the number of degrees of freedom in the system. For example, in this case, the number of degrees of freedom is 34, while in this case is approximately 229. Okay, but there is a lot to gain, as you can see here. So now we have a model. Let's build the MIMO channel matrix. The first point to answer is how to sample the channel in the spatial domain such that the Nyquist sampling condition is satisfied. And you can reasonably prove that if you sample the array with a uniform sampling, then if the distance is smaller than half wavelength, the Nyquist condition is satisfied. So this means that we need to keep, for example, for the receiver array, we need to keep the receiver array with a number of antennas which is bigger than this ratio here, which is, if you remember, bigger than the maximum number of degrees of freedom that is available at the receiver. Now, the point to satisfy the Nyquist condition is this. Remember, we want to have an holographic MIMO communication. We want to exploit all the potentials of the electromagnetic channel. This is the reason why we should have a number of antennas which is bigger than this number here. Otherwise, we're going to lose some of the degrees of freedom of the system, so we cannot achieve the ultimate performance of the MIMO communication system. So by doing this, by sampling in the spatial domain the system according to the Nyquist condition, we can come up with a simple MIMO channel matrix, which has this form here. I mean, don't pay attention to how to get here, but pay attention to the structure of this MIMO channel matrix. So these two matrices here are deterministic and semi-unitary, and they're basically the DFT matrices if you sample the array uniformly in space. Then in between you have this matrix here, which is random, and this is the angular random matrix, which is built by these diagonal matrices here, which account for the shift, for the distance, basically. And then in between, you have this matrix, which is basically given by the random Gaussian matrix, and then the variances that we have, basically the strength of the coupling coefficients that we have introduced before. So once you have the coupling coefficients and you know the power of the coupling coefficients, you can build the channel matrix by multiplying with this Gaussian matrix here, take into account the propagation, the distance between the source and the receiver, and then applying these DFT matrices. It's very simple, and at the same time, it's very accurate to model the electromagnetic propagation between the source and the receiver. Since the number of modes that you have in the wave number domain, the angular domain, is much lower than the number of transmit antennas and the number of receive antennas, we have a low rank approximation of the channel. So H is a low rank approximation of the channel, of the electromagnetic channel, because we have a very large matrix, but inside we have a much smaller matrix, which is basically capture the sense of electromagnetic propagations in the system. Okay, so by looking at this model, since these are semi-unitary matrices, all the information is in the angular random matrix, which is a function of the strength of the coupling coefficients. So if you want to measure the number of parallel streams that we can transmit over the MIMO channel, we only need to measure the rank of the angular random matrix, which is given by basically the number of coupling coefficients that we have in the system. So this is given by exactly by how many colors here, different colors here we have in the angular domain. Mathematically, this amounts to look for the number of rows and columns in this matrix which are not identically zero. The beauty of this result is that no matter how many antennas we have, the source and the receiver, the number of degrees of freedom is given by the electromagnetic propagation conditions, which, as it should be. The ultimate performance do not depend on the array geometry, how many antennas you have, the source and the receiver. They depend on the electromagnetic propagation conditions. And the maximum can be achieved under isotropic scattering conditions, which is what I have shown you here. So under isotropic propagation conditions, as you can see, you receive power everywhere in the angular domain. If you have non-isotropic conditions, then you receive power from particular angular directions, and the number of degrees of freedom reduces. So the maximum number is given by can achieved under isotropic scattering, and is given by it depends on the area of the source and the wavelength, and the area of the receiver and the wavelength. There is an important message here. It doesn't depend on the thickness of the source and the receiver. It doesn't depend if you, for example, instead of using a plane array, use a volume array, then the number of degrees of freedom is not going to change. And this is a known result in physics, because I mean, what you can gain by increasing the thickness of the array is fully deterministic. So there is no extra information that can be captured by using a volume instead of a plane array. So the key consequence is, if you have a 3D volumetric array, no extra degrees of freedom can be achieved compared to a planar array, 2D planar array. There is another important message that I want to bring to your attention, is that if you compute the statistics of the channel according to the model that we have developed, it doesn't have a Kronecker structure. Why? Because the source and the receiver are not decoupled. With the model, the source and the receiver are coupled together. So the model does not have a Kronecker structure. And the other message here is that if you go to measure the covariance matrix is going to measure the correlation that you experience in the channel, in the spatial domain. And a possible way to quantify the amount of spatial correlation is by plotting the eigenvalues of the correlation matrix. So if you plot the eigenvalues of the correlation matrix by using the plane wave model that we have developed, as you can see here, and you compare, for example, with the Clark isotropic channel model, which is exact but relies on a different approach. So first of all, they match. I mean, as you can see, the eigenvalues are approximately the same. The degrees of freedom are given by this point here. So first of all, they match, and this is a way to validate our model. The second observation is that, as you can see, if you compare the behavior of the eigenvalues with the identically independent redefining channel model, which is quite common in the MIMO literature, as you can see, they're quite different. They are quite different, which means that you shall never use this model to model the channel matrix when you use planar arrays. Because no matter what you have inside, isotropic, non-isotropic propagation conditions, spatial correlation will occur because of the electromagnetic propagation principles. If you consider anisotropic, non-isotropic scattering conditions, then the eigenvalues distribution changes a lot, and then the number of significant eigenvalues reduces substantially because of the non-isotropic propagation conditions. But the key point is that If you compare the Rayleigh fading distribution, which assumes to have independent antennas, the source and receiver, with the plane wave model, they're very different because you have spatial correlation in the system. And the message here is that you should never use, when you have plane arrays, the Rayleigh fading channel model, because it's not able to account for the spatial correlation that naturally you have because of the electromagnetic propagation conditions. Okay, let me tell you a few words about the generation of the channel by using this model. It's very simple. Once you have measured the coupling coefficients, the strength of the coupling coefficients, which is given by the matrix sigma here, you just need to generate random matrix to compute the angular random matrix. Once you have the angular random matrix, you apply the migration filters, the propagation filters, which takes into account, the position of the source and receiver. And finally, you apply the DFT matrices, or if you want the semi-unitary matrices to obtain the channel matrix H. The system is very simple. The way to generate the channel matrix is very simple. And there is an alternative way which can be used, which basically relies on using the statistics of the channel, and which is given by this one. So you compute the statistics of the channel, you compute the eigen decomposition of the channel, and then you can generate the channel matrix according to the unitary matrix that you get from the eigen decomposition of the correlation matrix. Now, because of the equivalence between the angular random matrix and the H tilde matrix here, the propagation, the migration filters, they did not change the statistics of the channel, you can use this alternative approach. Let me tell you just a few more things. I can skip this one. So if you want to evaluate the capacity of the holographic MIMO communication system based on this channel model, you can exploit the semi-unitary equivalence between the spatial domain and angular domain. So you move in the angular domain, and then you can compute the capacity of the system, that since according to this new channel model, new input-output relation, which is now in the angular domain. To clarify, this is what we had. According to the spatial domain characterization of the MIMO channel matrix, you can move into the angular domain by using the DFT pre-processing and post-processing matrices, and then you move in the angular domain. The beauty of operating in the angular domain is that you simplify the signal processing algorithms, because they are not a function of the number of antennas that you have at the source and receiver, which can be huge, but it's a function of the effective degrees of freedom of the electromagnetic channel, which are much less than the large number of antennas that you can have the receiver and the source. Okay, going back to the model. So once you have this model, you can simply compute the ergodic capacity of the system. And then by using information theory tools, you can compute the capacity under the assumption of perfect knowledge of the receiver, perfect knowledge of the source and the receiver, statistical knowledge of the channel of the source, and so forth. You can use all the classical results, apply the classical results in the angular domain, and compute the capacity of this equivalent MIMO channel model. Just to give you some numerical results, if you use the model for evaluating the capacity of the system as a function of the SNR, this is what you get. So by using the plane wave model, so under isotropic propagation conditions, we see a perfect match with the Clark model, which is exact but derived under by using different tools. If you have non-isotropic propagation conditions, the capacity reduces because of the spatial correlation that you have in the system. And once again, if you use the uncorrelated rate definite model, you get very much better performance. But as I said, this model is not electromagnetic, is not physically meaningful, because any electromagnetic channel model should exhibit correlation in the spatial domain when you have a 2D planar array. So let me go to the conclusions of this talk. So the main motivation of this talk and the work we're doing in my group together with different colleagues is that we are operating high frequencies and we are operating with very large antenna arrays. So we should change the classical models that we have in the MIMO literature in order to exploit the fundamental limits of the technology. The model that I have introduced you is valid under arbitrary scattering conditions in the near field and far field regime, and is very useful to conduct research whenever you have large and dense antenna arrays, large compared to the wavelength of the system. So this is not the end of the story, basically, because the model can be improved by introducing the mutual coupling effect, by introducing polarized antenna arrays. But the hope that we have here is that we want to excite the interest in wireless communications toward physics-inspired channel models. And this is the only way, the only way to push the limits of the MIMO technology. What is missing is real-world measurements to support the theory and to correctly extract the model parameters, because everything is based on the coupling coefficients in the angular domain. What we need real measurements to support the theory and to extract the model parameters. This is the hope. I think this is the way to go if we want to get the most out of the MIMO technology. We need to go back to the physics principles of electromagnetic propagations. This requires a lot of thinking for people like me in wireless communications. But the beauty, the good news is that we are 10 years ahead from 6G, so we still have a lot of time to think and work in order to get the most out of the next MIMO communication technologies. And this is the end of my talk. Thank you very much.
Thank you so much, Associate Professor Luca Sanguinetti. And of course, we'll now move on to the question and answer segment. We've got some questions for you, Associate Prof. Now, our first question for you is, the proposed channel model has been used in your work to compute the spectral efficiency of MIMO systems. What other possible applications in which the framework can provide new insights? What is your answer on that one?
Yeah, the model, the point of the model is very accurate. It's based on electromagnetic principles. It can be used to understand the fundamental limit of MIMO communications. For example, it can be computed for analytically computing the degrees of freedom of the electromagnetic channel, which means it can be used to design the system in advance based on the electromagnetic propagation conditions that you have in the system. Indeed, we are doing some work to come up with new communication schemes that operate in the wave number domain, which means in the angular domain, and exploit the electromagnetic characteristics of the channel. That this is the main point of our model. We can design the system according to what will be out there, not based on models which may not realistically represent the electromagnetic propagation conditions of the system.
Fantastic. And we have another question for you. Let's bring those questions up. And this next question is, what is the machine learning in MIMO channel? Any work is going on currently? Does that question make any sense?
Yeah,
What
I
is
mean,
the
so if the question is how machine learning is applied to massive MIMO or MIMO technologies, the answer is of course, because machine learning is everywhere now, and since the MIMO technology is a key technology of wireless communication systems, there is a lot of work going on in the application of machine learning in MIMO communication technologies. So it can be used for it's used for many different reasons, many different goals. But my personal view is that if you want to use machine learning in any communication system, you should use machine learning whenever you cannot properly model or tackle the problem by using classical, techniques and algorithms, because machine learning is like a black box. You let the machine learning algorithm work, and then you get a solution, and that's it. So that my point is that you shouldn't apply machine learning just to apply machine learning. Apply machine learning whenever there is a lack in terms of theoretical tools that can be used to get a better understanding of the system. My work goes in the opposite direction. Instead of moving up, we're moving down at the electromagnetic level, at the basics of the propagation conditions, because this is where we can gain a lot.
Thank you so much for that answer. And we've just got enough time for one final question. And this one is, here we go. Research activities in the beyond massive MIMO context are carried out for passive or active surfaces, known as reconfigurable intelligent surfaces, or RISs, and large intelligent surfaces, or LISs. What is your view on the two different technologies?
Okay, my general view is that, okay, that's true. There is a lot of research in using large surfaces in a passive or active large intelligent surfaces. My personal view is that, since I'm coming from the MIMO world, and especially massive MIMO world, I think the future is digital, is not analog. So if you want to design a wireless communication system which is based on passive surfaces, I think there is a lot more to gain if we introduce some active antennas in the system, such that maybe passive and active at the same time, but by introducing something active, which means in the digital domain, we can actually improve the performance. This is the way to improve the performance of the system. If you rely only on a passive surface, maybe the gains will not be very much relevant compared to what we can gain, what we can achieve today with a fully digital communication system. So my personal view is that we should go for digital, at least in part, in large intelligent surfaces, and not only passive or analog large intelligent surfaces.
Thank you so much, Associate Professor Sanguinetti, for joining us from Italy with that insightful presentation on holographic MIMO communication, which we all enjoyed. Thank you so much.
Thank you very much. Have a good day.
Thank you so much. And of course, that was Associate Professor Luca Sanguinetti. And I believe we are now ready to go on with our next keynote. And this will explore localization in 5G and beyond, enablers, methodologies, and challenges, which will cover some of the main technological enablers for 5G and beyond 5G localization, and propose an algorithmic framework for localization and mapping, and also highlight a variety of challenges in designing future radio localization systems. Sharing more about all of this from Sweden, our next speaker is a professor in communication systems with the Department of Electrical Engineering at Chalmers University of Technology. His awards include an ERC starting grant and a Chalmers Supervision Award. He also leads the CrossNet team at Chalmers. Ladies and gentlemen, please welcome Professor Henk Wymeersch.
Thank you and good evening. So let me first try to share my screen. Can you confirm the screen looks okay and that the audio is working?
Looks perfect.
Thank you. Good, so first of all, let me thank you for inviting me to present here on this work on localization. I've been working on radio localization for now 15 years, and in the beginning it was a very small and niche area, but now with the introduction of 5G and 6G it's becoming more prominent. Before I go on to the technical part, I just want to briefly mention where I am from. So this here on the right is a picture of Sweden. On the left side is the star. This is Gothenburg, which is Sweden's second largest city and the home of Volvo. Chalmers is a private technical university founded in the early 1800s, and I am part of the communication systems group, which has 9 professors in the area of physical layer communication, ranging from fiber optical communication to wireless to hardware limited systems and AI. Good. Now, to get started, I like to pose the work that we do in the form of a challenge. So this is what I call now the 5G Beyond Positioning Challenge. And incidentally, this picture is from downtown Singapore. And of course, when you drive with a taxi in downtown Singapore and you look at the GPS, you notice that the GPS doesn't work. And this is basically because the GPS signals are blocked by all the tall buildings around. And then this immediately leads to a need for a more advanced positioning system that can work in these dense urban scenarios, as well as in indoor environments such as parking garages. Okay, and the way that we phrase this problem is as follows. So suppose that you have a base station on the rooftop of a building equipped with a multi-antenna system. You have a user equipment in the vehicle, also with multiple antennas. And then we want to send a downlink signal from the base station to the user. And this is typically the kind of positioning signals that are sent in 5G today and 4G as well, but then from several base stations. But now we only have a single base station. Of course, this signal goes over the complex multipath environment. And then the question that we ask is the following. From the signal from a single base station in downlink, in an unknown propagation environment, can we localize the user? Can we synchronize the user to the base station? And can we also say something about the orientation of the user, for instance, the driving direction? And you could argue that this is already a quite tough challenge. But we will make it even harder. We also want to provide radar-like mapping capabilities. So we want the user to map the environment to figure out where the buildings are and where the other moving objects are. Next, we want to even do this when the line of sight is blocked. And this can happen when there's no line of sight because of an obstacle. And then still we want to localize the user. This becomes formidably hard. And finally, we want to use these intelligent surfaces, which was incidentally also discussed at the end of the previous talk, as a way to shape the propagation environment and support positioning and radar capabilities, not just communication. And I hope by the end of this presentation, you are convinced that all of these are indeed possible. So this will be the outline of my talk. I will start with first a brief basics on the idea of radio-based positioning, and then move on to the concepts within 5G and beyond 5G positioning that are being explored right now. Then I move on with a little bit more mathematical flavor into how 5G positioning really works. So going back to this downtown Singapore scenario, how does it really work? And then based on the available time, I will also go on to talk about beyond 5G positioning with intelligent services before wrapping up with conclusions. Okay, but let's start at the beginning. So the main idea of all radio-based positioning systems is that the radio waveform tells you something about geometry. And this is a picture here that I take from my wireless class at Chalmers, where there's a source on the left side of this building, there's a destination on the right, and a wideband signal is sent from the source to the destination, going over this environment. And if the signal has sufficient bandwidth, this is what the receiver will see. So it will receive as a function of time or delay the received signals. And you see that the signal is very much resolved in delay because of the large bandwidth. And the first arriving path could be from the direct line of sight, and then the other paths could come from the multipath components that arrive later. Important is that each of these multipath components tells you something about geometry. The question is, of course, how to exploit that information. Now, in practice, a receiver will not have access to this very wide band information, but have other kind of measurements such as signal strength, time-based measurements such as time of arrival or time difference of arrival, and angle measurements such as angle of arrival and angle of departure. And I will go through most of these later. Once you have these measurements in place, you can then fuse them or combine them to determine a position. And in positioning, there are two important criteria. The first one is resolution, and the second one is accuracy. And I want to spend a minute on this because they are often confused. So resolution refers to the ability to distinguish multipath in some domain. For instance, in the picture above, you see that two multipath components can be resolved if they are sufficiently far in delay. If they cannot be resolved, they will be blurred together and you have no hope of estimating the delays of the individual paths. So resolution is an important limitation in positioning systems. The second one is accuracy. Accuracy refers to the ability to estimate a single path that is resolved. And accuracy depends mainly on the signal-to-noise ratio. This means that if you only have a single path in your environment, the accuracy can be arbitrarily good just by increasing the SNR. However, the resolution cannot be improved by increasing the SNR. All right, so with these ideas in mind, now positioning is a kind of classical statistical estimation problem, right? You have observations, you have a likelihood function which describes a statistical model, and you want to infer the hidden variables, the positions. So this means that we can rely on all the tools from statistical estimation theory. For instance, performance bound, using Fisher information theory, a wide variety of algorithms ranging from geometric algorithms, maximum likelihood algorithms, convex optimization methods, and also ideas from Kalman filtering and particle filtering and so forth. We also can use, for instance, the bounds for signal optimization to optimize, for instance, where should base stations be, how should the measurements be designed. And of course, we need to deal with several practical aspects. The most important among those is probably synchronization. As you know, for instance, in GPS, a GPS receiver doesn't just position itself, it also synchronizes itself to the GPS constellation. And without this ability to synchronize, time-based measurements become basically useless. And because the synchronization requirements are so tough, we are also immediately faced by severe hardware limitations. And this will be a theme that I think will occur more and more in 6G. Nevertheless, the field of radio-based positioning is a kind of very safe research field in the sense that whenever people in communication come up with a new technology, we can reuse this for positioning. And this has happened, of course, for instance, for the idea of turbo coding in the 90s, massive MIMO a decade ago, and now, of course, for instance, the intelligent surfaces and artificial intelligence methods coming up now. Good, so this is a bit of background on radio-based positioning. How does radio-based positioning work now in your cell phones? So how it works now is through something called time difference of arrival, where in uplink, as you can see in this picture here, a user would broadcast a signal to several base stations. These base stations are perfectly synchronized and connected to a fusion center. The signal estimated at one base station would provide it with a time of arrival estimate. So the time of arrival estimate at base station I would be the distance between the user and base station I over the speed of light, plus the clock bias of the user plus noise. And so this clock bias refers to the lack of synchronization between the user and the base stations. And this bias is dependent on the specific user, not on the base stations, because as I said, the base stations are all mutually synchronized. From these time-based measurements, you can compute differential measurements. So you take one base station as the reference and compute its difference measurements, and there now the bias is gone. So these different measurements are basically differences of distances. And differences of distances can be geometrically captured by a hyperbola. And this is what's shown on the figure on the right. So there are three base stations here. One of them I call the reference, and then I can compute two time difference of arrival measurements, and each of these gives rise to a hyperbola. And then the user is on the intersection of those hyperbola. Now these hyperbola are a bit blurred because of the limited resolution, and this is due to the limited bandwidth of this system. Okay, so you cannot accurately localize yourself. You have some error of maybe 50 to 100 meters in this case. The nice thing is that it is really scalable. You need very few transmissions per device, but you're limited by the base station placement and of course the bandwidth, which is an effect of the multipath non-resolvability. This is what's happening now. So what is the vision towards 5G and 6G? So this is a picture I took from this paper from a few years ago. And there they predicted that future location methods within 5G would provide very accurate localization, so down to below 1 meter for indoor and urban outdoor scenarios, complementing existing radio-based technologies. And there's a lot of radio-based positioning technologies. For instance, GNSS, so GPS, GLONASS, Galileo. They can operate really well, providing high accuracy, but only when there's sufficient line of sight. So it only works in kind of nice outdoor scenarios. We also see 2G, 3G, and 4G, as well as wireless LAN technologies. And each of these are somehow limited because of their resolution, so they have accuracies above 1 meter. Now, again, this was a paper from a few years ago. Now 5G is really here, and we didn't actually realize this 1 meter vision. So if you look at what's really possible, it is something between 1 and 10 meter, not 1 meter. So then one of the authors of this paper actually revised this figure. So this is now the updated vision. So 5G is now shifted to the right, so it can provide accuracies down to 1 meter, but not better than that. And now we replace 5G with 6G, and the hope is now that 6G can provide this very accurate positioning, even in very tough indoor environments. Now, a reasonable question is, why would this be possible? What are the technological enablers to get these amazing accuracies? This is what I will talk about now. So what are the selling points for 5G and beyond 5G positioning? So, of course, 5G's positioning has been studied for a number of years, and I think a kind of nice paper from a European cost action is this one here. And there it is highlighted that there's a number of properties in 5G that are conducive for positioning. They include high carrier frequency, so the shift from sub 6 gigahertz to about 24, 26 gigahertz. The use of larger bandwidth, so up to 400 megahertz in 5G. A large number of antennas, and here large could be maybe 16 or 20 at definitely the base station side, but maybe also the user side. Device-to-device communication and network densification. So this was the vision for 5G a few years ago. Now, when we look at 6G, things are a little bit different. So the first 5 enablers are more or less the same, high carrier frequencies, but now instead of just going to 24, 26 gigahertz, we will also go up to and above 100 gigahertz. We'll have large bandwidth, so much more than 400 megahertz, maybe 1 to 10 gigahertz of bandwidth. Now, because we go to these high carrier frequencies, we need to counter this with large antenna arrays. We'll have hundreds of antennas, probably at both the transmitter and the receiver side. We will keep device-to-device communication for relative positioning. We will also need network densification because otherwise the links will be too short. But what is new in 6G is the technologies of meta surfaces, which will allow us to shape the environment, and the use of AI and machine learning to solve some of the harder problems. Now, a question that is kind of commonly asked here is, based on this, will 6G just be 5G plus? So will it be 5G but just a bit more challenging? I think there's a variety of answers to this. I think from my point of view, the most important difference will be when we go to this 100 gigahertz carriers and above, is that we will be much more hardware limited, which means that we from the communication or the positioning fields will need to talk to the circuits people to really understand what is happening and how to mitigate the impairments, and in some cases even to exploit the impairments. And this of course has implications to the waveform. So it is doubtful that 6G will be able to use OFDM, for instance, for the reasons of amplifier backoff. Another interesting thing is when we go to these very high carrier frequencies, the wavelength will become much shorter, antennas will become much smaller, but of course from a localization perspective, objects remain the same size. Objects don't move faster, objects don't shrink. So this has a scalability implication. For instance, when we use smaller antennas with more fine beams, we need to send many more beams in a wide variety of directions to map an environment. And this then incurs more delay. So these are some of the challenges that I see that will be different in 6G than in 5G. Nevertheless, I will spend now one slide each on each of these technological enablers and to clarify why they would help positioning. The first one is the use of high carrier frequencies. So what I show here is also kind of textbook example of a transmitter, a receiver. Let's say both transmitter and receiver have multiple antennas and they operate in a multipath environment. So there's a channel matrix in between the transmitter and the receiver. And if you imagine the transmitter and receiver each has 10 antennas, this is a 10 by 10 matrix, right? So with 100 degrees of freedom in principle. And if you open any textbook from the last few years, they would say to the students, in order to generate this matrix, you would just populate it with IID, complex Gaussian numbers, because that's what represents Rayleigh fading. And this is all fine and well at lower frequencies, but does not fit very well at higher carrier frequencies above 28 gigahertz. In that case, channel models tend to become more geometric. And this is because there is no shadowing anymore and the propagation effects are different. So when you open a millimeter wave paper at these frequencies, you will see a channel model that looks like this. So the channel is the superposition of a small number of paths or clusters. So L would be maybe 3 to 5. Each of the paths would be characterized by a complex channel gain, alpha L, a delay, tau L, so that's the propagation delay of that path. And then you have these A vectors, these are the response vector at the transmitter and the receiver, and they depend on transmit angle, so this theta TXL is the angle of departure at the base station, in this case the transmitter, in the frame of reference of the base station, and theta RXL is the angle of arrival at the user side in the frame of reference of the user. And when you look at this, of course, you see that all of these parameters, except for the channel gain, are geometric. So these are very relevant for positioning, because now you have more measurements that you can get from your observations, which tells you more about geometry, so good for positioning. All right, so high carrier frequencies are good because they provide a sparse communications channel, highly resolved in terms of multipath, related to the physical environment. Secondly, large bandwidths. Large bandwidths are good because they allow you to resolve multipath in the delay domain. So this means when two paths are arriving at very similar delays, with a low bandwidth, they are blurred together. But when the bandwidth increases, they become more and more resolvable. And this is what's shown, for instance, here on the right. This is a picture I took from this paper from almost a decade ago now, where they did measurements using 2 gigahertz of bandwidth, where the transmitter was fixed and the receiver was moving. And what you see here in each of the rows is the impulse response as a function of the delay tau in different positions. So as the receiver is moving, you see that this is first a path would be the line of sight path. Okay, before the line of sight path, there is no power, but you see here the kind of resolved line of sight path. But you see other kind of patterns emerging here, and these correspond to resolved multipath components. So each of these trajectories corresponds to some object in the environment. Of course, the object is not moving, only the user is moving, but the geometry keeps changing because of the user mobility. In any case, large bandwidth gives you a high degree of resolvability of multipath in the delay domain. And this is also the property that is used in automotive radar, for instance, to get very good performance. In addition to having large bandwidth, we will also have a large number of antennas. And again, in 5G, this will be maybe on the order of 16 or 20. 6G could be on the order of 100 or more. When you have a large number of receive antennas, you get more angle of arrival resolvability. And this is what is shown here on the picture on the right. So I show the angle of arrival on the x-axis. The y-axis is, you can imagine, as a kind of likelihood function. When I have very few antennas, even in the presence of 2 paths, as shown in this figure, I get the blue curve. So I see basically only one path because the 2 paths are blurred together. When I use more antennas, the 2 paths become resolvable. So a large number of antennas at the receiver is very good because it provides you angle of arrival resolvability. Similarly, but not precisely the same, when you have a large number of transmit antennas, you can send narrower beams, and this in principle gives you better angle of departure resolvability. An angle of departure resolvability is very important because it allows you to localize a user, for instance, with angles only. So for instance, if I have a base station here on the left, a user on the right, the base station has many antennas, the user has only one, then the user can estimate the angle of departure from the base station to the user, so it knows it's on a line from the base station towards itself. So this provides lots of geometric information. In any case, large arrays are very good because they provide angle resolvability, which will then be complemented by delay resolvability, as mentioned before. Next, we have device-to-device communication through side links. Now, side links is a somewhat controversial topic, but let's assume that side links will be there. These then provide measurements between devices. So this means that I could provide angle and delay measurements between devices, which then would in turn enable cooperative position technologies, but also radar-like mapping capabilities. So even if neither of those 2 devices are connected to the infrastructure, by sending these 5G or 6G waveforms, they could determine their relative position and cooperatively map the environment. Next is network densification. So we'll have many access nodes, so base stations or transmitting reference points, which means that we'll have a high chance of line of sight connectivity. And of course, you can already intuitively imagine that the line of sight link is the most important one for positioning. The non-line of sight paths are useful, but they're not the most useful ones. So we really like to have line of sight links between the transmitters and the receivers. And well, basically, in order to allow communication, this would be generally available. When they are not available, then we need to look at alternative technologies such as intelligent surfaces. This brings me to my next point. So there's been a lot of talk right now about reconfigurable intelligent surfaces. These are comprised of a plurality of very small elements with controllable phases, and this could be controlled in different ways. They are passive, so they don't introduce noise, and they could operate in different ways. So when a wave is coming towards the surface can be reconfigured to reflect back the wave in a non-natural direction, and the direction that it's reflected can be controlled. An intelligent surface could also operate as a lens, so that the wave would go through and it could be focused in a certain direction. Now, this has been used a lot in communication. So for instance, here is an example with a source to destination and an intelligent surface. And now this intelligent surface could provide a controllable high SNR link towards the user, even when the line of sight is blocked. And this has been studied a lot in communication, but from a point of view of positioning, these are also very interesting because they provide new positioning references. If you know where they are, typically they will not move around. So you have to know where they are, what their orientation is. You can use them as reference points for positioning. You can control their SNR, and you can also get a variety of measurements from them, including delay and angle measurements. I will talk more about that later. And then finally, the seventh selling point of 5G and beyond 5G is the use of AI. Okay. So there are problems where the relation between the observation of the channel and the location is really hard to figure out because there is no good model. And in that case, you could, for instance, train a neural network with labeled data. So you provided a bunch of channels, maybe converted to some embedded domain as shown in the picture here, with as supervised labels the user location. And then a neural network could learn the mapping from the channel to the user location. And this can provide also very good performance within this environment. Now, in general, I think AI has amazing potential, but my vision has always been to use it to solve those problems for which we don't have good models. If there is a good model and there's a well-known technique that can solve it, we should use it because that provides explainability, provides ways to do optimal design and so forth. But for those problems that are very challenging, for instance, when we have hardware impairments or the concatenation of multiple nonlinear and stochastic blocks, that's where AI, in my view, really shines. Good, so now we go back to the outline. So I hope now that you've convinced that 5G and beyond 5G have a lot of attractive properties for positioning. Let's go back to our downtown Singapore scenario and look in a little bit more detail what's really happening. All right, so the figure on the right shows a more abstract vision of the downtown Singapore scenario. There's the base station here shown in blue. There's a user, which is the car. The user has an unknown position, shown here as X, and an unknown orientation, shown as alpha, and is also not synchronized to the base station. Right, so the base station sends a downlink signal, and then the signal reaches the user via the line of sight path, shown in blue, and there could be also several multipath components. So the first multipath component can be going through this small object S1 to reach the user. Okay, so and I show this here as a small object like a lamp post, and this object is determined by a position. So it has a 3D position, which I don't know. There could also be large objects in the environments like a wall, so this is what's shown here. And then the signal goes from the base station, bounces off the wall, and reaches the user. And the point where the signal bounces is denoted here by XS. Now, a problem here is when the user is moving on the road, this incidence point, XS, will also move. So this is happening, for instance, when you drive by a skyscraper and you see the sun reflected. As you drive, you see the sun moving. So this is not maybe the most useful way to describe a building. So if we want to map the environment, we need to have a state definition of all the objects in the environment. And for this, what is usually done is that a large surface is described, the state is described by a so-called virtual anchor. So this is XVA. And XVA is the reflection of the base station with respect to the wall. So it's behind the wall here, and this is a fixed point. So this means when the user is driving, the incidence point on the wall will move, but the virtual anchor, which kind of the points from virtual anchor to instance point to the user, this virtual anchor location will be a fixed point. So this means that the virtual anchor is a nice and compact representation of a large surface. So you already see that the scenario becomes a bit complicated. There's the user, which is unknown, the state is unknown. There are objects in the environment which have an unknown state, so we could have small objects and large objects, and we don't know anything about where they are. So this is really the problem. So we want to estimate the user position, clock bias and heading in an environment with a transmitter, which has a known position, and then reflectors and objects, scatter points, and we also want to reconstruct the map. So we want to figure out the state of S1 and XVA, if possible. The way that we do this, we start from our standard millimeter wave received signal. So this is this Y of t. This depends on some pilot signal, X of t. So there are dedicated positioning reference signals that are sent. They could be pre-coded with a matrix F, because maybe the signal resides in a low-dimensional domain, and then F brings us to the antenna domain. Then it goes over the channel, and the channel, as before, is described by a few multipath components, each with a channel matrix depending on a channel gain. The receiver response factor with angle of arrival theta L, the transmitter response factor with angle of departure phi L. And then at the receiver, there could be a combining operation, bringing again back from a high-dimensional antenna space to a low-dimensional space. And this is what the receiver has, this Y of t. And now it needs to figure out where are all the objects in the environment. Now, the observations that the receiver can extract from this, we will denote by ZL. So if you have a parametric channel estimator, that can estimate ZL, which comprises for each path the delay, angle of arrival, and angle of departure plus noise. And there are standard channel estimators for this. I will talk about this in a second. And now, there's actually a very easy mapping if I know everything in the environment. So if I know where the user is, so the state of the user, if I know where all the objects in the map are, then I could compute all of those delays and angles. So that's the kind of forward model. The challenge is, of course, that I need to invert this relationship. So I'm only given angles and delays. I need to invert to figure out the user state and the map. And that's really the hard problem here. There's an additional challenge and an opportunity. The challenge is that from the observation Y, we could compute these measurements Z, and these are tuples in this case of 3 dimension, but we do not know which of these tuples corresponds to the line of sight path, which of these tuples corresponds to a previously seen object in the environment, which of them corresponds to a new object, or which of them just corresponds to a noise peak, so clutter. So that's a challenge. So there's a so-called data association problem. On the other hand, there's an opportunity, which is that for each object in the environment, there are 3 unknowns, right? There's X, Y, Z of that object. But if I have a 3D environment, I have 5 measurements, because I have the time of arrival measurements. And then I could have angle of arrival and azimuth and elevation at the user side, and angle of departure and azimuth and elevation at the base station side. So this means that with enough objects in the environment, I have way more measurements than unknowns. So then, in principle, I could have a chance to solve the problem. It also means that when there's no multipath in the environment and I only have line of sight, in that case, I cannot solve the localization problem. Right? I do not have enough information to determine where the user is. So this really shows that in this case, we use the multipath to our advantage. Of course, when there's no multipath, then maybe you wouldn't use these technologies. Good. Now, still the problem is quite complicated, so we break it down into smaller sub-problems. So this is how I would say the flow working between communication and positioning. So most of the time you have communication, because you don't need to position yourself every microsecond, maybe every 10 or 20 milliseconds is enough. Every now and again you will send a positioning reference signal or a sounding reference signal downlink to the user. The user then would observe this observation Y of t. It would then do channel estimation to estimate angles and delays. It would then do a data association to match which angles and delays correspond to previously seen objects. And then I would run a positioning and mapping routine to update its own state and map. And then, of course, there will be mobility, and you have these 2 loops operating concurrently. I will just spend one slide on each of these just to show what are some of the interesting problems that could occur. So the first one is in terms of the signal design. So in positioning, right now the base station is using a so-called positioning reference signal. This is basically a signal that spans the whole frequency band to have enough bandwidth and is orthogonal among different base stations. But there is no real spatial signal design. So a meaningful question is then, how should the base station signals be designed to have the best possible angle estimation? Okay, and this question is a little bit ambiguous because you could have angle of arrival and angle of departure estimation. And then you could solve these problems through a convex optimization approach. So let's look just at some of these. So the figure on the right shows what is the best signal that the base station should send for the user to estimate its angle of arrival as good as possible. In this case, both the base station and the user have multiple antennas, otherwise the problem is not meaningful. And this problem is also only meaningful when you have some side information of where the user is. So we assume this user is inside of this yellow sector, otherwise there's no meaningful signal design that you can do. And what it turns out to be the optimal solution is that you should send a sequence of beams which provide a kind of uniform coverage in this, yellow area around 90 degrees. And what this means in turn is that you should kind of blast as much energy as you can towards the user and as little as possible towards other directions. So the signal design is somehow very intuitive. Things become a bit more involved when you think about angle of departure optimal design. So now you can think of a scenario where the base station has many antennas and the user only has a single antenna. And you want to design a signal at the base station to help the user estimate the angle of departure from the base station to the user. So there is no angle of arrival anymore because the user only has a single antenna. And then when you solve the corresponding optimization problem, you see that the beams you should send look something like this. So they have a lot of emissions outside of the desired band. And this is needed in order to, within the desired band, to have lots of fluctuations. So you see these different beams, they fluctuate a lot in the angle of departure. And these fluctuations is really what helps the user to figure out what is the true angle of departure. And then you could, of course, combine both of them to have precoders at the base station that are good for both angle of departure and angle of arrival. And I foresee in 6G, when we want to track individual users, we probably want to design such pilot signals for the positioning individual for each user or for user groups. So I see this as an area that will gain more importance in the future. The second one is channel estimation. So given the observed waveform, how do we estimate the angles and delays for each path while maintaining the per path association? So we want the channel estimator to provide tuples of delays and angles, not just a bunch of angles and a bunch of delays, because then it's hard to figure out which one is associated to which. Now, this is a classical problem already. So, and the way that this is typically solved is by exploiting the sparsity in the beam space domain and then solving this using compressive sensing. And doing this, of course, provides you much higher accuracy than just figuring out what is the beam direction. So right now in 3GPP standards, what is happening is that the base station sends a number of beams in different directions. The user measures the energy, and the beam with the largest energy, that will be the nominal angle of departure. But that would give a very poor angle estimate, and by using these compressive sensing methods, you can do much better. Now, I don't want to explain in detail how this works because it's somehow classical, but conceptually what you do is you take your observation, which is a high dimensional object, and then you convert it to a domain where the sparsity becomes clear. This is just what you do when you have a natural image and you apply a discrete cosine transform to convert it to a domain where you see that all the energy is concentrated in just a few of the components. And in this MIMO scenario, this would be called the beam space domain. And in this beam space domain, you can read off the angle of departure and angle of arrival up to a scaling. And you see these different peaks. And each of these peaks now, they correspond to a propagation path. And once you have the location of the peak, you can figure out angle of departure and angle of arrival. Of course, the problem is a bit more complicated because we don't just have a two-dimensional problem, we have a much higher dimensional problem because we have angles of arrival in azimuth and elevation, angles of departure in azimuth and elevation, and delay. So it's a kind of five-dimensional structure that we need to consider. If you want to play around with this, a few years ago I put this GitHub MATLAB code online, which generates a scenario for positioning with objects. It generates a waveform, solves this compressive sensing method, and then positions the user in 3D. Next is SLAM. So now that once we have the measurements, we have the delays and angles, now we need to figure out where is the user and where are the objects in the map. And there are a lot of techniques for SLAM. One of them is the so-called PMBM filter, which stands for Poisson-Multi-Bernoulli filter. And the Poisson-Multi-Bernoulli filter is very attractive because it's a conjugate prior for many problems. So this is just like a like the Kalman filter. The Kalman filter, the Gaussian distribution is a conjugate prior for the linear Gaussian model. This means that when you do prediction and update step in the filter, the posterior distribution is still a Gaussian and can then be used as a prior for the next time step. So this is also what happens here with the PMBM filter, but in a much more complicated scenario. In the PMBM filter, you represent the user state with particles, and then condition on each particle you have a map. And each of these map comprises a so-called multi-Bernoulli distribution, which is, you could see as a bunch of Gaussians, basically. And then in addition, there's a so-called Poisson point process, or PPP, which represents all of the objects in the environment that you haven't measured yet. So they're objects that you think may exist, you don't know where they are, but you haven't received any measurements yet. And then there exists, of course, an update and prediction step for this multi-Bernoulli filter, which is what we use in our tracking routine. So this is what the image on the left will show. So there's a car moving around in an environment. There's a base station in the center. The user is this black circle in the middle. This dome represents the objects around it that it can see. So it kind of captures the field of view. In the beginning, the user only knows where the base station is, and it has some prior of its own location. And you will see it moving around, and as it moves, it will map the environment. So it will try to figure out over time where are the objects. So it needs to figure out the small and large objects. It also has clutter measurements, so it will generate false hypotheses and so forth. Now, the PMBM filter is a quite complex filter. The way that it works is it basically generates all possible associations. So for each measurement you get, it will say, okay, it could have come from this object, from that object, or from a new object or clutter. And each of these hypotheses are weighted with the likelihood function. And you just keep track of all these hypotheses over time, remove the low weight hypothesis, and then you get performance like this. And I think this is among the state-of-the-art filters for tracking. Good, let me go to the next slide. Now, just to give you a little feeling of how this then works in the end. So this is an example from a paper that we did a few years ago. This is a two-dimensional example. So on the left side is the transmitter with location Q and known orientation, known position. On the right is the user with an unknown position and an unknown orientation. So we need to estimate this P and alpha. And then there are some objects in the environment, and we do not know where these objects are. Okay. And now the receiver observes the waveform, will estimate angles and delays, and tries to map the environment. And now I hope you have at least some intuition that this is possible, right? Because for each object in the environment, you have two unknowns, but you get three measurements: the angle of departure, angle of arrival, and the delay. Okay, so you have more geometric information than unknowns. So the way that we solve this problem is we first apply this orthogonal matching pursuit to estimate angles and delays, and then we apply a standard nonlinear least squares to figure out the position. And of course, then you could extend this to other cases with more sophisticated algorithms. And then this is an example of the performance we get. Okay, so on the x-axis is signal to noise ratio, y-axis is the RMSE, so how well the estimator is. In red is the performance bound based on Fisher information theory, and in blue is the estimator performance. So we see that we get close to the bounds for high SNR, and this is not a very sophisticated estimator. When the line of sight is blocked, what do we get then? Then we get this performance. So we see that we can still localize the user, and you can still operate close to the bound. Okay. And again, even though the line of sight is blocked, because we have enough objects in the environment and enough measurements, we can still solve the problem. And again, we do not know a priori where the objects are, we don't know where the user is, and there's no line of sight. So this is an extremely challenging problem, but still with this kind of relatively simple methodology, we can solve for all the unknowns. All right, so this is the end of my part on 5G positioning. Now I'll move beyond 5G positioning with intelligent surfaces, and that will be the last part of this presentation. So there are different terminologies for these intelligent surfaces. There's LIS, ILS, RIS, IRS, reconfigurable metasurface, and so forth. Some of them mean slightly different things, but I will call them RIS, so RAS, reconfigurable intelligent surfaces, and they will function the following way for a communication application. So this is a figure taken from this paper from 2019. On the left side is a base station, on the right side is a number of users. The line of sight is blocked towards the users. Because if the line of sight was there, probably you want to use only the line of sight and not use the RIS at all. There's a channel from the base station to the RIS. There's a channel from the RIS to each single antenna user. And the RIS itself is characterized by phases. So each of these elements has a controllable phase. And this allows us to write the observation model at each user as follows. So the observation at a certain user is a transmitted signal, the channel matrix from the base station to the RIS, the phase control of the RIS, and the channel from the RIS to the user, plus noise. And now this omega can be changed in such a way to maximize the SNR. And this is basically leading to a high power beam from the RIS to the user without any amplification, so without any noise. Of course, you can extend it when the line of sight is there. And one of the main applications for this is to overcome line of sight blockage and coverage holes. An important challenge in RIS applications is to estimate the channel. So to estimate the channel HBR and HRU is actually really challenging because the RIS cannot estimate anything at all. It doesn't have any RF chains. Now, of course, since RIS has been widely studied for communication, there's now also an interest for localization. And these are figures taken from this paper here. An obvious application would be to do localization when line of sight is blocked, right? Because then the RIS, they provide signals just as a base station would with known position source. A RIS can also be relatively large electromagnetically, and this could lead to near field effect. So we could exploit the wavefront curvature to better localize the users. And there's a number of applications that are considered. So for instance, as localization in very harsh indoor multipath environments, as well as localization in high dimensions, so 6D localization of position orientation using this RIS. Now, what RIS can do, in principle, it can do two things. It can boost performance or enable localization. So boosting performance means that when you have 3 base stations and you put a RIS there, without the RIS you could localize, and with the RIS you can localize better. Similar for radar, so without the RIS you could do radar, but when the RIS is there, the radar performance will get better. So this is boosting performance. What I think is more interesting is to enable performance. So this means that when there is no RIS, you cannot localize. And we will see 2 examples. So one is single base station localization with line of sight, and the other one is single base station localization without line of sight. Now you say, hang on. You had already talked a lot about single base station localization. It is possible anyway. So here we make the scenario a bit more challenging by focusing on single base station localization with a single antenna. Okay. So in this case, the 5G positioning does not apply. All right, so let's look at this case of single base station localization with line of sight. The scenario is shown here on the right. So there's a single base station with a known position, has a single antenna element. There's a user, also has a single antenna element, has an unknown position, and then there's a RIS on the right with a known position and known orientation. This orientation is shown here with a coordinate system. So if there's no RIS, you have no way of localizing the user, because the only measurement you get is a delay measurement, and this puts you on an infinite number of balls around or spheres around the base station. So you cannot solve the localization problem. Now, when the RIS is there, you get additional measurements. So the following measurements are available. There's the line of sight delay. Then there's the delay of the path from the RIS. Oh, I'm sorry, I didn't mean to do that. And there's the angle of departure from the RIS to the user. This angle of departure you can estimate by changing the RIS phase profile over time. So this is similar as you would do in angle of departure estimation for analog phased array. Now, the time of arrival measurements, you can compute their difference, and that provides a time difference of arrival measurements. And the time difference of arrival measurement leads to a hyperbola. This is shown here in red, and in 3D it would be a hyperboloid. The angle of departure measurement gives you a line. This is shown in green. This will be a line in 2D, but in 3D, of course, it would also be a line. In either 2D and 3D, the intersection of this hyperbola and the line gives you a point. So this allows you to localize the user. Once you've localized the user, you can figure out the clock bias from the line of sight delay. And what I show here on the left is as a function of the position here, the error in localization for a very simple processing algorithm and including the bound, so we get very close to the bound. Now, so what is important here is that the RIS on the right acts like an additional base station which is synchronized by the primary base station and has a phased array. So that's basically the functionality that the RIS fulfills in this case. So this is another figure showing the same thing. So this is a top-down view with the base station here on the bottom, the RIS on the left, and I show here the position error bound. So this gives an indication of how well I can localize the user in this environment. And you can see when you're behind the wrist, you cannot localize, of course. And in the environment, you can localize well when you're close to the wrist, because that's when the path loss plays in your favor. It turns out when you're behind the base station, there's this small area where you cannot be localized, and there's some beautiful geometric interpretation for that. Now, nothing is stopping you from putting a plurality of wrists in the environments. You could have 3 wrists, and then you can kind of provide a uniform coverage even with a single transmitting base station. A challenge is, of course, how to estimate parameters from the several wrists, but the way that you can deal with that is by having orthogonal temporal codes for each of the wrists, and then the user can separate the line of sight path or the uncontrolled multipath from the paths from each of the wrists. All right, so now we'll make the problem even a little bit harder. Let's remove the line of sight. So in this case, the user only has the path from the wrist. So the scenarios here shown on the right, there's a base station with a certain location, there's a wrist shown here, and then the user could be anywhere in the deployment environment. If the user has line of sight to the base station and line of sight to the wrist, we now know that they can be localized, as shown before. But if the user is in a shadow of an obstacle, then the line of sight is blocked, then only the wrist is available. So this means that the delay measurement you have to throw out, okay, because we can no longer compute time difference of arrival. But what we can do is now exploit the wavefront curvature to localize the user. And now this is shown on the figure on the left. So this is shown the XY coordinate. The red triangle is the base station. The small green star is the wrist. And then the user can be anywhere here. And I'm showing the position error bound in dB meters. So 0 means 1 meter and minus 10 means 1 centimeter. Oh, sorry, means 10 centimeters. Okay. And if we work in far field, so we use a far field model, then the user can be localized again when it is close to the wrist, and otherwise it has some degradation. When we use the near field model, so we exploit the wavefront curvature, then we see that the user can be localized even in the shadow of the obstacle. Of course, there's a severe degradation because we no longer have the very favorable line of sight path, but localization is still possible. So this is something that can provide a kind of location continuity to bridge these gaps when the line of sight temporarily is blocked. So RISC has several benefits for positioning. There's also benefits for radar. And I tried here just to show the most extreme challenging cases with a single antenna base station with and without line of sight availability. So where does this go next? And this will then lead to the end of my talk. So right now, 5G and 4G have mainly focused on communication. When we will use more bandwidth and more antennas, the introduction of AI, the use of radar and sensing within the 5G and 6G system, a more dominant inclusion of localization and the way and an ability to adapt the environment with intelligent surfaces. And this will be leading to one combined 6G system that has all of these ingredients. And I think worldwide this is now appreciated that communication will probably not be possible at very high frequencies without having localization and sensing capabilities built in. There are a number of current EU projects that are investigating this, including the HexaX flagship project and the RISE 6G project, so which all try to define what 6G will be. There are many new enablers towards 6G, which leads to many new applications and opportunities. There are also severe challenges, such as the hardware limitations and link budget. If you want to know more, there was a white paper that was published last year, which was led by the 6G flagship in the University of Oulu, on the vision of 6G localization and sensing. So let me now conclude. I hope that even if you didn't know, now you realize that radio waves can provide geometric information which is useful for localization. This is what GPS is built on. This is how 5G positioning works and Wi-Fi localization. When we go to high frequencies with large bandwidths and many antenna elements, this becomes a very interesting regime for localization. In 5G, we can do single anchor positioning using multipath information. We can do heading estimation, synchronization, environment mapping, all with a single base station. And we can operate a new kind of radar, maybe not at very high resolution for some applications, but still it can have some radar capabilities. And of course, this is now studied in 3GPP. Beyond 5G, we see great potential for intelligent surfaces to boost localization performance and to enable localization. In contrast to communication, we typically like the line of sight path to be present when combined with a RIS, because that's really what provides us the diversity of geometrical information. Also, I think beyond 5G, as I mentioned before, communication and localization, they will go hand in hand. The communication can probably not work without the localization present. Nevertheless, there are many unanswered questions. There's an urgent need for measurements and hardware-compatible models, especially for beyond 5G, where hardware will be a main limitation. In general, I'm very happy to establish new collaboration. You are very welcome to contact me on this email address. I want to acknowledge several of the funding agencies that helped fund this research. And finally, I hope that in the next 10 years, when I show this picture, which shows two cars and this kind of red signal in between, and you ask me, is it radar or 6G or maybe 7G? I think the answer will be, it will be one and the same system. And with that, I thank you for your attention.
Thank you so much, Professor Henk Wymeersch, for that very insightful presentation. And we're going to move straight to the question and answer segment. I believe we have a few questions from our audience, starting with this one. What do you see as the main challenges towards 6G localization and sensing? Prof, what do you think?
Without a doubt, it is the hardware limitations. Everything changes when we go beyond 100 gigahertz. We need to include effects of IQI imbalance, phase noise, amplifier nonlinearity, transmitter receiver, mutual coupling effects. All of these effects will be much harder to deal with than for communication. In communication, you care about the end-to-end channel, right? The overall channel matrix is what you care about. For localization and sensing, you care about each of the geometric parameters inside of that channel. So this means you're affected by each of these hardware impairments severely. So we need ways to model these hardware impairments correctly and ways to mitigate them.
Thank you so much, and I hope that answered the question from our audience. Our second question that we have right over here is, are waveforms for localization and sensing different from those for communication? Are they?
That is yet unclear. I would say that any waveform for communication that has enough bandwidth and uses the angular resolution of the system well is suitable for localization and sensing. So my vision is that there will be a single waveform that will be parametric, for instance, like OFDM, where you can change the numerology, you can change the power allocation, and this flexibility will be used in one way for communication and another way for localization and sensing. But the underlying waveform will very likely be the same.
Thank you so much. We have a third question over here, and it is this. Will 6G localization offer something substantially new compared to 5G localization, or is it just better performance? What do you think?
I think in localization, the main difference will be better performance in terms of 3D positioning. So I do think it will be possible to go down to 10 centimeters or even lower. It will also allow more parameters of the state of devices to be measured. So not just the 3D position, but also the 3D orientation of devices, which is important for several applications. But in addition to localization, I think also the sensing aspect is important. 5G does not provide very good radar capabilities because the bandwidth is too small. But when you go to 6G, where you have multiple gigahertz of bandwidth, you become competitive with radar technologies, right? And I can imagine that a 6G radio unit can also serve as a radar for automotive applications. So these will be some of the main differences. And finally, because of the propagation effect at these very high frequencies, it is also possible that 6G waveforms can be used for spectroscopy or imaging applications that are not possible now. For instance, pollution monitoring or tissue imaging.
Thank you so much, Professor Wymeersch, for that very inspiring presentation on localization in 5G and beyond, and for answering all those questions from our audience. That was truly a wonderful way to end our day. Thank you so much.
Thank you very much. Good evening.
Thank you so much. And of course, that was Professor Henk Wymeersch with the final keynote for today. And of course, want to thank everyone. Thank you so much for your kind attention and participation so far. And of course, our gratitude as well to our sponsors and partners that have made this international workshop possible. Thank you to the generous sponsorship of Huawei International Private Limited, MPIX Innovations Private Limited, Roder and Schwartz Asia Private Limited, and the support of the IEEE Communication Society. Thank you very much to our sponsors and partners. Now, ladies and gentlemen, there's even more amazing content tomorrow as we continue with 4 more speakers. We'll be having Professor Vincent Poor, who'll be talking about towards 6G wireless communication networks, vision, enabling technologies, and new paradigm shifts. We'll have Professor Kai-Xue Ma talking about generalized multiple tanks and applications for silicon-based RF MM-wave IC. We'll also have Professor Marios Kontouris, and he'll be talking about rethinking communication theory for wireless network systems. And finally, we'll have Professor Lin Dai on random access for machine-to-machine communications, connection-based or connection-free. We're truly looking forward to all of that. We'll see you tomorrow right here at 9 a.m. Thank you, everybody.